All right, we're going to get started. So, welcome to day 2 of the FERC Software Conference. We will be dual tracking all day, which means that we will have sessions both in this room and HR1, the room next door. We're going to get started in a second, but first I wanted to remind everyone of the ex parte concern. So, please try to avoid topics that might be ex parte for FERC. We know you're doing your best, but just wanted to flag that for you. In addition, today is going to be a little bit of a longer day, so hang in there. And there are snacks upstairs, and water and coffee if you need them. And speaking of which, I'd like to remind everyone that food and drinks are not allowed in the CMR or HR1 other than water. So to get started here today, we're going to have Kat Wong and AJ Lambert from Tapestry and PJM presenting Tapestry's AI-enabled interconnection automation software, speeding grid interconnections and enabling dynamic planning and operations. Sorry, it was a mouthful. Thank you. Go ahead, Kat.
All right, good morning, everyone. My name is Kat Wong, and I am the head of the technical operation at Tapestry, Alphabet Moonshot for the electric grid. While waiting for the slide to load, you can actually go to the next one. And today with me is AJ Lambert from PJM. We're going to present together. And it is our privilege to be here at the FERC Software Conference to talk about how we are translating advanced AI into practical solutions for our energy futures. As both of us are electrical engineers and been working in the industry, we know the complexity of this challenge here that we are facing, and also the importance of having reliable grid operations. Next slide. All right. So this over 100 years old grid is going through a huge transformations. And we've been hearing a lot about grid modernization, decarbonization, and electrification, and now a lot of topics around AI. To meet this moment, we need a grid that is as intelligent, efficient, and also resilient as the technology that is powering. You can go to the next slide, please. And this precisely where AI can offer a transformative opportunity to address challenges that FERC is also keenly focusing on, such as resource adequacy and interconnection efficiency. But in order to have AI to be transformative, it has to be useful. Next slide, please. And we believe this requires strong cross-sector collaboration. And that's why we call ourselves Tapestry. We are weaving together wealth technology, information, and industrial partners to build a grid that can power our future. Next slide. So Tapestry is born out of X, Alphabet Moonshot Factories, that building on a 15 years legacy on applying AI to real-world physical problems. Alphabet has decades of experience making the impossible possible. We map the world with Google Map. A lot of us been using today, and it helped me to get here this morning. We made it possible for computers to see the world with LiDAR. And AJ mentioned yesterday that he saw a couple Waymo driving around in DC. And now we are making the grid visible. Our core mission is to make the electric grid visible and intelligent so everyone can access reliable, affordable, and clean energy. Next slide. Many of our Alphabet breakthrough technologies start with a powerful questions. What if? So we ask ourselves, what if we could make Google Maps for electrons? What if we can make the world electricity system as intuitive as to navigate as Google Map? So we start with those what if questions and start building our technology from there. Next slide. And building on Google's best-in-class geospatial technology, we're able to map the grid, just like they map the world. And AI analyze diverse data and able to assess the physical grid, like the transformers, transmission tower, distribution energy resources, and providing crucial real-time information on asset status and also potential issues. With AI, we're able to clean and validate data with the goal of creating an accurate and unified model of the grid. So how exactly can AI help with this? Next slide, please. At its core, AI uses data and algorithm to perform tasks like problem solving, data analysis, and learning, tasks that traditionally required human intelligence. And similarly, AI need large, high-quality data and learn so that they become helpful. Just like similarly how human learned, that you continue to learn more with good quality of data, good algorithm, and then you'll become proficient at it. Next slide. And we're creating the world's first knowledge graph for the grid, analyzing diverse data to map and access the physical grid in real time. Think about Google Search Knowledge Graph. It builds connection from web data and connect the relationship between all this different data to understand things like Lincoln Memorial is a monument that is dedicated to Abraham Lincoln, is located in the National Mall in DC areas, and who's its architect, and at the same time associate historical event with it. So we're building a knowledge graph for the electric grid that analyze all this data that are available in the grid to understand things like transformer A is at substation X, having a breaker and a half configurations, and at this time is operating at certain load. And by the way, potentially it has showing some sign of degradation. Maybe you want to do something with it. And our foundational step to make the grid visible is similar to analogous to Google indexing the internet and Google Map for electrons. Next slide. So powered by Tapestry Grid Knowledge Graph, our unified platform combines data, machine learning and AI, simulation, and all the collaborative tools that we're developing to make sure that we can effectively manage, plan, and operate the grid. We focus on deep AI to tackle the complex real-world challenges for the system here. We've been applying machine learning and AI to the grid for many years, working with different industry partners that we have to train our model and continue to refine our technology for intuitive and impactful tool. Next slide. We understand that the current approach has been using data that can be siloed and also model that created from them can be disconnected. And having all this siloed and disconnected data and model and tool can be pretty painful when you make a change in one of the model and you need to make changes to all the other associated model that you need to analyze about. This can be extremely difficult to track all the change and make sure that data are consistent across all the model and studies that you're doing and make sure that they are updated. So to tackle this huge problem here, we're developing a first kind of a unified model approach. Next slide. And with this approach, we unlock data fusion and stakeholder collaborations. This is not only to eliminate the update needed between model and data manually, but also enable different stakeholders like operators, developers to track all the changes with a more controlled way to know that what is happening, no need to really, move between models and update the data and information manually, and access and make the vision needed in one place that they can all see with each others. Next slide. As we all know, energy is a global issue, and so similar to what we've done with Waymo, we need to learn from different geographic and environment. While every country has its unique insight and challenge, the physics remain the same. And so we don't really need to relearn all the time. We can share insight across the industry. And we've been operating globally with partners in 6 countries, demonstrating the universal need for these solutions. And we've been focusing on transforming the way the world make, move, and use of energy. And by partnering with innovative partners, we can design practical AI power solutions that take AI out of the lab and put it into the real world. Next slide. Taking the lesson learned from the partners around the world, we apply them to the largest electricity market in North America, PJM. We recently announced a multi-phase initiative with PJM. For the first time, AI will apply to transmission planning end-to-end. We first focus on interconnection automation, modeling, and collaborative platform, and more to come. Next slide, please. So the first part of our work will be developing AI tool to streamline the interconnection application process. I have this beautiful GIF here that unfortunately is not working. Otherwise, you'll see how we can illustrate some of the features that we're developing here. So the key focus here is to automating and approving data verification process for things like land right, equipment and grid impact, to aim to reduce the burden for PJM planners and also energy developers, so that we can significantly reduce the time that it takes to process all this new project application, and they can connect online much faster. And this is only the first part of our collaboration work together, and there are more to come, and we'll be very happy to share more in the future. Next one. With that, I'm going to pass it to AJ to talk more about the first part of our work and why AI is needed from his perspective.
Thanks, Kat. My name is AJ Lambert. I'm the Interconnection Planning Projects Manager at PJM, and our group handles interconnection applications all the way up until commercial operation for interconnection projects. So PGM is, we're excited to partner with the Google and Tapestry team. We see Google has the experience of technology and AI, and then PGM has the experience or knowledge of our tariff and also the interconnection process. And we think kind of combining those two skill sets will really allow us to see some real value and improvements in the overall process. So kind of describe in the next few slides kind of our thought process and kind of our strategy for going about making these improvements. So go next slide, please. So I'm sure it's no surprise, but I wanted to just kind of take a step back and look at why we're here. And the graph here kind of shows that we've really over the last few years seen an explosion or a significant increase in interconnection applications in PJM and really across the entire country. So PJM recognized that. We saw the large increase and really that the old process just didn't support this new scale that we were operating at. So a few years ago, we did file with FERC and received approval for a new process. So the old process that we had was just not designed to operate at this scale. It was a first come, first serve. Our new process is a cluster based and really focuses on readiness. So we've termed that first ready, first served. So right now we're implementing a transition plan to get to this new process. And ultimately, our goal through the new process and leveraging the technology that we're building with Google is really to get to an inbox zero. So our goal is to clear out the backlog of old projects that we have and move those forward so that they can ultimately inject energy onto the system, but as well as provide a predictable and repeatable and timely interconnection process. So we think kind of, again, leveraging the skill sets of both the Google team and PGM that we could be successful. So if you go to the next slide. So, kind of just to, again, like describe the process here. So the old process we mentioned was first come, first serve. Then the new process really dramatically changes that. It's now a cycle-based process. So we're studying these in a collection of projects. And there's also an elevated readiness factor associated with that. So the goal here for PJM is to ensure that the most viable projects move forward. And while my team, we have this new tariff, which is great. I think for us, the next challenge is how do you actually go about implementing it? And the new process has some inherent challenges based on the cluster base of it. So one of the challenges of implementation is all these projects move together. So how do you develop reports and issue them on the exact same day for all the projects? How do you put all the projects on the same decision point and have them make decisions within the same window and organize that, kind of choreograph that process? Then similarly, how do you then review could be 500 or 1,000 applications all at once and do that in a timely manner? So there's the new process. I think we're very confident will set us up for success here to be able to operate at this scale. But we recognize that there's definitely some different implementation challenges that we need to address, which is why we're looking for artificial intelligence and new technology to help us efficiently implement that. The next slide. So our old method of doing things was just throw more people at the problem. And I think going back several years ago, it was a constant theme in our stakeholder communities, hire more people, hire more people, hire more contractors. And I can say that we did that. We definitely hired more people. But I think we recognize that every new engineer or every new contractor you hire offers, a diminishing return, kind of just a law of economics. So what we're trying to do with Google, the creativity that and out-of-box thinking that they bring is really now rethink this process. So how can we, rethink to gain more exponential returns on the investment as opposed to just throwing more people at the problem? And the next slide kind of talks about what we're trying to go after. So if you go to the next slide, please. So again, with the expertise of Google and technology and PGM's understanding the process and really where are the pinch points in this process and where do we see the most amount of time being spent? There's two specific things that we're going to be going after with Google. It's automated document verification and then automated model validation. So with the automated document verification, I mentioned one of the key aspects of the new process is the readiness requirements. And we think it's very important for the projects to demonstrate their readiness and their ability to eventually inject megawatts onto the system for us to be considered in the cases and put into our model. So again, with this elevated readiness requirement comes in the challenge of you have to have someone to review it. So there's some administrative challenges associated with that. Now we're getting could be again 500 to 1,000 applications at once, and we're getting more readiness documents associated with that. So how can we? The old way of doing it was we would assign an engineer, an analyst, or a lawyer to review these documents to ensure that they're compliant with a tariff. But with the help of Google, we're looking to leverage AI to help us do these checks in real time. And I think our ultimate vision is to provide not only support to PJM, but eventually support to the developers as well. So we can just create a more, customer support really tool for this overall interconnection process. So I'd say that's more of on the administrative side where we can leverage technology. And then also on the technical side, we're looking to automate some of the model validation. So again, when we have hundreds or up to 1,000 projects coming at us, they're all unique. They all have different technical characteristics, and quite frankly, maybe the data given to us isn't always right, and we have to ensure it's a high quality and accurate before we go and build our models and run the study. So it's really important that we have high quality data. So the current way of doing it is we have engineers review all of that data, kind of just hand over hand, working with the developers, clear up any inconsistencies. But with Google, we're hoping how can we use AI to really kind of do those checks in real time and help us very quickly identify any critical parameters that may be out of spec and provide that feedback to the developer. So that will allow us to build these models cleaner. We can run the studies quicker. We can get the reports to the developers quicker, and then it allows them to make a more informed decision in kind of the synchronization of this process. So for a PGM standpoint, we see it as both an administrative challenge in implementing the new tariff, as well as a technical challenge of this new tariff, and looking to leverage technology on both sides. And we really do think you have to have both to be successful. If you just solve the technical piece and not the administrative piece, you may not recognize those time savings. So we want to be able to run this process efficiently and then also run the technical studies efficiently to recognize the most gains. So our ultimate vision here is really being able to turn what is currently weeks or honestly even sometimes months into minutes using this technology that we're building with Google. Next slide. So I think really going back with Google, they have the expertise of technology and artificial intelligence, and PGM, we have a very strong understanding of the tariff and what requirements are needed for interconnection. And we think leveraging both of those skill sets will allow us to build a process that is both smarter, faster, and scalable, and again can help us build a process that's repeatable and predictable and it's timely so we can process these and ultimately get more megawatts onto the system. That's all we had. If there's any questions.
Good morning, and thank you for the presentation. My name is Vishnu Bhatrai. I'm from Orchid. Very quick question, especially there are multiple steps you showed, like potentially I can use to make it faster. I'm more curious on the one of the item you put was on the model side, right? Model verification. That's where I'd see like relatively harder part. Can you share a little bit more insights, your thoughts on how AI can help, especially on those model verification or running some of those studies? That's where I do see like the biggest challenge. Thank you.
Sure. In a high level, when we learn from PJM and AJ's team is when the application is submitted, you have multiple places to enter those information. You may have a file that contains those model. You may have a place for you to enter those information online when you submit the application. At the same time, you submit a one-line diagram to show some of the parameters. So the first step is really to make sure that all the data enters are consistent. If there's any discrepancy between them, how can we really using artificial intelligence to flag those inconsistency? That's the first steps. And then after we make sure that this data are consistent with each other, then the next step is really looking if the data makes sense or not. Are they in the range, or is there any other rule or intelligence that we can apply, like an engineer looking at the data that, okay, those data make sense. Instead of a 9999, it should be, say, 100. And that's the next step is after the consistency, and then it's really about the accuracy. And then the last step is really sometime what engineer will do is they will run through simulation and see if those results also make sense. Because in the past, when I was running studies, I sometimes copy and paste and then make an error. And then when you look at the result, you're like, doesn't make sense. But when you're just looking at the data itself, it's really hard to determine. So it's really a multi-steps for us to really do this verification. And we all believe that like data have three main problems: inconsistency, inaccurate, and incomplete. So how can we leverage artificial intelligence to really fill in all these three gaps?
Hafiz Bazafshan from Habitat Energy. Thank you for your presentation. I'm just curious to know whether the scope of work is just for transmission, or is it like the map for electrons? Is it going all the way to distribution and three-phase systems or not? Thank you.
So we are working with different partners in the industry on both transmission and distribution side. Right now, our work with PJM will be focusing on transmission, but we do look into the future working with them on the distributed energy resources on the distribution grid, or also sub-transmission areas, because they do bring an impact onto the transmission side. And with other partners that we've been working, as you saw earlier on the map, that we've also been working on the distribution side. We have different products that focusing on the distribution work, that including mapping the distribution system onto the map, and also planning work as well. So if you're interested, we can talk offline and I can share more with you.
Rob Homer from Energy Zone. Thank you for the presentation. Just a quick question on the kind of where you are in the project. So it sounds like you guys are pretty early. Can you give us some sense of, what your timelines look like, where you're kind of testing or validating results at this point? Thank you.
Yeah, we are pretty early on, but we're working with Google and kind of looking at what is the current PJM transition timeline, and really trying to find kind of the key milestones to support that is what we're looking for. So even coming up in potentially like TC1, TC2, some decision points. So I'll say some internal tools we're going to look to leverage to help us better perform those reviews. So there's a short time frame for some internal tools, and then we have more of a long-term roadmap as well where we could start to expand that.
Yeah, and to add on, our work with PJM started this year. So to your point, it can be early on from that perspective. And we've been working with other partners, including the one in Chile, that we've been working with the system operator called SEN over there for a couple of years already. So our technology is really building on what we have learned from the past and continue to iterate and improve and work with PJM on their need. And we're planning to have an operational tool by the end of the year to support what AJ mentioned on the transition 1 and transition 2.
Hello, my name is Wong from Good Insights. Thanks for the presentation, and we're really excited to see finally AI is coming into our lovely interconnection industry. I saw that one of the slide you have a two AI model. One is the document verification, and then the second one is the AI model verification. So such as voltage and Qmax and Qmin. But right now, PGM's dynamic model guideline is kind enough to say what to do for the interconnection customer. And then checking those voltage and then Qmax and Qmin and dynamic model parameters are straightforward to check using some APIs, using PSSC or other method. So how AI will like improve or enhance any of that, process? Because that is already given answer is right there.
So we're still pretty early on in the model verification, but our vision there is when developers submit the information, there's this, like you mentioned, the dynamic modeling guideline, there's certain requirements associated with that. There's other documents, single line drawings that they have to upload. And kind of our vision is how can we really help automate that review process to make sure that all the data that's submitted is in accordance with the PGM requirements, and then it all makes sense. So if there are times maybe where we collect the same information twice, but if there's conflicts, that we could have a system that identifies that and flags it, really to speed up this review time. So right now we assign engineers, we have contractors, so we really deal with a large. Just transition cycle 2 is over 500 projects. So we're looking at over 500 projects and all their associated technical details. And it takes time for humans to go through and verify, is all the information consistent? Is it in accordance with the requirements? There's a back and forth associated with the developers to correct any issues. And we think that kind of leveraging this automated validation, it can help immediately flag those to speed up the review process. So we do this in the new process. We collect technical information at the application, decision point 1, decision point 2, and even decision point 3. So if we have to do that same review 4 times, right, and it could be a different engineer, right, if people come and go the company. So really we want to be recognizing the kind of the importance of it in ensuring high quality data and how many times we have to do it. We think there's a lot of significant time savings in automating that review.
We have one question from the online audience. It was asked anonymously. The question is, what benchmarking is anticipated for model validation and simulation, for example, power flow modeling?
So as we mentioned here, we're still early on in our process that we definitely look into benchmarking. And on our platform, we have simulation tool that we're running to compare results. And that's been ongoing work for us to continue to benchmark and work with PJM with their expertise to make sure that the results are in the acceptable range.
Thank you.
My name is Felix Wang from Great Insights. Kat, I think this is a question for you because you mentioned there's some ongoing project with Chile and their system operator. So is there any plan to leverage whatever you guys have used, work with Chile and use that or similar things going to help PGM to do transmission planning?
Definitely. So our work in Chile are mainly focusing on a long-term planning studies that cover 20 years of analysis, focusing on how we can leverage the renewable resources that they have in their grid, because in Chile, they have a challenge of having a lot of renewable, but sometimes because of congestion, they're not going to be able to really provide the full powers. And the studies that we've been doing with really understanding how where congestion are and how they can really leverage all this renewable provide continue to expand into our other partners, including PJMs. Like right now, as you heard from AJ, we're starting with the data verification and also the modeling. And the next step is to run simulations. So that is as a multi-phase project that we're working on, we definitely will leverage what we learn and continue to apply.
Yeah, thank you. So can you elaborate a little bit more on what kind of simulation you're running or planning running with this PGM? Is it power flow? Is it like a market simulation? Or is it like something like AI-based tool? Because I think people here, have a lot of knowledge about, what kind of market simulation. But it seems like the problem in Chile is it's a market issue. It's a congestion issue. You can run SCAD to review it. So are you guys having your own SCAD engine? You're running on your own software, or you're using other, vendor software?
I can get offline with you on the detail, but we are working with different technology partner to have different tool and software on our platform. So we are not building a lot of our own software. If there's we're not reinventing the wheel that is out there already. If there's great tool out there, we are looking forward to work together. And so for the Chile work, it's a dual stochastic program that looking at how they can really look at the resources and provide solving the congestion. It's a market studies, but also it's a long-term resource adequacy studies. And then we also work with them on power flow studies as well, because after you know where's the congestion are, then you need to work on where the upgrade should go to reduce those congestions.
So next up, we have solving mathematical programs with embedded surrogate models using GAMSPy by Adam Christensen from GAMS Development Corporation.
Alrighty, thank you, everybody. Just gonna wait for the slides to pull up here. So while we're waiting, I thought I would just ask the audience quick, is anybody a GAMS user? This always helps me. Got 1, 2, that's it, 3. Is anybody a GAMSPy user? Yeah, okay, so 2, 3, all right, nice. So it's a little bit more than I expected actually, because GAMSPy is a little bit new for us. I think it was last year at this conference, we announced that we were going to be doing some licensing changes and pushing GAMSPy out into the academic world a little bit more than we had in the past. So I appreciate the new users. So does anybody collaborate with an academic partner that might use GAMS? Just out of curiosity too, because I'll have a licensing slide here in a second, but there could be something that would be of interest to you guys. So no, okay. Well, anyway, hopefully I can convince you guys to give it a shot a little bit later. So, okay, onto the talk. So the slides are up. My name's Adam Christensen. I'm senior technical staff at GAMS. I'm based here in Fairfax County. If anybody's local and using GAMS, we love having visitors in the office. So just putting that out there. Next slide, please. All right. I had a colleague recently attend a conference, and a person came up to the booth and said, like, oh my gosh, you're from GAMS? It's like seeing a unicorn. I've never met anybody from GAMS before. And this slide is to say that we are actual people. We are attending conferences. We love to interact with everybody. It was kind of surprising that they were so fascinated to see somebody. But the first 3 folks, myself, Steve, and Otharv, were the US technical team, I guess. We've got a lot of folks in Germany, as well as Sweden, UK. We're not fully remote. We do have physical offices, but the work here that I'm going to be talking about today is definitely driven by Barak and Mohammed at the end there. So kudos to them. All right, next slide, please. All right, so quick outline. We're going to talk a little bit about GAMSPy just because it is kind of new. It's always something we have to talk about, and my sales team says that I should be talking about it. So talk a little about motivation and our formulations, because this talk is all about merging optimization tools and ML tools into one framework. So a little bit of the universe of possible AI topics that's at this conference is very, very large. We're kind of focusing on a narrow subset of applications of ML and optimization together. So, all right, formulations, talk a little bit about it. There's some math in here. I'm going to throw some code at you. I'm sorry if my font is a little too tiny at the end here, but please reference the slides at the end online if you need some references, or just contact me. All right, next slide, please. All right, this is the big reveal that I think was last year, but maybe is now this year, because I went back to our LinkedIn page and it said we had announced this about 10 months ago. So we have free academic licenses. So if you are partnering with a university or anybody with a .edu domain, you can go get an academic license for free, totally unrestricted model size. And there's a couple like node limits. So 2 node limits without an internet connection. You can have network nodes as well. So something like Google Colab or other kind of online systems that you can collaborate and do code development. We have the big news here is at the bottom here, full access to CPlex, full access to Express Global, full access to COPT, full access to Mosaic. And then if you go to Gurobi's website, you can go get an academic license through them. We provide you with the Gurobi link to GAMS, so you can go use Gurobi as well. So these are truly commercial scale solvers, best in class, all available for free through the use of GAMSPy for academic users. So it says valid for 12 months, but yep, completely renewable every year. You just go onto our portal and renew. All right, next slide, please. All right, so the motivation for GAMSPy is that Python is completely ubiquitous. Every conference I've been to, it's always about Python. There's a huge variety of third-party packages, especially for ML. And then next slide, please. We always had this, we've always had Python APIs and APIs to GAMS through other languages, but the external communication to GAMS has always been a friction point for us. We wanted to merge Python and GAMS into one system where you can truly do algebraic modeling in Python without leaving that process and going to GAMS and then coming back to Python and doing all sorts of data handling on the back end. So we're now doing that for you. All right, next slide, please. All right, so the new opportunities here with GAMSPy is that we can start to do things that are a little bit more integrative in a larger sense than just what we were born as an algebraic modeling language. We can kind of bring in tools from PyTorch, scikit-learn, all these other tools that are ubiquitous in the ML community. Maybe we can take those formulations or those models that have been trained in those languages or those packages, I guess. We can formulate models in GAMSPy, and then GAMSPy would do the handoff to these nice solvers that you've got. So this is kind of the flow that we envision. You can use GAMSPy to do the training too, but I think it might be more regular to find a trained model with PyTorch or something like that going to GAMSPy and then through to the solve side. So, but because Python is the ML language, this is what we're focusing in on. All right, next slide, please. All right, my first GAMSPy, it's like my first Sony when I was a kid. So this is exactly what the syntax is like. It feels a lot like classic GAMS. Down at the bottom there, I'm not going to go through the details, but the supply and demand equations at the bottom, that's the new stuff for us. So Python's great because you can overload just about everything, and you can make all these logical operators like less than or greater than operations. You can make them aware of GAMSPy symbol objects and then have that be the algebraic formulation that then gets handed off to GAMS in the back end. So it's kind of architecturally like NumPy or Pandas, where you've got a kind of compiled extension in the back end to do the heavy lifting. Python just does the handoff of the syntax. All right, next slide, please. Model objects get created off of what we call a container. So the container contains all of the equations, all the variables, all the parameters and data, other set data. Having everything in a container means that everything is aware of everything else. And so you can do GAMS-like things where you find domain violations, problems with your data. You can even do some data manipulations in kind of a powerful and very GAMS-like way, I guess. So model objects live outside the container. You can see that we just are passing all the equations. So equations m dot get equations, just passes all those equation objects in. You can even pass the objective straight into the model object as well. Yeah, next slide, please. All right. Also, kind of like GAMS, although GAMS Classic, we're started calling it GAMS Classic, has a two-pass system, so we're compiling and executing. You might see compilation errors fairly early on, but you actually have to do something. If you're in an interactive environment, you have to actually do the compilation. If you are in an interactive environment using Python, which a lot of people are doing, you're going to get early errors here that some sort of logical inconsistency has popped up in your model. So that's an example here where we've got a validation error that's popping up. So early errors, and next slide, please. Yeah, so the GAMS philosophy here is that early errors, tight syntax leads to better modeling is just our kind of core belief. So domain violations are something that is core to GAMS. If you're getting those, then that means that you've got a data issue, and so you need to work on resolving that. So next slide, please. All right, some of the new stuff that's coming out in GAMSPy is that GAMS is a sparse data system where we've got labels that are kind of manipulating data. We need to now kind of work in a world of dense data structures where not necessarily everything has a label or a kind of logical meaning to it. We just have sizes and shapes. So this is an example of how to input new data structures, dense data structures, in kind of a GAMS-like way, hopefully smoothing out some of those bumps along the way. So the dim operation just means you're putting in a dense data structure with a certain size, and all it's got is an index, basically, as the label. And that way GAMS understands that dense data structure as essentially a converted into a sparse data structure. And again, we've done more syntax overloading with the matmult, so matrix multiplication. We can start doing things that's a little bit more machine learning like instead of classic AML modeling. All right, next slide, please. All right, so if you look in the literature, you'll see a lot of folks that just say that ML in math programming is tedious and error prone, and this is like gold for us. So we want to be able to take that tedious and error prone step out of the equation and get all you guys that are doing these great models into a pipeline that is easy to maintain, easy to test, all sorts of other things, basically fully automated in a nice way. So we want to be able to offer that to our customers. And so there's no so when we're doing this ML in GAMSPy, we are not looking at any singular right answer here. We want to make sure that it's flexible, and we expect that all of this will evolve over time. And if there's anybody that's interested in a particular formulation that I don't mention on here, please contact me afterwards, and we're likely to, I don't know, give you the best support imaginable, I guess. So, all right, we must stay flexible. That's, I guess, our core belief here. All right, next slide, please. All right, so some of these formulations, and this formulation term is something that you're going to see again because we use it in GAMSPy as actually part of our package syntax. So it's just the idea that there are going to be some mathematical constructs in ML and math programming that are very, very common, and that it's very cumbersome to kind of keep adding these things over and over again into a math program. So we want to make sure that the automation part is we're at a high level of automation so people can kind of swap these structures in and out. And next slide, please. So just to start off with some very basic activation formulations that we've got inside of GAMSPy already. I mean, these are very common in ML layer, neural nets, especially. So ReLU, hyperbolic tangent, softmax, these are kind of the common activation formulations that we've got. There's the ReLU, which is just max, the max function here. If you go to the next slide, you could see what these things turn into if you put them into a math program. So ReLU is can be formulated in a number of different ways. You can have kind of a big M formulation or a big sigma formulation. You've got some binary variables that are in here now. You can also formulate this as a complementarity condition, where you now have maybe an MPEC that then might get translated or transformed into a nonlinear program for ultimate solving later on. So this is an example of the flexibility. We want to make sure that users have options of different ways to formulate ReLU or other functions. All right, next slide, please. Okay, so now we're going to get into some of the syntax of GAMSPy plus ML. So there's going to be more on our documentation page. We've only got 20 minutes today, so I don't have any live demos, but please talk to me afterwards if you want to kind of sit down and talk. I've got my computer with, so basically what we've got is a series of, if you wanted to do a ReLU formulation with a binary variable, not the complementarity condition, we've got these activation functions, and they have generators in them. So helper functions basically that create all of the variables and the equations inside of the GAMSPy container for you based on some of the input variables, so that you want to maybe get from the last layer or something. So you can see what I'm doing here with the ReLU with binary variable function here is that I'm passing in a variable that maybe came from, this is all just fake, just to illustrate the point here, but maybe it was the last layer variable, passing it in, and then after that, I get handles to my variables of interest at output, and maybe the formulation variables actually, the YB and the equations are actually the reformulation of ReLU in a math programming context. So the container was previously just populated with I and X, now has a number of other things. You don't have to worry about the naming. We go through and do all the naming for you. Okay, next slide, please. Behind the scenes, this is exactly what's happening. This is the GAMSPy syntax. We've got a couple of equations. Bounds are also there. Next slide, please. All right.
5-minute warning.
Yep, thanks. Okay, this is a picture of our documentation page. If you're really curious about all the formulations, because that's sometimes devil is in the details, just click on the source. The formulations are available online. All right, next slide, please. All right, we've also got layer formulations as well. So activation functions combined with layers will create a neural net at some point. Linear layers, I think, is basically the only thing I'm going to touch on today because of time. Same idea. We've got a gp.formulation, so that keyword here is that we want to port in a linear layer formulation into our model to use in an optimization sense. So, all right, next slide, please. And these formulations get called, and they populate the container with new symbol objects that GAMSPy understands as part of as the equivalent formulation of the ML object. All right, next slide, please. And we see that even the layers, we get kind of the same idea. We're populating the container with new objects that represent these linear layers in this case. All right, next slide. All right, so quick other thoughts. Can you train ML models in GAMS? Yes, you can. Maybe it's a specialized application. I mean, the simplest forms of ML models are something like ordinary least squares or something like this, but maybe you want to add in a specialized constraint. You could do that pretty easily with GAMS. So non-neural net models, because basically I've only been talking about neural nets at this point. We are currently supporting regression trees, and we're always expanding. So if you've got a specific interest in something, we're happy to take a look at it. All right, next slide, please. All right, I'm going to blow through this real fast. This was a quick example of a reformer process. So the idea that GAMS has kind of taken the idea of a surrogate model or something that's proxy model and tried to embed it into an optimization model. In this case, I've got a proxy model for a reformer. All right, next slide, please. It's just a complex engineering system. Doesn't actually have to be an engineering system, but it's a complex system. In this case, it is an engineering system. All right, next slide. We want to maximize hydrogen production with some special constraints on nitrogen concentration in this system. All right, next slide. Right, we don't have a first principles model of this, but we've got a ton of data because I'm a plant manager and I've collected a lot of data, but I don't have a PDE model or something like that. All right, next slide, please. All right, so this is an example of what you would do with the training a neural net with PyTorch. So this is the syntax. If you've got a bunch of different layers, some linear layers, some ReLU activation functions in between, this is what PyTorch is. This is not GAMSPy. All right, it's a lot of experimentation that goes into this and a lot of stuff that I am not an expert on how to verify and say that this is a very well-trained neural net. But fair enough to say that this is a lot, there's a lot of development time in these types of things. All right, next slide. If you kind of keep that mental model of the last slide in your head, our formulations mirror this very similarly. So if you wanted to bring in that neural net, we communicate this through NumPy arrays. And so we have to add in each of the layers in particular and loading all the weights and everything like that. So we kind of bring in those data one by one. All right, next slide. And I think this might be the last. Extract the data, put it into an optimization model. So we're taking and actually formulating a model at this point because we're starting to add these formulations to the container. ReLU and linear layers are kind of being constructed down here at the bottom because we need to grab variables from the previous layer and put them into the next layer. So we kind of have this stair-stepped approach, which you see underneath the data normalization. All right, next slide. Maybe this is my last slide. Oh, sorry, that was a duplicate. My bad. One more, please. All right, now we've got an actual constraint that we're kind of interested in where we're constraining the amount of nitrogen in the output stream. We've got an objective here to maximize hydrogen production. And then at this point, we can just go to .solve. So in this case, it's reformulated as a MIP, mixed integer program, solving it with Cplex. All right, next slide. All right, that's it. I think I might be a little bit past my time, but yeah, like I said, we're always super. We're always looking for new formulations. We're always looking for new partnerships and interested parties in developing models. So yeah, look forward to any questions you have.
Awesome. Thanks for the talk. So I'm Luke Lavin. I work at the National Renewable Energy Laboratory, and it's really cool to hear more about GAMSPy. And my question is how you all think about rewriting existing large models that are in GAMS into GAMSPy. I know over the years we've had the Reads model and a few other models where there's a lot of legacy GAMS code, and we dump a lot of stuff to GDX files, and it's slower than we wish it was. How do you think about numerically what the efficiency gains might be from going to GAMSPy, and what have you all looked at there?
So the overhead for kind of doing modeling in GAMSPy is only slight. So like I said, the GAMSPy is structured architecturally where you're kind of just, GAMS runs as a server in the background, and we ping GAMS in an incremental basis to kind of suck in new data. So every single line that gets executed is kind of communicating with a running GAMS process in the background. So that's already kind of a savings because you don't have to start up a process, run it, shut it down, save a GDX file. It's already there. We've got a blog post that does some comparison of GAMS and GAMSPy, and it does scale. So you should expect there to be, Reads has some instances that, I've worked with Reads a little bit too, so they can have 500 million non-zeros, and that's a huge model. Yes. And you should expect that GAMSPy would be able to handle that as well. But as far as translating GAMS into GAMSPy, almost all the data structures that are in GAMS Classic are available in GAMSPy. There are a couple things that don't port over, like slightly more exotic, like looping in GAMS. You have to use Python for loops. And so the looping context is a little bit different. There's going to be some ways around it, but that'll feel a little bit different. Everything else is going to be almost one-to-one by design. So in our time off, we have played a bit with training models on GAMS Classic and GAMSPy, and then trying to like put in a new new model, see how well it does. And it doesn't do bad. You should expect some errors, but we have a model library of maybe 120, 130 models out there that have GAMS Classic and GAMSPy kind of side by side. So, so this is like kind of possible. But with Reed specifically, I know the structure a bit. I don't think it would be too bad. It would take a little bit of time, but I don't know, solid couple weeks.
Awesome. That's super helpful.
Yeah.
Thank you for your presentation. I'm Hafiz Bazrafshan from Habitat Energy. Curious whether for production systems like on Kubernetes or like on the cloud, whether we need like a server or can it be hosted locally? Like how does that work with GAMSPy?
So you can do this. So that does get into a little bit more of a licensing question, but you can absolutely run it in on the cloud. We offer our own system called GAMS Engine that is an AWS-based software as a service product. So if you don't want to do all of the management of the instances and user access to different models and all that stuff, it's a fully featured kind of ecosystem with REST API interaction. So you can do that as well, but you can, as long as you get kind of a network license, you can also kind of spin up your own cloud. If you've got servers on-prem or something like that, then you can do this yourself too. But it would just be a licensing thing. Does that answer your question?
Yeah. Thank you.
And as far as like the installation, like with GAMSPy, it's a pip installation process. So you don't have to go to our website and download a giant GAMS file anymore. It was totally modularized. So it's all on pip. So that makes it nice for kind of Docker containers and stuff like that. You don't have to go and do some big curl operation to get a 2 GB file. So. All right.
Do we have any more questions?
Okay. All right. Thank you.
All right. Next up, we have Alexandre Parisot from Linux Foundation Energy, presenting on building open source AI solutions and foundation models for market and planning efficiency.
Much. And thank you to the FERC team for organizing this great conference. So my name is Alexandre Parisot. So good morning, everybody. I have two goals today. It's just to try to tell you a little bit more about open source and how you can use it for especially application for AI and energy, and also to illustrate on behalf of one of our projects how this kind of thing can work in particular application. So here I'll be using a project around foundational models to speak about this. Let's see, can we get the slides up? Wonderful. So here on the foundational model part, I'm going to be speaking on behalf of the open source community that is running this project and represented here by the co-authors from Hydro-Québec and IBM. So next slide, please. So first, a little bit of an introduction on how to think about open source. Really, open source is a standard approach for collaborating on a digital technology. And the basic idea is you can work collaboratively on a shared foundation and then build things that are specific to you, or build some commercial applications on top of it. And basically make value, make strategic value on top of that shared foundation. The fact of having that shared foundation is not, you're not reinventing the wheel. You're doing things with your peers. You are benefiting from interoperability. And basically, when you look across the board, a lot of the technology we use today, including in some of the most well-known commercial products, are really leveraging a lot of these open source components. to just speed up adoption and just achieve interoperable solutions. So next slide, please. And so the Linux Foundation is really the home for some of these for some of these projects. The Linux Foundation doesn't do any software development itself. It really helps these communities to come together, and then handles, it's a neutral place for them, and then it handles all sort of services that makes this project successful in terms of the governance, legal, IP, security, all these kind of things that make it something that you can trust and really build industrial solutions on top of it. And so you can see some of the examples of the technology that the Linux Foundation hosts. And the next slide, please. And so Linux Foundation Energy is just basically doing exactly that same process, but for energy-specific applications. And so this is something that has been started a couple of years ago, and it is that has been growing into a portfolio now of more than 30 open source, freely available projects that you can use, that you can contribute to. So some examples, I'll be talking about some examples around AI, but I want to flag, for example, Trolley, which is an implementation of FERC Order 881, that has been started by Mazo Energy and has been getting a lot of traction, or Possible, which is a set of building block for power system modeling that's going to be showcased tomorrow by the Artelis team. And so what you can see is basically this: behind those projects, there is a lot of industry leaders that are just contributing to this and building operational solutions. So really, all of these projects are meant to be used for your actual industrial process, for your critical processes, and so there's a lot of emphasis put on making those solutions efficient, reliable, secure, and everything. Next slide, please. And so I'll be focusing a little bit more on LF Energy AI projects, so kind of the thing that we're doing. So OpenSynth is an ecosystem for the creation, dissemination, and evaluation of privacy-preserving synthetic grid data, and there's going to be a presentation on this in this room right after the break. A CDS is a set of specification for energy-related data with secure, standardized ISAC access and sharing. That's really meant to also enable AI applications using this data. Grid2Op is a framework to train essentially AI agents that you can use in your control room. So you can think about it as operator assistance. And so this framework brings you a lot of the things that you can use to actually do that. OpenStaff is a machine learning stack to forecast the load. So it's short-term load forecasting. It's been used, started by the Dutch DSO Alexandre and being used in their actual operation, and again getting a lot of traction beyond that. And then lastly, GridFM, which I'm going to be focusing on, which is really an open source framework to enable AI foundation model for power grids. So next slide, please. So if we go now a little bit more on this idea of foundation models. You can think about foundation models as just an evolution of AI. AI has been around for more than 50, 60 years, gone through different parts. So from expert system, machine learning. Now we're talking a lot about deep learning, and you can see that basically in the different sequence, if you look at model side features, learning, data, adaptability, there's been evolution. And the foundational model, really what they're meant to be very large model. They're meant to be trained on a lot of unlabeled data and some amount of labeled data. This is self-supervised. This is, of course, using learning. And the basic idea is you do a lot of learning effort across the board with a lot of of data, but you get a model that can be used for many, many applications, hence the term foundational. Next slide, please. And so when you look at this also from an historical point of view, a lot of this idea around foundational models and Gen AI started with doing language, and basically what you can do is essentially in that case is guess what's going to be the next word. So, and this is essentially what those LLMs that you've all been using do. You can do the same technique also with vision, so image recognitions, and you can use that for geographic information systems. And so again, with a lot of applications that we use regularly. Most recently, they've been working on across the board on using foundational model for climate. And what they found in this is actually a really interesting compared to all of this thing is just basically if you train a climate model on a lot of climate data, you can actually achieve similar performance as when you're using physics-based model, which might seem a little bit surprising, but actually it turns out that's the case. But it relies really on really training on a lot of different data and using some of these techniques that I've said. And based on all of this success, you'll say, well, it's very natural to say, hey, can we attempt to try that? Can we replicate a little bit of that for electrical networks, where we have a very diverse set of phenomena. We have very complicated systems. We have a lot of data, actually, and so can we try and do the same thing? So next slide, please. And so here the idea is, so you essentially train the model on every data set that you can get your hands on. You train a very large model that is general purpose one, and then you can fine tune it either on your specific data or things that are relevant for a specific applications. And the different application can range from doing load flow, forecasting, dynamic stability, system security, cyber security, control operation, expansion planning, electricity markets. Really, the idea is you have the ability within a single framework to apply the learning from the data to very, very different use cases. And the basics of this is really just applying some of the things that you've seen before from the large language models, from the image recognitions, and from the climate model. Basically, you're using some techniques based on encoder decoder, and you're using graph representations and with parameter masking. So what you do to learn to train the model is you're going to mask some of the parameters and ask the model, train the model to guess what are the missing parameters, and then from this it's going to learn some features representation, is going to gain knowledge on this and being able to apply it to a variety of use cases. So next slide, please. And so depending on the way you actually then do either that training, or you do the fine tuning, or you do the inference, you can do a lot of different things based on the fact that you're using a graph representation. So you can do contingency analysis. So essentially you are adding or removing some part of the graph, and so masking some of this, and then trying to get to the model to guess what will be the actual situation, predict from when it's learned. You can do some state estimation, so in which basically you sort of like to put either you have noise, or you actually put it. You do some things like you can do some things like virtual sensors, disaggregation on load, or you can look also at temporal phenomena, so holistic forecasting from load forecasting, unit commitment, electricity markets. So you get a lot of different applications from a very general framework. And here, basically, the promise is you get the significant speed up from a classical method, just as in not less, not more than any other AI ML tools, but you have this modular, versatile, and integrative framework that basically allows to make a lot of the connection and ask a lot of different questions from the same model or the same set of models. Next slide, please. And one of the cool things also is that because it's very foundational, it's very integrative, you can very much pair those models with other foundational models. So either ones that are based on a large language model, so understanding text, so anything in that can be correlated. You can work on weather foundational models that I've talked about, looking at, for example, if there is a extreme weather event, what's going to be the impact on the grid? Well, you don't have to do anything specific. Basically, you get within the same framework. It's very easy to couple these different models and to look, for example, at when the storms eat a part of your grid, what's going to be the impact? Well, the foundational model is going to have some insights on that. And then you can also look at a time series. There's a lot of applications, around the forecasting and the multivariate time series estimation. Is very easy also to couple this kind of thing with the grid foundational model. And all of this with this framework is really very well situated to tackle some of the issues that we've been talking in this conference in terms of interconnection planning, congestion management, and things like that. So next slide, please. And a lot of this really relies on the kind of data that you can input in the system. And here basically the idea is to look at data either from a static point of view, so you can get grid topologies, so you can get load data, you can get injections and perturbator from a variety of sources. We're going to be leveraging the OpenSynth project that is going to be presented after the break. We're going to be also leveraging synthetic networks or even real networks when this data is actually available. And the idea is to go from a static representation to a more dynamic representation where you have the time series, and you can even go into electromechanical dynamics. So as an extension, again, within the same framework. So next slide, please. And so now, okay, how do we make this happen? Because it seems like at least something that is really worth investigating. Well, there is no way a single stakeholder can actually achieve any of a project of this size. It requires a collaboration between tech companies, academia, between utilities and system operators, between national labs and things like that. So basically, this is why we decided with that community to set this up as an open source project, where you can essentially have everybody collaborating on the same sandbox, and with ideas of you're going at it at a very progressive and modular fashion, but also having different ways to handle the openness of the model and the data. So you can, for example, have an open source, open weight grid FM that anybody can use and contribute to and make changes. But also, if you want to use now that thing on more of your data behind the firewall sensitive data, you can definitely take that model and fine tune it on a specific data for further testing. You can also have apply some of the federated learning approaches to train the model between several operators and essentially exchange information on the different models. And all of the open source licenses allow you to do that. You can also take all of this framework and build either your own operational model on premise, or you can embed it in your commercial product and sell either products, other product or services based on that. And all of this is enabled by applying the right approach to open source to this context, and really enable both the collaboration with a variety of actors and the idea of being able to use it either for your own purposes or for a commercial product or services. So next slide, please. And so where are we with this? So last week, so a first version of some of these modules was released on GitHub. So there is actually something that's out there. Right now, it's we have two models. One model is a data kit that allows you to take some of the existing data sets that you have out there and generate that data that you can use for training of such foundational models. So you can use either very small IEEE networks. You can use very large scale networks with thousands of buses, because you have to think about scale right away, and you can prepare the data for the different features that you want in these masking techniques that I've showed by for example generating different contingencies and getting input data with this. And the graph kit is the other module that uses what you generate from the data kit, where you can try and fine tune and interact with that foundational model. So so if you want to have a look at it, all these two modules, which are really fresh out the box, that their first version are on GitHub. So I invite you to have a look at this, look at documentation, and give it a try. And you know, this is the beginning of the story. So next slide, please. And so basically, all this is really the first step of probably multi-year roadmap. So in the way the community has been thinking about where it wants to go, the idea right now is they're focusing on trying to capture a load flow dynamic as a first building block, and then expanding it on other different applications and going to more transient phenomena. Next slide, please. And so, as in terms of your collaborative efforts, so this community was formed about over a year ago. Started with a set of workshop. Published a vision paper that you can find on Joule that essentially highlights this vision. So decided that open source was the right way to actually scale up this thing, and released a first version that you've seen in a set of conferences. And basically, all this thing was punctuated with different workshops where you can see a lot of different contributors and actors joining in. And so, next slide, please. Yes. Next slide, please. Yeah. Sorry, one before. Yeah, very good. So the next one of this event is going to take place in Aachen, in Germany. So it's going to be in early September this year. It's going to be coupled on the same week with the broader LF Energy Summit in Europe, again in Aachen. So feel free, if you're interested, either by Grid FM, of some of the other initiatives and projects that I've shown. Feel free to have a look at these events. And more specifically for the Grid FM community, they have monthly community meetings, and they have a technology subgroup where they're looking more about the more technological aspects of and challenges of building such a foundational model. And so you're very welcome to join this event. You're very welcome to join this community meeting. Everything is open in the spirit of open source. And so if that's of interest for you, either go to the GitHub, try it out, come to these meetings. So the community meetings are virtual, or get a chance to go to Germany to meet this community in person. And so with this, thank you very much. You'll find on the presentation some links for the community and my contact info if you have any further questions. And I'd be happy to hear those who are in the room and remote. Thank you very much.
Any questions?
Thank you. Thank you, Alexandre, for the presentation. Josep Fanals from Mirrors Analytics. I wanted to ask you about the electromagnetic transient part that you mentioned, because I'm aware there are not that many open source packages that can tackle that. So what's your roadmap in this direction?
So on this, there is actually an open source project that is essentially doing modeling of those electromagnetic transfer. It's a project that's called DINAWO, and that is essentially built upon what RTE, the TSO of France, is using for its all operational studies. And so it's a fully open source package. It's still under development right now. I think that they have a fully working package for voltage stability, and they're expanding on the load flow and the more electromagnetic transient. But there is actually a package on this, and so I think the idea for the Grid FM is it's a little bit further down the road. I think they want to get the load flow right first, and then progressively going into a more transient phenomena and leveraging this DINAWO framework that essentially captures that as an open source project. So feel free to have a look at this DINAWO package. Because it does exactly what you're describing.
And while we're moving to the next question, I'll just remind the virtual audience to try and use the Q&A feature. We do have a virtual question next, but first, please.
Great, thank you. Audun Bottrud, MIT and Argonne. So thank you so much. Interesting presentation. My question is, so I get the impression you're trying to develop a general purpose tool that can address a range of different applications, but at the same time, we have highly specialized tools for those individual applications. So, is the expectation that this general purpose tool would be able to do a better job than those, specialized tools?
There's a lot of debate, even within the Grid FM, a community on what you can really expect. Is it going to do better than the simulation and optimization tools that we've been using for decades? What I can say about this is when you look at what's been happening with the climate models, it's actually very surprising that you can get an AI model to really perform just so well. So how much of that is going to transpose to power system? It's very hard to say, but what I can think, even if you don't replace your other models, they can really be used in conjunction with them. And I think that's why it's worth pursuing anyway, because you can find ways to use these foundational models or more specialized AI model for that purpose to work in conjunction with simulation and optimization to essentially speed up or address some things like scale that this optimization and a simulation model we know are a little bit having difficulty with. And so we'll see whether what's the actual performance, but at the very least it can be used as conjunction with those models. So I think that's the way. That's an open question. I don't have the answer for your question, but that's really something that the community is putting a lot of attention on.
We have an online question. Lee, will you unmute?
Okay, yes, thank you. My question concerns your use of ML. I'm wondering, I'm an agent-based modeler, and I'm very interested in modeling electric power grids, which have participants who are private and motivated by private profit-seeking goals and so forth. So my question is this: does your grid FM permit humans in a loop to be modeled who are actually strategic decision makers entering into the system, actively trying to gain profits and advantages and so forth, and trying to hide their true intentions, their next intended actions, for example, from other external view? And so that's why I use agent-based modeling, which allows encapsulation. Does your grid FM allow encapsulated action like that? Thank you.
Not at the moment. Thank you. Thank you for the questions. It's very relevant. At the moment, no, I haven't seen that discussed within the community as part of discussions we have attended or its roadmap. But yeah, I think that's something that would be interesting to look at, how you can embed some of these agent-based approaches into such a foundational model. So if you're interested, we can talk a little bit more offline on this and how that in action. I'll be very happy to connect you to the community members to explore that in more detail.
No further online questions. Any more questions from the audience? All right. Well, let's thank our speaker. Thank you.
Thank you.
All right. Thank you all for joining us. We are starting another shorter session this time, as we'll be switching to our panel on AI in 1 hour. But this is session W2A. I'm Daniel Wagner with the Policy Office, and starting us off is Gus Chadney with Octopus Energy, presenting on generative AI software for high-fidelity household load profiles, innovations in resource adequacy modeling, and planning efficiency. Gus, the floor is yours.
Hey, hi everyone. Yeah, I'm Gus, flown over from the UK. Got some slides, I think. Yeah, here we go. Cool. So I'm going to be talking about mainly synthetic smart meter data. That this title alludes to that. But so yeah, we're using generative AI to generate synthetic smart meter data for household load profiles. So next slide, please. So who are we? So I'm from Centre for Net Zero. We're a research institute which is part of Octopus Energy Group. So Octopus Energy is the biggest UK energy retailer, and well, it started as that, and now it has lots of different kind of areas in generation, technology, flexibility. They created Centre for Net Zero in 2020 to kind of basically leverage Octopus Energy's retail data, huge amounts of retail data. So while we kind of operate autonomously, so we set our own research agenda, and are really interested in modeling the future energy system and understanding the future energy system. We also have access to Octopus's vast customer data, and that's where we get most of our insight and modeling. So next slide, please. So yeah, a bit of context. This is obviously not new to anyone here, but the energy system's changed lots. Household demand has changed massively due to inclusion of renewables into the system and distributed energy resources, and also all of the kind of low carbon tech, which is changing how households use energy. Next slide, please. And yeah, we need better data. So smart meter data, household consumption data, we think is crucial to understanding the energy transition and being able to model kind of like what's going to happen. But especially in the UK and pretty much everywhere, the energy modeling is really dependent on either kind of old static demand data or highly aggregated data to get around kind of privacy issues. So demand data is really limited by privacy protections in Europe and the US. You can't just get out for free. And that was one of the things we found as this early organization. We got huge amounts of requests for access to Octopus's smart meter data for research. And we were really thinking of ways that we could release this data, get it into the hands of more important people by also, yeah, not kind of not being limited by the customer privacy protections. So next slide, please. So our solution to this was to look into synthetic data. So at the time, synthetic data was really well established in tech, finance, and healthcare. So it was really mature, the generation and use of synthetic data in these industries. A few big organizations listed there, which were in this space and generating lots of amounts of data and making it open and for use for other organizations and researchers. So we started looking into how we could generate synthetic data in energy, specifically in demand. And next slide, please. And yeah, and why the benefits of synthetic data are that we can release and look at demand data at the household level, so that the lowest level of the grid, and really add to kind of bottom-up modeling efforts where we can model lots of households and then aggregate up to various levels of the grid and really understand how demand changes throughout that hierarchy. We built a little kind of demo here which shows how we can kind of model real versions of the grid using bottom-up household demand data and kind of show how it changes over time. Next slide, please. So yeah, we created Faraday. So the Faraday is the algorithm that uses generative AI to create granular smart meter data securely. So we generate daily kind of half-hour load profile. So 30 minutes is the kind of the granularity of demand data in the UK for the most part. And this data is purely like synthetic, so it can't be traced back to individual customers. So it kind of respects the privacy and GDPR requirements, which is the privacy regulation in Europe. And we trained it on 1.8 billion rows of real smart meter data from Octopus's customer base. Next slide, please. So how it works, it's a variational autoencoder plus Gaussian mixture model. So the encoder maps data into the latent space, and then we train a model onto that latent space to learn the distribution of the smart meter data, and then draw random samples out of that space and decode them with the decoder. And the benefit of doing this is we can sample from the model kind of ad hoc, so we can generate samples in real time, which are all kind of each of them unique and synthetic, and we can generate as many as we want for the purposes that we have. So we don't just kind of feed the model with smart meter data. We also feed it with some other characteristics, mainly of the households of the customer and some kind of customer adjacent data, which is not too private. So we can generate samples for different types of households, different types of insulation of the household, whether the households have various low carbon technologies like heat pumps and solar panels and that kind of thing, and also what tariff the type of tariff the household is, whether it's a smart tariff, automated tariff, that kind of thing. And what that means is that we can then generate synthetic household demand profiles for like any amount of household characteristics and build up not just a kind of a population of households that exists in certain regions of the grid, but also that might exist in the future. So we can create scenarios of populations based on kind of projections of low carbon technology ownership in the future and understand what the demand will be for that population. Next slide, please. So yeah, one of the main hurdles that we found with people using this data is that, yeah, it's not that in use in the energy industry, and people have some concerns about it, whether it truly protects privacy or if it's even useful enough or reflects the underlying data. So we worked with a number of other research institutes in the UK and the US to come up to develop a paper that explored these attributes of the data, and it focused on three main areas: so fidelity, how well the distribution of the synthetic data matches the distribution of the real data set statistically, its utility, how useful the data is, how easily we can use it in place of real smart meter data for kind of various tasks like forecasting or classification, and how private it is. What's the likelihood of private data leakage by developing our own privacy attacks and measuring the data we've created. And this paper really kind of explored how these three metrics interacted with each other. So how the more private the synthetic data got, how that affected the fidelity and utility of the data as well. So that's out there if you want to read it. And it's the goal of it was to kind of get some confidence in the smart meter data that it could be useful. Next slide, please. And then the next step with this was the creation of OpenSynth. So we worked with LF Energy, which is Alex's organization just presented, to develop an open source community for this synthetic energy data. Our goal here was, so we had access to Octopus Energy's smart meter data, but there's lots of other holders of smart meter data around the world. And we wanted to share our algorithms with those organizations so that they can generate their own synthetic energy data and then ideally share it back to the community as well so that other researchers and institutions can use that data. We've contributed the synthetic demand data that we've created to the community, so that's available to download now, and the algorithms also available as well. And the idea is we are trying to build up a community of people, users and creators of this data, and to add to the models. So different models will be useful for different use cases. So we want to have people to be able to choose for the most appropriate one, and then also a data repository where people could go and download synthetic data sets for their own use cases. Next slide, please. And yeah, we think there's a massive variety of applications for this data. So not just in electricity system and network modeling, but we've spoken to people in kind of buildings and housing development planning, where it's useful for them to understand the houses they'll build and the demands and their demands. Financial products and services for lending and regulatory compliance, and also consumer products, the different tariffs, time of use tariffs, automated tariffs, and how they will interact with the actual demand that the households generate. Next slide, please. And then, yeah, in terms of the systems side of the thing, whilst this data is, usually a bit more medium to long-term strategic, there's also other use cases for different kind of temporal granularities. So for near real-time control, using it to help with state estimation models, tactical short-term modeling, and then innovation of new products and services, and incorporating it with other initiatives like Grid FM, which Alex spoke about. Next slide, please. So in terms of how it's been used so far, so early models, we worked with a university in the UK, the University of Birmingham, who had access to kind of local hyperlocal demand data to kind of validate our data against their real data. And the data we produced really closely matched what they were seeing when they built up the right population of households and generated smart meter data. So the timing and magnitude of the peaks aligned really well. Early versions, we did notice there was a slight bias with our smart meter data and their data, and we were able to kind of isolate the reasons of this bias and correct for it in future versions, which was quite successful. Next slide, please. And then, yeah, as we've grown OpenSynth, we've kind of got partnerships with other organizations and system operators, not just in the UK. So Leander in the Netherlands, really interested in using this data. And they have, a massive part of the Netherlands kind of distribution network, but they had quite a few kind of data gaps in their grid measurements. And they are exploring how this generative synthetic data can reconstruct the gaps essentially, and help build up a more complete model of what they're seeing in the Netherlands. Next slide, please. And then, yeah, quite recently, the kind of early days of OpenSynth, we were mainly focused on synthetic smart meter data, but we've just recently started to think about expanding the scope to other kind of synthetic and even non-synthetic energy data, with the goal of making OpenSynth a more holistic kind of one-stop shop for energy data. And so we've recently been working with RTE, who are incorporating their recent release of data, which is kind of a map of the France grid down to kind of node breaker topology, along with time series demand data covering a whole year. And the way they've done this is to disaggregate demand data down through the grid topology. So a different way of generating kind of synthetic data. So yeah, again, there's a really good paper on this that they've released. And our idea here is, the method we've generated synthetic smart meter data is one way, but there's definitely other ways, and by having them all in kind of one place, we can see how they interact and combine the methods, and also have the kind of standardized place to have all the data.
Housekeeping note: you have 4 minutes.
Okay, next slide, please. I think I'm near the end. So what's next for Faraday? So Faraday V4 was the most recently released one. Faraday V5 is what we'll work on now, and the idea here is to introduce a kind of geographical location aware element to the data. We see variations in data across the UK, and we wanted to understand if we could add that locational element to the model. And then moving on from there, we're going to work more closely with system operators to map this demand data onto grid topology, validate it more, and then work with operators to see what the best use cases will be. Next slide, please. And for OpenSynth, we are carrying on working with other organizations to add more models to the project and add more data sets. And there's a few in the pipeline, some in North America, where organizations are trying to generate their own synthetic data. And yeah, the idea is these will all be contributed back to OpenSynth. Next slide. That's the final one. Yeah, so that's basically it. Yeah, looking for people to give us more use cases to implement applications of this data, developing and deploying more models, and using and contributing back the data. And that's it. So yeah, thank you for listening. I'm happy to take any questions.
All right, a big hand for Gus Chadney, please. All right. If you're in the room, please introduce yourself before asking a question. And if you are online, please put your questions in the online Q&A feature in Zoom.
Great, thanks for the great talk. I'm Luke Lavin, I'm at NREL, nice to meet you. My question is, it sounds like most of this data that's already there is available for European entities. My understanding, feel free to correct this, is that Octopus now has a retail business in ERCOT. Should we expect at some point data to become available about US electricity consumption, or are there barriers to that?
Absolutely. So yeah, Octopus, while the UK is by far the biggest, we have retail businesses in I think like 11 different countries now, with Texas being one of them. That's definitely our plan. We're quite a small team, and it's quite intensive building these models for us. But yeah, we're definitely looking to expand to other regions. One slight barrier is just having that critical mass of number of customers so that we have enough data to train on. But yeah, that's basically the only one, that and resourcing. But Texas is one we're definitely really interested in, just because of the uniqueness of the grid compared to some other regions.
Yeah, Alexandre Parisot from LF Energies. Just perhaps an additional comment on this is because it's an open source framework, actually the idea is also to convince other utilities or system operator to apply the framework. It's really ready to go. So just a matter of having this discussion going forward, and as to specific barriers, well, we'll have to address that with them. But definitely what Octopus did on their footprint through this open source framework can be replicated, and that's the intent of actually growing this community. Yep. So welcoming anybody that has some smart meter data and wants to generate synthetic data to make it more available.
Yeah, and just to add that to that, we've helped some organizations. So maybe they've provided the resource, we've helped them with the expertise to try and generate that data, and we're happy to continue to do that.
Do we have any questions online?
Hello, I'm Hafez Bazrafshan from Habitat Energy. Thank you for the talk. It was really impressive to see the synthetic data. I have a question. When you move from region to region, have you ever seen whether transfer learning can happen? So like parts of the model can be trained, I don't know, in France, and then parts of it, you can just take those coefficients and then update it for another country?
Yeah, absolutely. So in terms of the demand data, absolutely, because demand is relatively kind of straightforward data set, even though the temporal granularity may change from region to region. One of the challenges is to make it really useful is to add that social demographic and household data into the mix, which is different levels of access depending where you go. So that's one of the main challenges, but the model itself is flexible enough to handle different kind of attributes and characteristics. So yeah, people will definitely have their own kind of ways of conditioning the model, and it can accept that. But there's going to be a kind of trial and error approach to getting the most out of it in those regions.
Vishnu Vatrai from Orchid. Very quick question. I think when we talk about the data, it's always a question of synthetic versus the real, right? I just wanted to get a sense of what's your thought in terms of the how much of the data you really need to be in the real data versus how much you can rely on the synthetic data, right? Of course, there is a probably you may not have the exact sharp number, but at least some like observation or some thought would be helpful.
Yeah, I think, to be honest, you can't replace real data. Like, if in a perfect world, we'd all have access to all of this, data in real time. And then there's various kind of tools and methods to actually deal with it in reality, of which this is just one piece of the puzzle. And it really depends on the use case. So obviously, in a lot of modeling, aggregated data is completely fine, because that's the level we're looking at it. And then some cases, if the kind of techniques are good enough, just obfuscating and making other techniques to make the real data privacy kind of aware is also good. But we think the synthetic data kind of is really strong because it gets around some, like quite a few of these issues we have with no access to or limited access to the real data.
Do we have any more questions in the room? Any more questions online? Gus, thank you very much.
Thank you.
All right. For our second and final presentation of this session, we have Farhan Hyder at the Rochester Institute of Technology presenting on machine learning enhanced formulation tightening of energy storage resource constraints in unit commitment. Farhan, the floor is yours. Please share your slides, and you're in the driver's seat.
All right, can you hear me?
Yes, we can hear you.
Okay. Okay. Well, you can see my screen as well, I think.
So far we just see a message about
Okay,
okay, now we see it.
now?
Yeah. Now it looks great.
Okay, thank you. All right. Good morning, everyone. My name is Farhan. I'm a PhD candidate at RIT. My talk is going to be on machine learning enhanced formulation tightening of energy storage resource constraints in the unit commitment problem. This is a brief outline. First, I'll be going over the motivation for this topic. After motivation, I would also look at explain what is formulation tightening, briefly go over existing work and remaining challenges, and introduce our novel ideas. After that, I go into a deep dive, first explaining the formulation we're using, and then the meat of the work, which is the machine learning enhanced formulation tightening, followed by results and conclusions. So the motivation. So we know that renewable energy is intermittent in nature. And we need something that is an effective, efficient storage system that can store excess energy and release it whenever it's required. And in the US, in the last few years, we have seen an exponential growth in integration of utility scale energy storage resources. Last year alone, there was a 66% increase in ESR capacity within the US. And most of these batteries that are being added are predominantly 4-hour chemical batteries. By 4-hour, we mean they can fully charge or fully discharge within 4 hours. And in the coming years, it's expected to increase further. So we will have to figure out a way to model the energy storage resources in the unit commitment problem. And the first challenge with that is it requires binary variables to prevent simultaneous charging and discharging of batteries. To model that behavior, we need binary variables. But this problem increases the computational complexity of the UC problem, which is already a very hard problem. And adding more binary variables only makes it harder. So what we need is a more efficient way of modeling the constraints. And by that, we mean developing tighter constraints. So what do we mean by tighter constraints? So let me discuss what is formulation tightening quickly. So consider a simple linear programming problem defined by these constraints. And the level curves will let you know that the LP optimum is the green dot, which is X star prime. And this is fairly easy to find out. Most algorithms today can easily find the LP optimum. But for MILP problems, the challenge becomes how to find the best integer solution. That is to go from X star prime to X star, which is in red. One way to do it, and a very common way to do it, is using branching and cutting algorithms, which are computationally expensive. Branching operations can take forever to get to a good integer solution. So our idea is, what if we could determine the convex hull of the problem? So a convex hull is just a smallest convex set of all feasible solutions, which are these blue dots. So if you could modify the constraints in such a way that instead of the blue lines, we get the red lines, which is the convex hull of the problem, we can solve an MILP problem using LP methods without any combinatorial difficulties. The process of transforming constraints is what we call formulation tightening, to delineate the convex hull of the problem. So some existing work on tight constraints for the UC. So there were a few papers that go over how to get tight ramp rate constraints or minimum downtime constraints for generators in a UC problem. And a recent paper goes over how to get tight SOC constraints for ESRs. However, most of these studies do not explain the process of developing tight constraints. They explain the tight constraint that's been developed, they define it, they examine it, but how do we get to tight constraints is not known. In our earlier work, we developed a systematic 4-step method to tighten any mixed binary linear program, like the unit commitment. Here we do constraint to vertex manipulation. In future slides, I'll explain this in greater detail. So we work with a numerical example, and we generate tight numerical constraints. So the last step to make it reusable is to express the numerical coefficients in terms of generator parameters. So they're general and they can be reused. And this approach was used to tighten generator formulations. And it showed significant computational improvement on the IEEE 118 bus system and the Polish 2383 bus system, which is a pretty big system. Given that this is the brief overview of the literature, we looked at what are the remaining challenges, especially with our previous technique. So constraint to vertex conversion requires numerical example. Numerical constraints cannot be done symbolically, which requires a significant amount of manual analysis for its parameterization, and which becomes particularly hard when you want to handle large number of ESR parameters. So there is a need for a computationally efficient and generalizable approach. That's the gap we identified. And our idea to handle it is the use of machine learning. So we want to develop a model that takes ESR parameters as inputs, numerical coefficients of the tight constraints as outputs, solve it for a perfect match, that is zero error, such a way that in the end, the weights of the ML model will reflect the mathematical relationship between input and output, that is the coefficients and parameters. Most of these relationships are typically linear and the weights are integer. So we are considering linear regression with integer weights, which is integer constrained least squares method. And a couple of slides, I'll go into greater detail and explain how this works. Before we get to that, I'm just going to briefly tell you what the ESR formulation we are using. And we assume that the ESR during charging mode purchases power from the grid at marginal price, so it's a negative charging cost. And in discharging mode, it has the option to sell it in the energy market or in the reserve market. So both are positive costs. We use a one-bin model, and these are the charging limits. Minimum charging limit is assumed to be 0, as it's common for most batteries nowadays. So state of charge constraints, state of SOC dynamics, and we have an initial and final SOC requirement as well. Start of the day and end of the day. So now it's a deep dive into how systematic formulation tightening works and where does machine learning come in. So let's consider a simple constraint, which is x1 plus x2 greater than or equal to 0.5, where x1 and x2 are both binary. It's this blue line. Now, the first step is to relax integrality requirement and convert constraints to vertices. When you do that, you get 5 vertices, 3 of which are binary and 2 are fractional vertices. Since x1 and x2 in our original problem can never take a value other than 0 or 1, we can drop fractional vertices without affecting the feasible space. So we drop that and we get 3 vertices, all of which are binary. The next step is to convert these new vertices to constraints. When you do that, you get a new constraint, which is a tight constraint, x1 plus x2 greater than or equal to 1. And when you draw the feasible, and it perfectly encapsulates the feasible region. It's the smallest convex set of feasible solutions, which is the convex hull. And this way, we just do some constraint to vertex manipulations, drop fractional vertices, and get to the convex hull. Now, the tight constraint now here contains a numerical value, which is 1. Now, what we want to do in the next step is parameterize it in terms of the problem parameters. For example, if a generator, it's the generator parameters. Based on this idea, we develop tight constraints for different categories of ESRs. ESRs that are slow to charge, ESRs that are faster to charge, so on. So now I'll explain where the machine learning part comes in. So we saw that parameterization of numbers is not easy. Here is a simple example so we can tell, but in general, it's hard to figure out where that particular number is coming after you tighten the constraints. So let's consider a simple numerical constraints for a battery. So it has the discharge variable and reserve and the binary variable Z. All of that added less than equal to 0. And Q is just a numerical coefficient. We want to express Q in terms of ESR parameters like SOC min or SOC max or PC min, PC max or PD max. So for that, we first consider n ESRs at a time. Each ESR has m parameters, typically 2 to 4 to 5, not too many. And ESRs we typically consider 20 to 100 ESRs. So how we do this is using linear regression. The problem is just shown here. So our aim is to minimize the error, where P is your n cross m parameter matrix for n ESRs with m parameters each. Q is a vector of coefficients, numerical coefficients. It's a vector of all Qs across several ESRs. So we take all the Qs and put them on the other side in Q. And W is the vector of model weights at this point. And vector W is constrained to be an integer. The error of this problem is typically 0. So numerical coefficients can be perfectly expressed as a linear combination of ESR parameters. Let me show you an example. We are working with this constraint as an example, and we want to express Q in terms of ESR parameters. Let's say Q is 370 in this case. So when Q is 370, and let's say these are the 4 ESR parameters we are considering, and these are the values for it. So the integer constrained linear regression solves the model, and since the weights have to be integer, it expresses input as a integer combination that equals the output. So what we want to do is express the Q as a combination of ESR parameters. And in this example, it is SOC max minus 2 times SOC min. That perfectly explains Q. Now that it is parameterized, we know exactly where those numbers come from, and this can be reused. Mathematically, for an n-dimensional problem, it looks like this. Here I've taken n and m both to be 4, and zero error as 0. So when you solve this, you get weights as 1 and minus 2 and 0, 0. So that gives us SOC max minus 2 SOC min. This is the fundamental idea of where we bring in machine learning. Instead of trying to do this manually through trial and error and figuring out which number might have come from which parameter, we have automated the process with the help of integer constraint least squares that gives us the exact mathematical relationship between input and output. Moving on, I'm going to explain you the automated process that we use to get to this final Titan constraint. I have a few simple steps. It is broadly divided into 2 stages. First, to generate tight constraints, and then to parameterize those tight constraints. So for generating constraints, we start with random ESR parameter values. We write the constraints for a 2-hour problem. We consider a 2 or 3-hour problem because for a large number of hours, the number of variables and number of constraints increases exponentially. So we start with the 2-hour problem, get the tight constraints, and then extend it to any number of time periods. So this example is a simple 2-hour problem with these parameters. So the next step is to convert constraints to vertices using a software called Porter. That gives us the vertices. So then we identify fractional values for binary variables, as this is an example. And then since these can never be part of the feasible set, we eliminate them. What we're left with is only binary values for binary variables. And then we convert vertices to constraints, and that gives us the tight constraints. So an example of it looks like this. We started with the standard formulation on the left, and we ended up with this Titan formulation on the right. And we now understand where these numbers are coming from because it's a simple example. We know that 12 is the only number that is new, and 12 can just be expressed as SOC max minus SOC min. For a simple example like this, it's easier to identify where these numbers are coming from and how to parameterize them. Larger problems for slower ESRs, it's a lot harder to do. But this is essentially the idea. Do the constraint to vertex manipulation, get the tight constraints, and express those tight constraints, the numbers in those tight constraints as a combination of ESR parameters. The next step is parameterization. We first extract all the information, factorize it, and use the ML-based parameterization process that we developed earlier. Model is solved for a perfect fit, so the weights represent the exact mathematical relationship between ESR parameters and coefficients. So this process takes care of, removes the need for manual analysis and gives us the exact parameterized constraints. Once we have those constraints, we go into constraint validation, where we first examine the physical meaning of every constraint to ensure that it makes sense, because the constraints originally as the standard constraints come from the physical system. Now that we have tightened it, it still needs to make sense. So this is an example for a 2-hour battery that takes 2 hours to fully charge or fully discharge. That's why it has 2 time indices, t-1 and t. So on first look, it's not easy to analyze.
5 minutes.
Okay. Not easy to understand this. But if you describe it in terms of several combination of binary variables, it makes sense very easily. For example, if it is charging across 2 time intervals, the PCH t-1 and PCH t together should be less than the capacity of the battery, which is SOC max minus SOC min. The final step is constraint generalization, where we extend it from a 2-hour problem to a problem that is general, constraint that is general and can be applied to any number of hours. So for testing, we use the IEEE 118 bus system, added 10 ESRs to it, and we introduced stress by reducing ramp rates and reducing transmission line capacities. All the tests were done using Cplex, and the stopping criteria is a 0.1% relative MIB gap. To evaluate performance, we did two different types of evaluation. One is a computational evaluation using number of ticks, which is a measure of deterministic time in Cplex, solving time and percentage reduction in solving time. And we evaluated the solution with the help of best bound, feasible cost, and relative MIB gap. First, we did Class A batteries. Class A batteries are which can fully charge and discharge within 1 hour. And these were some of the very simple constraints generated for Class A. We tested them, and these are the results. We compared it with the standard formulation in terms of ticks, solving time, reduction in solving time, bounds, cost, and gap. So we saw that in all cases, we maintain the solution quality. The gap is same, while reducing the solving time significantly. Like in a simple case, it was 60%, and in some stress cases, it was at least 35%. So the results seemed encouraging. We carried on and tested Class B batteries, which are a lot more complicated and harder to analyze. But when you analyze it in terms of combinations of binary variables, it becomes a lot easier. Then these are batteries that can fully charge or discharge within 1 to 2 hours. We noticed that some of these constraints are repeated from Class A because they're still applicable to Class B. The rest are unique. Some of them are here, some of them are in the appendix. So we tested Class B batteries that discharge in 1 to 2 hours. A no stress case and with stress, where we have reduced the ramp coefficients and transmission coefficients, reducing the capacity to the transmission lines. What interesting thing we notice here is for high stress cases, we had a greater time reduction. Time reduction increased from around 26% to 52%, while we keep the solution quality in check. The solution quality is maintained for all cases, and the time reduction is fairly effective. And all these values represent the average values over 10 different runs. So in conclusion, we made the following contributions, and the conclusions are we developed a novel machine learning-based approach to enhance a previous systematic formulation tightening approach. We developed a machine learning algorithm that takes ESR parameters as inputs, numerical coefficients as output to identify the relationship between them. Using this approach, we obtained tightened constraints for fast ESRs that can charge discharge in 1 hour or 1 to 2 hours. Performance evaluation showed that there's a significant reduction in solving time while maintaining solution quality. The approach is general and can be applied for tightening any complicated MBLP problem in power systems or any other area. Finally, some of the future extensions that we're currently working on is to extend it to slower batteries that take 2 to 3 hours, or even 3 to 4 hour batteries, Class C and Class D. And we are in the process of extending our testing to larger grids, like the Polish 2383 bus system. And we don't want to be for cases where the coefficients might be a nonlinear combination of ESR parameters, so the linear regression may not work. And for those cases, we are developing symbolic regression, which is a type of regression analysis that searches a space of mathematical expressions and finds the model that best fits that given data set. So it would look like this. So for example, if we have something like PCH max divided by a big expression, you cannot do it through linear regression, but symbolic regression can handle these sort of situations because it has all kinds of mathematical operations and ESR parameters as input, and can draw a tree structure that examines the number and the parameters that can define it and express it as a full expression, give it as a full expression. And that's my presentation, and this is the remaining constraints. Thank you very much.
All right. Thank you very much, Farhan. All right. A reminder, If you are asking a question in the room, please introduce yourself before asking it. And if you are online, please put your questions in the Q&A feature in Zoom. To start us off, do we have any questions from the room? Do we have any questions online? All right. Going once, going twice. Oh,
Thanks for this is Adam Christensen from GAMS. Appreciate the presentation, very interesting. I was just kind of curious, I might have missed it, but it's a multi-stage solve process, right? You solve the relaxed MIP, and then you do your convex hull calculations, and then do the bounds tightening and all that stuff. And I guess I'm curious a little bit about, are there any variables that are fixed in that step? Or in that process at all, because it looked like some of the objective functions might have been a little bit different. And a maybe follow-up question on the objective functions. Was there any, did you use that as a metric of solution quality? Were there any other metrics that you were kind of thinking about to kind of judge solution quality at the end? Thanks.
Okay. Firstly, I think I should make it clear that the whole tightening process is done before we do the final optimization. So it's a form of reformulating the problem. So what we do here is not even pre-processing, it is reformulating, modeling it differently. Secondly, what we do with solution quality is when we have the tightening constraints and we're comparing with standard constraints, we look at the final lower bound, best bounds, as well as the final feasible cost and measure the MIP gap for that. So that is towards the testing end. And as far as objective function is concerned, for the tightening process, objective function is not important. Objective function is something that is important when you are testing the work after you have reformulated the problem.
right. Do we have any more questions in the room? Do we have any questions online? Looks like no. All right. Going once, going twice, going 3 times. Farhan, thank you very much for your presentation.
All right. Hello, everyone, and welcome back from break. We will be starting off this session with a panel on AI integration in markets. And we have our esteemed panelists, Alexandre Parisot, Director of Ecosystem and AI Energy Systems at Linux Foundation Energy, Dr. Adam Christensen, Senior Technical Staff at GAMS Development Corporation, Andy Whitmere, Director of Resource Utilization at MISO, and Brian Fitzsimmons, Chief Executive Officer at Grid Unity. And our moderator for our panel will be Emma Nicholson from our very own FERC.
All right. Thank you very much, Monica, and to our esteemed panelists. This is going to be a different, more chatty, conversational panel, not presenting papers, but in fact, just asking questions and having a conversation about the use of AI in power systems. So thanks again for joining us. And I'd love to go down the line. I know we're coming at this from different perspectives, but as a general case, we wanted to get on staff, want to understand, in your view, what's the most promising use case or use cases for AI in the wholesale power markets and planning today? And also, what is, in your view, what is the biggest misconception about using AI in these applications? So please go ahead with Alexandre, and you can have your own mic. Thanks.
Okay, well, so, thank you very much for organizing and moderating this panel. So I'm not going to pick like most promising. I'm going to pick like a short term, middle term, and long term, and then we can expand a little bit on this. I think short term, basically, I think using AI for anything around automation, and especially for interconnection processes, and especially in the US, is very much something big. And I think there's a lot of potential for me. One misconception is, again, AI relies on data exchange, and so basically I think that one of the other things is if you want to take the most out of it, you will still need to make sure that the data goes from the right place to the right place and things like that. So middle term, I would mention operator assistance. So anything that would help our operator in the control room manage a system that is increasingly complicated to operate, and AI can do a lot of things in there. And the misconception here, I would say, is it's not only a technological challenge. So if you think of this as only a technical problem, you will face a problem because your operators are humans, they're in the loop, and you're going to have to make sure that the AI works well with them. And a long term, I would say, even if it can help like on a more short term, is everything around AI augmented optimization and simulation. So using AI in concert with simulation and optimization engine to improve their performance. And here, really, the idea is it's not a black and white situation. It's not all AI. It's not all optimization simulation. You have to find ways to make sure that they can work together. And there are many, many ways to explore to this. So here are my picks.
Yeah, I agree. I don't have a specific like long, medium, and short-term goals here, but giving the most sounds like I'm giving investment advice. So I'm not sure that I've got any investment advice, but the idea that well, and so GAMS, for anybody that doesn't know, is specifically a software company. We're not necessarily we help develop models in of energy systems and stuff like that. That's our bread and butter. Energy is a big customer of ours, energy of all different kinds, oil and gas, electricity, all that. Yeah, we don't have any stakeholders that do interconnection or anything like this. So we take it as more of an engineering problem and think about trying to embed ML technologies inside of our tools. And so merging optimization and ML is a real promising area. And I think a lot of the representatives at this conference have done similar things already and are trying to push the boundaries on this even more. And so in other fields that we participate in, chemical engineering, they come up with surrogate models. And so describing in more detail complex systems inside of an optimization problem is something that we're very interested in. And so that's a very promising avenue. I think one of the biggest misconceptions that we see, because we are optimization focused, is that there's a lot of comparison between optimization, the optimization toolbox, and the ML toolbox as equivalents, and that's not necessarily the case. I want to make it pretty clear that optimization comes with some sort of mathematical guarantee for optimality, and that's provable, and that is not necessarily what ML models do. They work together, and they will work more closely together in the future, but just wanted to be pretty clear about that one. So thanks.
Yeah, so again, I feel like the odd duck out on this, and sitting in this room next to these folks who are leading the industry, the usage of AI and in the power systems. But where most of my comments will come from is my extensive background in operations at MISO, and where we think that we see the best near-term usage of AI, and a lot of that has to do around uncertainty management. So we are constantly seeing weather forecasts change, and as we go to a more renewable energy platform, how does that change all those weather-dependent resources? How does your solar respond? How does your wind respond to all those changes? How does your load change to that? There's a lot of distributed energy resources that we don't see as a system operator that is behind the meter. So how does that impact? So we focus a lot right now on how we are training our forecasts and how do we decide when to make adjustments to our forecast. You heard yesterday some of my colleagues talk about how they're looking at dynamic requirements to reserve requirements and things like that. And so right now we're focusing a lot on how AI can best be used in operations to be able to train those models. Certainly, from an interconnection perspective, where I currently operate. We do see a lot of help in there. As Brian mentioned, his use of Grid Unity and what they're doing, what we're doing with Sugar. So we see a lot of help there as well. But our MISO's main focus is around ops. From what might be missing is empathy, that human piece of it, right? There's a lot of concern and trust about AI, and so how do those operators utilize it, and how do they get the trust in it? And then the general public. I mean, obviously, we're providing a service to the general public in the form of electricity, and so when we make decisions that impact people's power, there's going to be concerns about, well, how did you make that decision? Why did you make that decision? Was AI doing it alone? And so, the need to have that human portion of it is always going to be important as we continue to go into the space of how we utilize AI.
Great answer. So for us, for Grid Unity, we believe AI's biggest opportunity today is transforming the interconnection process. It's what we focus on. We can see AI through the testing we've done, basically accelerating intake, accelerating validations, providing better grid upgrade reasoning, and then queue forecasting, and doing this all through kind of structured rule-based automation approaches, right? The tools like Grid Unity's Scale that we showed yesterday are co-pilots. They're not replacements, right? That's a key thing in the human factor that Andy just pointed out. People need to know, how is that decision made, right? But we do believe that AI can help embed expert knowledge into the process and every interaction through the interconnection process. I think the biggest misconception, though, is that AI must be opaque. It doesn't need to be. And what we're trying to do and what we've been proving out is that AI will thrive when it's transparent and being asked to be transparent, and when it's auditable, and when it also amplifies human decision making. That's where we see it fitting in.
Well, I have my own. And thank you all very much for that. And I think I'd love to pull a thread into both of your Alexandre and Adam's points about the difference between optimization and sort of solving and optimizing with a set of constraints, which is very familiar problem to folks in this room, and then AI and sort of making sure they align well. And any sort of further comments to help us either understand the difference of and sort of the challenges of aligning the two, and differences that people should always respect to make sure that they always achieve efficient and expected outcomes. Any further thoughts on that?
Okay, I'll give this a shot. So I think that the idea that optimization is a rigorous set of algebraic expressions that can be that goes through a solver of whatever technology. It could be local, it can be global optimal solutions that kind of come out of this. So we can kind of dig in on some of that if you want to, but it might be a little too technical for now. But it's there, and it's in some ways kind of auditable. Everybody kind of understands that Kirchhoff's laws are there, and these things are physics-based. So that's something that yeah, we sometimes say we give those solutions a certificate. They've got an optimal certificate. They get the solvers do a great job with the return codes that say this is what you get. And yeah, there might be some numerical tolerances and stuff like that involved in it, but it's going to be pretty different when you look at. I always have this mental model, and probably important for the audience to know when that I always think about neural nets and these surrogate models. So that's just kind of where I'm coming from. That's my bias, I guess. So these types of systems are, trained on data, and the training is used to kind of reproduce the data in the best way possible. And whatever that data set is, wherever it comes from, is going to have some kind of perspective in it as well. So you might have a local solution. There might be some sort of gradient method to kind of find your parameters to actually result in this neural net. But you don't get to have the same certificate that anything that comes out of that is going to be optimal anymore. It might be very useful in some cases, but it's not going to be optimal. And so the usefulness is still really good because you might have more and more open energy systems. Instead of just wires, you're going to have climate, or you're going to have very short-term transient effects or something like that. And those are hard to feasibly put into an optimization problem because the problem size might blow up or something. But putting those details in is important for other people to consider. So hopefully that's more detail than maybe the question was. But
yeah, I can add. I can add a little bit to this, and I completely agree with what you said. And I'd say that where you should expect AI to shine is the ability to give you a very quick, I mean, a pretty good answer. It's not going to be the exact answer. It's going to be really close to it. But basically, the way AI works is you spend a lot of time training on a very large amount of data, and then the inference is actually really quick. So you get an approximate solution. You get something that looks like something useful pretty fast. So that comes with a shortcoming. It's very close to the actual solution, but it's not. It doesn't have all the guarantees. And when you're running, for example, this kind of inference on an optimization problem, you may find that some of the constraints are actually violated. They're not there. They are. It's pretty close, but it's not exact, and so there are techniques to work your way to actually get back to an actual solution. But that can be pretty useful. For example, if you want to kickstart an optimization engine with a pretty good solution in order to speed ups in performance. And of course, surrogate models or proxies are pretty good if you have very larger system side. There are things, for example, you want to model some distribution network dynamics, but not with an exact distribution network dynamic, because that would actually blow up your problem. The AI can give you some ideas of what's going on this. And so there are many ways they can actually complement each other. It's not a black and white situation.
Thank you very much. I think also picking up on another comment I think that Andy made is, as regulators who are not AI experts, one of the concerns I could think could come from the regulatory community is transparency and sort of comprehensibility to the both regulators and, very importantly, all the market participants who are participating in wholesale power markets, loads, generators, demand response providers. So in your view, how do you best address sort of what could be perceived as a transparency problem when you start using AI and machine learning increasingly in these systems? Any thoughts on that? And we're programming note from our host. Please try to speak into the mic. Thank you.
I would say only two words: open source. So, but I'll let you expand on that.
I will note that might not be helpful to everyone, the open source part, but they might need to help some others along.
Yeah, obviously I mentioned, the concern about trust, and how do you get that? It's through transparency, right? I mean, maybe not complete open access or open source, but when we are, we have multiple models within MISO, and whether it be obviously weather and wind and load and generation, and so how do you make sure you're providing that trust to folks? And it is through transparency, right? And so we have to figure out how we do that by also keeping concerns about CEII and market sensitive information and data. And so I think we can do that in snippets, right? I mean, yesterday's MISO's presentation talked about how we were using our enhanced forecasts to better predict uncertainty during major storms, right? So Heather from last year, Enzo from earlier this year, the amount of uplift that MISO had, and therefore the cost to deliver electricity to people was significantly reduced because of our better uncertainty management, right? And so can we, if we ever get it wrong, can we look at those types of issues and to provide transparency into folks to say, look, here's how we utilize the data, here's what it resulted in, right? Whether that be a good or a bad result. And so as we continue to adopt more uses of AI, how do you provide that transparency while maintaining sensitive information.
Yeah, I would just add that with AI, especially as it becomes more prevalent, and we do see it for what we're doing, really sweeping through the end-to-end process of interconnection. But in other areas, years ago, we were the first company to really develop a solution to do automated iterative capacity analysis in California. So, and we spent a great deal of time of making sure that we understood the data inputs and outputs at every single step, because we were also passing things off to a third-party power flow solver at the time. And it was clear that there were things going on within the solver that didn't make sense based on the inputs and the outputs. And so now when we look back at all that work, and now we started to look at that and saying, well, how would we apply AI in an agentic process here to really dig in and find out which data points were outside the expected ranges that the third-party solver that we didn't really control was confused about. And we do see AI the really helping actually create a well-defined audit trail. And it is something that we believe is absolutely necessary in the industry. And then also well-defined policy. And the policies that FERC makes, they have to be clear. And then not only that, they have to evolve, because AI is going to force us all to evolve quickly.
Yeah, I'll just add on to that. Brian reminded me of my own presentation from yesterday. Is that how do we provide that transparency and when we make decisions on the study results that we create, right, with the use of sugar? Well, we created a transparent workbook and documented that here's our decision tree. Here's how we make those decisions. Here is how we define costs. And it's AI is just getting us to that answer faster. But here's how we trained it, and here's what it's using, so folks can get that trust.
And I think I'll just add to that very briefly that coming from a more European perspective, so you're probably aware that the EU AI Act imposes a lot of constraints around transparency, auditability, documentation, and things on what they call high risk system. They have this risk classification, and most of the power system application fall into this high risk system. So basically, I think Europe is trying to figure out ways to comply with this. It's not necessarily an easy process, and there's a lot of things that need to be clarified. But Europe is also looking at this more from a EU Act, EU AI Act regularity. Regulation compliance. So there might be some interesting inspiration to draw from that.
Thank you. We'll have to check that one out. I think picking up on that other question, I'm sorry, some of your, actually your response in terms of identifying risks. What, in your view, are the risks, if any, that are posed by using AI and ML more and more in the wholesale market space? Do you see like hallucinations predicting infeasible dispatch or other type of risks? Like any thoughts on what those risks are, their magnitude, and means to mitigate them would be great. I know you already spoke, Brian, to that somewhat. You can have AI help you check and identify bad research, but any thoughts on that would be greatly appreciated.
I'll go first so that I can get my easy answers out of the way, right? Let these guys fill in the hard stuff. Obviously putting controls around AI, right? How when you use ChatGPT, if you don't give it the right inputs, it's not going to give you the right outputs, right? I had it recently read a FERC order to me, and then when I got my lawyers, they're like, I didn't quite get it all right, But how do you put those controls around it? Cybersecurity is going to be the biggest one, I think. Is that if you're using a closed AI system, as what it's being taught and what it has access to, but then how is that data being stored, right? If you're using a third-party vendor and you're loading sensitive information into that, You got to be concerned about where that data might be stored or who might be using it, right? So us as an RTO, we need to make sure anybody we partner with, we understand all that and we have the right controls around where it's being stored and how it's being processed. And then of course, again, I'll reiterate, how do you keep people into the process as one of those controls to make sure that there's a human element evaluating it's being told, so it can utilize, although that very quick information, utilize it towards other more standard processes.
Well, I'm gonna take that. All right. So I don't think the risks are in AI or in the technology. It's more about how the technology is applied, right? We do believe, and to Andy's point, there has to be clear logic that's well documented. You must have curated data in the process. And you also make sure that AI is aligned with regulatory processes, right? This industry is and to Alexandre's point about Europe, they've identified key risks around technologies, right? We, as a country where we're very FERC and other regulatory bodies really have an influence on how we look at the grid, support the grid, and make sure there's transparency in the grid. So AI can also be used to reinforce outdated practices, right? And as we do change, you don't want to be using those because all it's going to do is introduce fragmentation. So guardrails like standardization, transparency, and oversight must scale alongside with the technology in our mind.
I'm just gonna add a little bit to this because I completely agree with that. I think the key terms in the term of trust is how we can get explainable AI. You need to be, the AI needs to be able, when it's interacting with an operator, the operator needs to understand how the AI came up with this, and that's a whole research. That's the whole field of research that I think we need to invest in this. Not only the technology, is how the AI operates well with the operator. It's here to help. Otherwise, the operators are just going to reject it, and and we're seeing this. So there's a lot of things, and that takes us a little bit away from a technical focus to more of a social science perspective, which perhaps could be something where we explore this in future conferences. But to me, it's really important. And on the cybersecurity, I'll just add that AI introduces new risks in terms of cybersecurity that are specific to it. So AI on the one hand is very good at helping cybersecurity because it's very good at detecting some kind of threats, but there are other ways like your data pollution, for example. And to your point, I think one of the best way to actually trick any kind of AI thing is just like to induce a little bit of pollution on the AI data, and this is something that we're not really equipped right now from our standard cybersecurity approaches to look at these very specific things. So there need to be a lot of research, and there is a lot of research on this. It's not only power systems, but for us this is something that needs to advance to the point where we can say it meets the standards of cybersecurity that we need for our critical systems.
Yeah, thank you. It's certainly true that power systems brings to bear many disciplines of engineering, computer science, operations, regulations, economics. So we all belong in the room, Andy. And so it's really helpful to have this conversation. I would love to hear your views on what are some of the biggest obstacles to leveraging AI and machine learning to improve outcomes and add efficiencies and reduce costs to power systems, and including one of those obstacles can certainly be regulatory. And if you have any sort of solutions or advice or that you'd like to share with FERC, thanks for noting already the EU guidance on AI, but sort of your thoughts on the biggest obstacles to wider adoption, including regulatory, and and sort of solutions to overcome those obstacles.
Yeah, sure. So I just say as a preliminary thing is if you want to add to your reading list, LF Energy released a white paper on AI earlier this year, so you can look it up, and it actually addresses a lot of the questions that you have. So here, in terms of barriers. So we've talked about data quality, AI governance, operator adoptions. I think one of the things that I hear a lot from the AI community is how can we get access to data? And I think that this is a complicated topic because on the one hand, we know that there are privacy and CIP constraints that there's no way around it. These are important. The privacy is an important thing. CIP is a very important. Critical infrastructure protection is something that is critical, and so you cannot get around it. And at the same time, our researchers, innovators, they need access to realistic data to work on. They need access to the real problems. Otherwise, they're not going to do anything relevant. I mean, or it's going to be much slower. And so one thing that we've been promoting at the Linux Foundation is establishing open, realistic benchmarks that are basically leveraging techniques around synthetic data generation. You can do simulations. You can do essentially. It's about making a mix of real, simulated, and synthetic data to provide something that's realistic. It looks like you're the real thing, but it's not the real thing. So it's not as critical in terms of privacy and CIP as the real thing. And that's what that allows innovators to take a crack at these problems in an open fashion. They can they can do a peer review research. They can do a lot of those things, open research that are really good. And once they come up with something that works, then they can go back to the actual data holder and say, okay, we're going to sign an NDA and then test it on the real thing and do a real application. But basically, that's one of the things we need. And the other piece is actually the benchmark side. One of the problems right now is for lack of those established data sets. A lot of people are just playing with the data they have and in an inconsistent manner. So when you find two techniques, two presentations from this conference, two papers, sometimes the benchmark, how they benchmark on the data set is very different and you cannot really compare it. So it used to be back in the days, IEEE worked on this IEEE network that we all like and love. That was in the 70s. Our networks have changed since then. The size of them have changed. The problems on them have changed. So we need to work as an industry to reduce some of these benchmarks that are proved really useful and make sure that our researcher, innovators, startups, all of this innovation ecosystem that's begging to help us as an industry solve our issues, they can get access to the data they need to work.
So I'm an engineer, so this is for the engineers in the room. I came into this panel discussion thinking that there would be no way that anybody's going to share data, and I completely forgot that synthetic data was a real thing, and that actually GAMS had participated in ARPA-E Go competition a few years ago that was all about synthetic electric grids, and yeah, that was on me. But the idea that just sharing maybe a trained neural net was just not going to ever be enough because the trained model is just going to kind of sit there and you can poke at it and stuff, but no one's really going to gain that confidence and that trust unless they saw some data. But if they can't share data because of critical infrastructure issues, then how else can we all agree on something? So I think it's exciting to hear that there are folks doing really tough work on generating synthetic data to train these things. So kudos.
Yeah, so I guess I'll ground us again, as a system operator. It does come down to trust, right? I mean, yes, the folks who are working in AI, they want more data, more data, more data. Let's feed the machines. But there's always going to be a human element in it. And how do we make sure that they have the trust in it, right? Certainly transparency is one of them. But it's like, how do we train the people as well? It's like, okay, you have the transparency, you're getting the trust and the outcomes, but then how do you train our folks on it? And, so that's really what it's going to come down to for us is that the industry is moving so fast. The AI can have this exponential growth, but then you still need to have your people there to provide the experience and provide the needed information that computer system doesn't have. And so how do you train folks to be able to use it, to make right decisions, to trust what they're seeing? That's what it's going to come down to.
And thank you very much, Andy. I want to make sure, Brian, did you have any further comment? And you don't have to, it's
No,
voluntary.
I think it's been covered by the other speakers.
Great, thank you. And Andy, you also brought up a really important dynamic, which is a human element. We like to think we still have some value to add. And it sounds like at MISO, and the human element is gaining trust, but also making sure you still have all that experience and heuristics that the operators of the system and planners have. So how do you, any sort of thoughts on making sure that we still, how to best integrate the human element to ensure good, efficient outcomes and avoid some of the risks? Any other thoughts on that?
Yeah, I'll go back to the control.
Including trading, sorry.
Yeah.
Another great point too.
Training and controls, right? When you see such quick results that are near close, we talked about that, and like, oh, you want to keep feeding it and keep using it and seeing what it'll come up with next. But there's a lot of this group is all in research, right? And so that's where it needs to start, right? Is start in the research, get comfortable with it, before you start deploying it in operations, or even into planning, right? Like what we're doing in interconnection, right? I mean, well, that's the first step, right? The generators aren't even built yet, right? So we have a lot of time, and you can speed that process up to be able to get the right answer for interconnecting, what are the network upgrade costs, and so on and so forth. But as we really got to think about what's necessary from informing operators is really we want to make sure we keep the lights on, and that's first and foremost.
So one thing I would add is the human element is critical, and it is critical to what we discussed earlier about trust, right? In our way of thinking, because we've been involved in interconnection now for a decade, and we have millions and millions of generation and load applications that have gone through the end-to-end process. It's about training, not just training the engines, but training the people. So you need to understand the role of each individual in the process, and you need to make sure that they can look at historically what were the decisions made when we first look at this application, and then how did we validate it? And then what did we do during the study process, and what decisions were made? You're basically asking people, and you put them through, in effect, a training course where to look at what was done historically, because there's no threat in that. It's just an observation. It's very objective. And so you can see what decisions we made until the project was commissioned. And then what you can do is make sure that the software kind of rides shotgun with you as you go through the next cycle, which is what we're doing, right? So then people can see it's kind of like having your little angel on your shoulder, right? And it's there to observe and help you look at what is being suggested, what might be missed, and then you prompting it, right? And you telling it, well, this is the right answer. And it just becomes a comfort feeling of having another person, kind of like a peapod approach, sitting right next to you and helping guide you. So, but it is all about training the people in the process in order for them to become comfortable. And I think that's fundamental to actually allowing, AI to be interwoven into our processes and create value.
Any other comments on that? Well, please go ahead, Alexandre.
So I completely agree, and this echoes a lot of the discussion we have with our utility system operator and other members at the Linux Foundation. We're trying to build sort of a toolbox around AI readiness and AI governance. What does it take? What are these practical things? So of course, from the operators that we have and what we get from training, the human element is is really key. So happy to actually work with anyone that wants to share best practices, because I think that is really your common challenge for the operators, especially, and where everybody can actually take good ideas and input from this. On a more research side, I wanted to point out again from the European experience. There's a European project that's called AI for RealNet, and that is basically looking at how you design AI to interact with operators. And basically, the EU is funding it. It's actually across industry, looking at power system, transportation, and aviation, for reasons that you can immediately guess. These are situations where you have operators taking real-time decisions, and basically how you design AI system to help them, and not I mean, with the right training and everything, and so they've been doing a lot of good work on the research basis. So if you want to have a look at this is a pretty good inspiration.
Thank you all very much for your insightful answers and raising new issues that I think are certainly new to me and hopefully insightful to the audience. We have just a couple minutes left. Before I have one question, but I wanted to see if anyone in the audience would like to ask a question, pose a question to the group. Here we go.
I always can be relied on, but I do have a kind of concerning question here. So I wanted to ask each panelist, what is the application in power systems, because we're talking about power systems here, and power markets, that you think is the most exciting opportunity to create value from AI? And lest we get to be too much cheerleaders for AI, I'd like you also to each identify one of the areas where you'd say AI is not appropriate, because in fact, we need to remember that AI is nothing more than a really fancy regression method. And like regression methods we learned in school, we can be overfitting to the data, and we're always just training on the data we have, which means that that's maybe the origin of hallucinations, and also we can't use it to forecast what's coming in the future. And also it is opaque. And in spite of the question that was asked about transparency, it's not transparent. And so we just need to always keep in mind that we're just doing a fancy regression. So if you could address, with that in mind, what you'd also say we need to stay away from with AI. Thank you.
Sure. So I'll say what I had said before. We see a lot of benefit in uncertainty management, right? As we, there's still a huge appetite in the United States for renewable energy, and if we get more wind and solar and batteries, all of those provide uncertain behavior because of their reliance on weather. We're getting more climate changes causing more extreme weather, and so you're getting all this information, and a human brain just can't process it all that quickly. So how can you use AI to be able to do that? So we're doing that to help train our forecasts, and really what it comes down to is we want to provide energy the lowest possible price. That's the whole point of markets, is to provide the lowest cost price. And so how do you shave those margins? How do you ensure that you don't have more generation on than you need? Well, you need to know what your generation is going to be there to be able to provide just enough headroom to keep you reliable, or maybe you need to provide a little bit more headroom because of the uncertainty of what you're dealing with. So we think that's what's exciting right now, and what we're really trying to focus on, and how we believe that we can and we have shown results in providing electricity cheaper costs because of the weather conditions that we're dealing with today. I'll say from a risk perspective is that do you ever want to turn it over to AI, right? No, probably not. At least not in the near future, right? You always have to have that human component there. We've had a unit dispatch system for over a decade that has been dispatching power for us almost 2 decades. But it's still an operator there that hits that button every 5 minutes, right? We have the ability to have it be automatic for a long time, but when you send out those 5-minute prices, and maybe you could have done better because you didn't rely on a computer, do you still want to have that operator there? I think that's something that we'll continue to need, to have that human intervention until you really have that full trust in those computer systems.
So I think I'll try So I appreciate the regression analogy because that's always important to keep in mind. So I think that there's a lot of work that I don't necessarily know about, but I've heard a little bit about where ML models might be looked at as replacements for physics-based models in the future. Now, it's a total research area as far as I can tell. Maybe other people can educate me on this, but boy, it would be really, I would want to go slowly towards that kind of, if that was a goal. That seemed like, that was surprising for me to hear. So that would be something that I would see as immediately a risk, but it's just maybe because I don't know enough about it, but it's also seems different to me. I like the equations that can kind of be written down and stuff, so that's good. So so that would be a risk. I think the opportunities here, I was trying to read a little bit about what the state of research is and Google Scholar before coming out here today, and there's some really interesting models that have been trained on physics-based simulations that can then embed new more detail into kind of other models. So you don't have the explosion of variables. You don't have the solving difficulties or extra nonlinearities that you just can't deal with. But you can kind of approximate some really interesting effects. And I think that's a pretty exciting area for us. So anybody else?
I would just add what I've already said. I think interconnection lifecycle management, AI basically is it going to make a significant change in the amount of time it takes us to go through the process. Those experts along each person's shoulder, from just reviews, analysis, even during construction management and out to commissioning, I think AI really will play a strong role there. To your other question, I wouldn't seek out love through AI.
A great final word over from you, Brian. Andy.
I don't have anything to close on that.
Please go ahead. Any thoughts? Are you?
No.
Well, thank you.
Can't follow that.
Yeah, indeed. That's a good note to end the panel on. No, but I really truly appreciate this discussion, bringing some other dimensions and other people from different disciplines into the room to have this conversation. There's definitely been some very successful demonstrations of AI and machine learning in power systems, and we look forward to what the future brings. Thank you all for helping us think about that.
Thank you.
Thank you, Emma, and thank you to our panelists. We are breaking for lunch, and we will be back at 2 p.m. Thank you.
Alrighty, we are going to go ahead and get started. Welcome to session W3A. And up first, we have a virtual presenter. So we have Andres Ramirez from Lehigh University. And Andres' presentation is titled Advancing Market Efficiency and Reliability, Forecasting Emissions and Asset Risk in Electricity Systems.
Thank you. I appreciate it. I just want to make sure that my audio is working correctly. Hello?
Yep, we can hear you.
Yep. Wonderful. I appreciate that. Thank you. So my name is Andres Ramirez. I'm here with Lehigh University and Professor Alberto Lamadrid, and I will be presenting today app scores, an application of banking scoring and rating to electricity systems. This is the team that collaborated within this project. From Lehigh, we created the majority of the methodology and results that you will be seeing in this presentation, but behind this, there are several other projects that supported this initiative as well. So the Lehigh Risk Scoring Project, or the App Scores Project, is an initiative to create a risk scoring system for energy generators and prosumers, among other stakeholders in the United States. The case study we used specifically is for New York ISO. However, this could be used across the United States. And the goal is to quantify the likelihood of imbalances from the accelerated inclusion of renewable energy sources. So since the main goal of the project is of risk scoring or risk assessment of energy generators, it's important to define what risk is in our project. For us, risk is a positive or negative deviation beyond the expectation from the energy unit commitment for a specific generator. The problem statement is, how can we use data, machine learning, optimization tools to better evaluate and forecast the risk of assets in the electricity system? And then how can we use these risk measurements to help manage overall risk and also help the generators or prosumers to be more efficient in their operations? So let me start with a motivation of how we started with this project and where this idea arrived. So the current issue is there's often imperfect, asymmetric, and private information that contains all the nuances of the operation of the energy generators that really can't be shared between generators, or even like share on a more broader scale to take actions across the whole system. And there are also missing mechanisms to manage risk due to these information failures. So the idea is, how can we create a risk scoring system similar to what credit scores is doing with the probability of default on a loan application, right? To create a system that will allow us to generate a risk score for every generator that can be shared both amongst energy participants and also be used to create mechanisms or policies that will alleviate the risk of the overall system. So here in the top, you'll see two charts. The one on the left is that idea of how we understand credit scores versus app scores, which is what we're proposing, and also how that relates to the probability of default on a banking system, and we understanding that risk in the electricity system based on their deviations from their unit commitment. How we can use this at a high level is, once we have an understanding of all the energy generator profile, we will have distributions of these risks that will allow to create policies or treatments that will allow to manage low risk or high risk generators and understand how they are contributing to the overall risk of the system, all using the app scores as a metric. So the opportunity here that we find is to introduce an independent third-party risk assessment software that will generate these risk scores, and then that eventually will leverage them to try to, again, bring that efficiency to the whole system. So the solution we propose is a data-driven electric asset risk bureau that enable financial products for trading and managing assets, and also managing the system risk within the electricity system. So it will summarize multidimensional data. Again, the main goal is to remove that asymmetrical information, creating a centrally managed and market-driven system that includes operational decisions and long-term planning, as well as evaluating the impact of day-to-day reliability and resilience to high-low or high-impact, low-probability events. The benefits of this is, with more reliable data, we get a better understanding of current and future risks. And also, and most importantly, less information asymmetry means better dispatch decisions by operators and other market participants, as well as a more reliable and stable grid. So I'll start speaking about this idea of the data-driven risk bureau, or this third-party independent risk assessment software, and we call it the Electric Asset Risk Bureau. So the goal here is to develop a novel data-driven probabilistic scoring and rating model, and then creating an information management system that shows both historical data, their performance there, and also we could create forecasts on how this risk is going to look into the future and provide all this information both to energy generators, prosumers, but also in a more regulatory manner. And then the key goal here, the main goal here, is the integration of the risk scores as the tool that would allow this to remove the information asymmetry while still incorporating the risk. So incorporating the risk goal in the operational decision making, and then identifying, based on this risk score, missing mechanisms and products that will allow better risk management, and of course developing those products and starting like that incorporation into the overall operation. So for the path to broader adoption, we sort of established like a 3-step procedure. Of course, this is not written in stone, but this is the main idea. So the first step is buying from stakeholders, so obtaining support from PGM, New York ISO, CAISO, etc. And then do a 2-phase pilot. First, looking at historical data, creating the app scores and evaluating how they perform, and then doing a more real-time sort of integration, leveraging information from agents or generators, and incorporating the findings from the historical information. That third step will be, once the pilot is completed and it shows its promise, establishment of an independent electric asset risk bureau that pretty much operates this moving forward. So this is an interesting chart on top that sort of shows that 2-phase pilot I'm speaking about. So the first phase, which we call centrally planned, is using historical information, the app scores that we will generate, and other strategies to try to understand how can we improve scheduling and create risk differentiated strategies to minimize risk both for energy generators and the overall system. And the second phase, which we call restructure, is again using the app scores, but now including information from the agents, not only historical information, to develop a marketplace or a design of market sort of software that will allow delivering services, pricing, evaluation, and other strategies that, again, will the main goal of all of this, as I mentioned before, is trying to reduce the risk of the overall system. There are a couple of other important things here. So, for example, identifying geographical tendencies, performing counterfactual and what-if analysis, and then, of course, providing the app scores to stakeholders and market participants, which is the main goal of this risk bureau. Key innovations of this electricity asset risk bureau will be like first an onboarding process. So first we need to understand past data recollection, requirements, constraints, system characteristics, and whatnot. Second step is identify usable data sets. And then third is to create scenarios, perturbations for risk measurement. So using the app score risk calculation to evaluate historical patterns and then create future scenarios that will allow us to be prepared sort of for the quote-unquote black swan events, making sure that we are using the risk score as a way to evaluating how system might deviate from the operation of energy generators. Okay, so I'm going to transition now more into the details of what this risk score looks like and how it's calculated. So I'm going to start from the top chart. We start from scenarios. These are data scenarios. So energy generation, particularly from renewables, which are the sources that provide the highest variability, and then also load, so demand of energy. We take that information and feed that into an optimization model. So the optimization model is going to be that bottom left box. You see that's running the security constraint unit commitment and security constraint economic dispatch. So this is pretty much evaluating the unit commitments and the economic dispatch and providing a robust data set that contains prices, unit commitments by generators over time. With this information, we go into that third step, which is called estimation, which is really just understanding this data, doing the feature engineering, and building the data required to create the scoring mechanism or the risk score. The fourth step, which is what we call the machine learning pipeline, is taking this information and translating this information into the risk score. The risk score is based on the probability of deviating positively or negatively from the unit commitment. I will go into detail on these two in the later slides. After the scores are ready, there's a re-optimization and counterfactual step, pretty much evaluating the impact of these scores, what would happen if we applied certain policies, like a threshold policy, for example, on limiting the unit commitment from energy generators based on their risk. So, for example, a high-risk energy generator may be constrained of what they can commit or not, versus a low-risk, maybe their scope of commitment may be broadened in order to, again, the main goal here is to reduce the risk of the overall system. So let me get maybe into a little bit more in the details on both the optimization model and the machine learning model. For the optimization model, again, we're running the security constraining commitment and security constraint economic dispatch. The flow of the system can be represented by alternating current models, creating nonlinearities or with different linearizations. How we use a direct current linear model of the network flows. I'm not going to get into many details of the generalized formulation, but I think the main components of the objective function is to evaluate the cost associated with discrete variables and the cost associated with continuous variables related to physical deliveries or contingent services, and then the constraints of optimal power flow and security constraints guaranteeing the system can operate if there are any deviations. This optimization model was implemented using MatPower, and then again, we run all the simulations through the security constraint unit commitment and economic dispatch to generate what is the optimal output for each specific scenario, which is all data then we use in the next step. The next step is the risk scoring generation. To generate the risk score, there's two big steps. The first one is to evaluate the probability of deviating positively or negatively from the unit commitment. And then the next step is the scoring mechanism, which I'll speak about in the next slide. For calculating the probability of deviation, we use a classification method. Here we're using an elastic net logistic regression. We evaluated several models from purely black box models like neural networks to tree-based models, ensemble models, and whatnot. We landed on the elastic net logistic regression, or also known as logistic regression with L1, L2 regularization, both because it provided great accuracies matching the black box models, and also it allowed us to understand the specific or individual effect of all the input variables with their coefficients, allowing us to also provide an understanding of why a probability is given, not only obtaining an accurate probability. So it provided that balance that we were looking for. And that was also needed to be able to apply the scoring mechanism that I'm going to speak about now. So this is the scoring mechanism. This is something we borrowed from credit scoring, where we use something that's called as weight of evidence. And the coefficients from this elastic net logistic regression to create a score metric. The reasoning behind going from a probability to a score metric is there's a broad knowledge of what a score means. If you tell somebody their score is 350, it's kind of already in our minds what a 350 score means, like it's high risk versus an 850, for example, that is low risk. So we try to use this because we want to leverage that knowledge that is broadened across all industries and apply it here in terms of evaluating the risk of an energy generator.
And sorry to interrupt, but just a 5-minute warning.
Thank you so much. I appreciate that. So I'll show some results real quick, and I want to get some to the questions as fast as possible. So this is the generation mix, and risk scores for different periods of time. For example, what you will see here, right? It's for a future forecasted period in 2030, what the generation mix looks like for two different periods of time. So the first one is in March, 24 hours of a day in March for 2030. And then the chart on the right is 24 hours in August. The key difference here, it's the renewable energy penetration and also the natural gas consumption. So in March, you will see the wind, which is that green section you'll see there, it's much larger than on the right chart. And if you look at the chart on the right, you'll find how the natural gas megawatts requires much larger than March. And this is due to seasonalities. The reason we're showing this is to show a little bit of the difference, the seasonal difference, and how that impacts the consumption of renewable energies, which should be directly correlated to the risk of the system, how we are understanding risk, since a greater inclusion of renewable energy sources should increase the variability or risk within the system. These are some of the results of the risk score. I'm going to try to go as in much detail as possible. So these are things that we can provide from the risk score that we are generating. So I'm going to start from the top left chart. The top left chart shows a distribution of the risk score for all the energy generators by the hour of the day. So you can sort of see that majority of generators are between that 600 and 800 mark. There's some generators that are towards the left, closer to that 400 range for this specific day. So that allows us to understand, okay, why are these generators out there? What is prompting them to have a low risk score versus a high risk score? And this allows me to move into the second chart, which is the one in the middle on top. This is a breakdown of the impact of each specific feature we are using in the risk score. These features range from energy generator characteristics, the fuel they use, for example, among many others, and also the operational variables that are outputted from the optimization module. So their unit commitment, prices, the ramping mechanisms, etc. It's all incorporated here. We anonymize the features just for the sake of this presentation, but ideally we will provide a breakdown of what's driving the risk scores up or down for each generator to understand their performance. The one in the top right is the risk score profile for every hour on all the generators for a specific generator, excuse me, that is a wind generator. And then on the bottom chart, you will see a little bit of that, how the risk score is changing over time. So from the hour 0 to hour 24, and we find some of those intraday characteristics or seasonalities in terms of energy consumption. I'm gonna end up this slide with the bottom right chart, which is the app scores desk, which is a dashboard that we constructed that contains all this information and allows the user to go through generators and look at aggregated and deaggregated views of all the risks. There's spatial risk scoring, which is understanding how the risk changes in space and time. And this is connected to the chart I showed before with the generational mix, where you'll find those discrepancies in March versus August. But because of time, I want to move a little bit faster here because I want to speak about the emissions piece of this analysis. So on top of what I've shown before, there's a key component, which is emissions forecasting. So leveraging that same infrastructure I spoke before, we could also predict, instead of predicting a probability of deviating, we could predict also emissions from these generators and incorporate this into the overall strategy and again, accounting for emissions. So the idea behind this is pretty similar. We use the same type of data, but the model in itself that we're using changes. So instead of a classification model, it's now a regression model that tries to predict the emission, for example, CO2, NOx, or SO2 for a specific hour for a specific generator. We analyzed data from 2019, so the same data used for the app scores, and we forecasted the pollutions for all these generators as well, using the information from EPA. I'm going to quickly show this chart here just to finish the presentation with this, which shows the fit of our model on how we're able to predict the emissions of all the generators for every hour of a specific month accurately. And then the goal of this is, again, to incorporate this as an additional attribute or dimension to the risk score in case there's policies that want to control for emissions or penalize them or not. Is something that we also wanted to incorporate into this analysis. That's it for my time. I appreciate you so much, and any questions I'm happy to take now.
Hope you can hear us clapping in the room.
Thank you.
Now we will turn to a Q&A. Just a reminder for folks joining us online, please place your question in the Q&A and we will call on you to introduce yourself and ask your question. And we will start with any questions in the room.
I have one, actually. So when you're calculating emissions specifically, are you looking at the entire life cycle of the generator, or are you just looking at their live emissions from fuel specifically?
That's a great question. So the answer for that is we are incorporating characteristics of the generator that will account slightly for their historical performance. So like when was it first installed and that sort of nature of the generator. But for the emission itself, we're only looking at the output of the optimization module. So based on the ramping and based on their energy output, etc. With that, we're sort of estimating what their emissions may be, depending on the fuel type, depending on the hour of the day, the seasonality, where they are located in space, for example. Those sort of intrinsic characteristics of the generator we're using. But in terms of operations, it's only whatever is outputted from the optimization module.
Okay, thank you.
I don't see any questions online. Are there any other questions in the room?
Well, thank you. I appreciate it. It was wonderful to be here. Thank you.
Thank you so much. Alrighty, so next up, we have Adnan Badarud from MIT. And his presentation is titled Factor-Based Portfolio Optimization for Risk Management in Electricity Markets with Renewable Energy. Thank you.
Great. Thank you so much for the introduction. It's great to be here. I've been to this conference quite a few times, and I always learn a lot when I listen to all the presentations. So actually maybe on a personal note, so managing risk is important, right? So I need to get back to Boston tonight for family reasons. It turns out the flight I booked was canceled due to weather, apparently. So I booked another one, which was also canceled. So N-2. But luckily, the train is still operating, so I'll have to catch the train right after this presentation. That's good. Flexibility is a good thing. So what I'll be talking about is something we've been working on at MIT, which deals with managing other types of risks, renewables risks primarily. And if you go to the next slide. Okay, so that's the old set. That's all right. So okay, so this is also part of the same project that Andres was talking about in the previous presentation. It's one of the ARPA ePerform projects, app scores. So Andres was talking about the work on developing risk scores and you know. How that could be used in operational decisions. So we at MIT, we contributed to this work in several ways. So maybe if you look at this figure, let's focus on the right-hand side, on the kind of green box there, which is kind of illustrating electricity market operations at a high level, where you have ISO RTOs running scheduling dispatch decisions and clearing markets as well, interacting with market participants, of course, and also you have a market monitor. And one sort of basic guideline in this project was that we didn't want to mess or change too much with the basic. All right, let's see what happens next here. But we didn't want to change too much the inner workings of these electricity markets. So that was sort of a constraint, if you like, in how we approach the problem. And Andres, he was talking about, maybe this is the most up-to-date presentation. Yes, there we go. Okay. So yeah, so backtracking a little bit here. So you have seen these pictures in the previous talk. I just want to point out the key contributors to the work I'm talking about. It's Yusu there on the right-hand side under the MIT team. She was a postdoc at MIT until last year. She has extensive experience from finance, so she brought some of that experience into the mix here, which was great. And then Arnab as well at Lehigh contributed in terms of power systems modeling. And Alberto Lamadrid, the project PI, was also part of the team. So if you go to the next slide. So yeah, so here's what I was talking about. We didn't want to make too much changes to the inner workings of markets. So we kind of arrived on placing this risk bureau idea, this new entity outside of that existing box there. At MIT, we focused on a couple of ways to improve system level scheduling, and that could take part within this risk bureau. We kind of converged on the message that these types of optimized schedules would kind of inform decision making happening in the green box without directly changing or adjusting schedules. That was kind of the philosophy we used here. So we worked on two different ways of accounting for risk and uncertainty in system-level scheduling. The first one was that we developed a stochastic bi-level model, which still aligns with deterministic traditional market operations. Basically, that model would find the deterministic schedule that brings you closest to the stochastic ideal. And that's a computationally challenging problem. So we were, thanks to Dong Wei, who is actually here in the other room probably, he was able to come up with a computational scheme to speed up that calculation. So we could solve that at a relatively large scale. Now, what I want to talk about today is just the point in red there, factor-based portfolio optimization, which deals with managing correlation in uncertainties in system scheduling. So if you go to the next slide. Yeah, just to show that as part of the project, we did produce, as good academics, we produced several papers, and the one that I'm talking about today is in red there. It's available as a working paper. Next slide. Okay, so we were interested in applying learning methods, computational learning, machine learning, to look at the complementarity, primarily in renewable energy assets, so wind and solar. We experimented a bit with different approaches, so-called self-organizing maps for investment planning. But we made more progress with the factor-based portfolio construction for operational deployment. So if you go to the next slide. And the way we approached this was to compare different approaches, primarily two different approaches to managing risk in system-level scheduling. And we defined risk. In this case, we focused on renewables. So it's the difference between the forecasted generation and the actual real-time delivery for renewables assets. And based on risk measures, risk scores, or other metrics, you could, in principle, adjust how much of these renewables you schedule ahead of time to better position your system to deal with this uncertainty in renewables. So that's kind of what we're trying to do here. And the first approach, which we refer to as the single asset approach, assigns a risk score to each individual asset. It could be done along the lines that Andres talked about in the previous talk. And then you would adjust the schedule of those assets based on that individual risk score. So it's simple and transparent and easy to manage, but it has some shortcomings. And that's why we focused on the factor-based portfolio construction, because the idea there is that you also look at the correlation in forecasting errors between different assets. So we try to construct a portfolio that minimizes the aggregate forecasting error across the region that you're looking at. So in principle, that means that you don't necessarily penalize an asset because of large variance in the forecasting error. If that variance is negatively correlated with other assets, it may actually not be a bad thing. So we're accounting for that here with this approach. Yeah, so next slide. So what we did here, and Yusu, the postdoc, she was driving this work, and she, again, inspired from some of her work in finance, she applied what's called factor-based portfolio construction. And this kind of gives you a high-level idea about what's going on here in terms of math. You start up with a matrix of forecasting errors. So the forecast minus the actual delivery for different assets, different plans, and different time periods. And then you want to identify a subset of factors that explain most of the observed variability in those forecasting errors. And that's where we use so-called principal component analysis. That's a method, a well-established method that's been around for a long time, but it came in very handy here. And basically what you do with PCA is that you first standardize that E, the forecasting error matrix. You calculate the covariance of that matrix, and then you do some so-called eigen decomposition to identify eigenvalues and eigenvectors, and those vectors basically form what's called principal components, and they are orthogonal on each others. And the good thing is that, typically just a handful of those principal components is sufficient to explain most of the observed variability in the original forecasting error matrix. So the final step of PCA is to determine how many factors you want to include in your set of principal components, or factors as we call them as well. And then you get the matrix F there, which is the set of those factors. And then, the next step is to calculate the risk or the variance of your portfolio. That's the equation in the middle there. And then we introduce W's, which is the weight that you apply to each individual asset. And then you use the principal components to calculate the level of risk that's captured by those components. And then you have an additional component which is independent of those factors. And that's a pretty simple equation. And the next step then is to try to minimize the risk that is captured by those factors. And that's the final step there in the slide, where you try to find the weights, how much you dispatch of each individual asset to minimize the total risk or the total variance. And that's subject to a constraint, which is perhaps somewhat artificial, but it tells you how much of the original renewables you want to make use of in the system. And that you can vary, from 100% to less than 100%. Okay, next slide. Okay, so to be a bit more practical here, so we applied this on a data set from New York ISO, about 300 existing or planned solar PV sites. 1 year of data that we split into 2/3 of training, 1/3 of testing. We did the PCA approach to identify those principal components or factors. If you look at the table there, you can see that the first one explains as much as 58% of the original variance in forecasting errors. And if you add a couple of more, the cumulative variance becomes as large as 90%. So you capture 90% of the original forecasting errors. So we decided to stop at 3 principal components in this case. And they don't have like a direct physical interpretation, but if you look at the graph on the right-hand side, which is a measure of the errors captured by each factor, they kind of have a seasonal type of shape, which may be possible to link to some physical phenomena in the system potentially, but it's all data-driven. So if you go to the next slide. So as part of the factor-based analysis and PCA approach, we also can calculate what's called factor loadings. That's basically the correlation between the individual assets forecasting error and the factors, the 3 factors. If you look at these dots there, you might be able to identify the state of New York. So these are individual solar farms spread around in the state. The different colors represents the level of correlation between the 3 factors that we chose. So blue means negative correlation, red means positive. And the thing is, when it comes to constructing portfolios, you would want to have a mix of different colors, basically, because if you do that, you would tend to get forecasting errors that cancels each other's out. So, diversity is good because it reduces forecasting errors, similar to how diversity is a good thing in finance and in some other parts of life as well. So that's another output from the analysis. We go to the next step. Next slide, sorry. So we did calculate some more aggregate forecasting error metrics. This is all pure statistics, for the aggregate forecasting error from those assets. Shortfall is that's just one side of the error distribution when you're short in real time, and we compare the single asset versus the factor-based portfolio approach. And if you look on the left-hand side, you can see that shortfall measure is considerably lower for the orange factor-based approach. We also used another risk metric, conditional value at risk, and we looked at the improvement in conditional value at risk for different confidence levels. That's on the right-hand side, and for different renewables demand levels. And you can see like improvements around 15-20% when you go from single asset to factor-based multi-asset approach. So, the message is that you do reduce forecasting errors considerably when you do this, when you account for the covariance between forecasting errors. Next slide. Yeah, this is too much information, but we also kind of did a more granular analysis where we looked at individual days and hours. Basically, red is a good thing because it means you have a lower shortfall based on the factor-based analysis. And you see a lot of red in this map. So that basically shows that the method consistently performs better than the benchmark single asset approach. Next slide. Okay, so so far it's pure statistics. We have shown that by accounting for correlation in forecasting errors between different assets, you can reduce the aggregate forecasting error, but we need to schedule the power system, right? So how can we make use of this when it comes to scheduling decisions? We focus on day ahead, and it turns out you can actually make use of the information from the factor-based analysis quite easily here. So we took like a classical unit commitment formulation from Math Power, I believe. You can see the high-level objective function and constraints there. And the key is that the only change that we made was in the maximum operating limits of the variable renewable assets in the system. We introduced this weight, this W, that comes directly from the factor-based analysis. So we basically reduced or adjusted the maximum output from the renewables based on that weight that we calculated in the statistical analysis. So that's the only change in the formulation. So if you go to the next slide. And we did some testing, again, using the New York ISO system, a future configuration for 2030. You see some of the statistics for the system. What I didn't include there is that we also considered transmission constraints, something like 2,000 nodes and lines from what I recall. We used wind and solar power time series from a different part of the Perform project, and also this PG-SEN tool from Princeton to generate a set of scenarios for wind and solar. The testing so far hasn't been particularly extensive. We only looked at one select day, a high demand day, August 2nd. We compared 3 different day-ahead strategies. The baseline is to use your mean, your average VRE forecast as input to your unit commitment problem. The second one is the factor model that I've been talking about. So we adjust the renewables outputs based on those weights. And then we also have a third single asset score model where we adjust renewables outputs based on the single asset analysis. In real-time dispatch, we do the same model across the board, but we evaluate across 200 different scenarios. Next case. Okay. Okay, so a few results for that selected day. If you look at costs and real-time prices here, I should add that the costs here are measured in terms of load times real-time price. But orange is the factor model, blue is the baseline, and if you look at the distribution of cost, you see that it's shifted a little bit to the left, meaning that you have reduced cost significantly by moving from the baseline average forecast to adjusting VRE schedules based on the factor model, about 20% reduction in the operating cost for that specific day. And that's because or it's the wholesale cost, I should say, actually. And that's because the prices that you see on the right-hand side also have been shifted to the left. So we have fewer of those high prices with the orange factor model results there. Next slide. You can also zoom in on individual hours. These are two different hours. There we look at the variations in locational marginal prices from using a baseline versus factor, and blue means lower prices, orange means higher prices. So in some hours, you see like some areas with lower prices, others with higher, like on the left-hand side. In that case, New York City, Long Island is it's the congested area, so it's not so surprising perhaps that you see a different effect there. On the right-hand side, you have lower prices across the board. Next slide. And also we had a little bit of load shedding, and that was also reduced once we used the factor-based model to guide our scheduling decisions. Next slide. And we did the same exercise where we used the single asset score model as the benchmark for comparison, and we kind of get the same results, although the magnitude is a little bit less in this case, around 10% reductions in wholesale cost and real-time prices. And next slide. Yeah, again, illustrations of how price differences may vary between different hours. Next slide. And also, yeah, about 20% reduction in the load shedding in this case. Next slide. Okay, so to conclude, what we proposed in this work was to, as a way to address the risk and uncertainty in renewables and system scheduling, was to make use of well-established methods, more like based on statistics, so factor-based analysis and principal components to basically reduce the aggregate forecasting errors in wind and solar generation. And the key there that we are exploiting is that there is, we are accounting for the geographical correlation or covariance between the forecasting errors in different assets. And we do show in the statistical analysis that you can reduce that forecasting error quite significantly compared to an approach where you treat each individual asset independently. And we also show that it's actually quite, it's quite easy to integrate these results into the traditional deterministic unit commitment formulation. We take the standard model, and then the only change we make is to adjust the VRE schedule based on the weights that come out of the factor-based analysis. Yeah, the case study from New York ISO, although it's not a very extensive one, but it still shows that there are potentially significant benefits that could emerge from these types of portfolio-based solutions. So perhaps just to go, more details in the paper there. To go back to the larger project, so this is one type of functionality that could be done by a risk bureau, if such an entity is introduced, and the corresponding schedules or outputs could then be used as guidance to market participants, the ISO perhaps, and also market monitors, with the hope that it contributes to more efficient market solutions. So, thank you.
Thank you. I also really liked your graphs, so thanks for those. All right, so we're going to turn to the Q&A now. As a reminder, I feel like folks online, I see over 40 of you. You're getting a little sleepy on us. Put any questions you may have in the Q&A, and we'll call on you. For anyone with a question, please introduce yourself. And at this point, we will open it up to questions in the room.
Thank you. Alex Rutkiewicz, Newton Energy Group. I am quite interested with your result that three principal components explain more than like 90% of the variation in wind output in New York ISO.
Yeah, actually, it's solar output in that specific case. I forgot to mention that, but yeah, it's solar output. But yeah, go on.
Okay. Yeah. Now, is that just the generation regardless of their location and the implication of their output, say, on prices. If you looked at something like revenues, like market revenues they make, and see whether, in that sense, how many principal components would be necessary to explain that variation?
Yeah, no, it's a great question. So yeah, so to clarify, what we are trying to estimate or characterize is the forecasting errors from those 300 or so, in that case, solar PV plants. So yeah, so what we did find based on the statistical principal component analysis was that as much as 90% could be captured by three principal components. It was done across the New York ISO footprint. No, there's no power systems considerations involved or no like market consequences. So it's purely trying to understand that forecasting error.
No, I get it. It's just if you kind of put a bound on the factor analysis, right? Irrespective of where they are located and what impact they make on congestion, I was just wondering if you do it in combination with, say, the prices they normally, receive, right? And that would capture the impact they make on congestion. Maybe it would be more principal components, but I wonder if that would actually improve the solution.
No, I think it's a great suggestion. We haven't done anything along those lines, really. You could definitely add more, ingredients into what you're trying to estimate and the impact of like transmission constraints and other things. For instance, one easy thing that could be done would be to split the region into different areas. In particular, the New York City, Long Island, perhaps treat that as one area and the rest as another area. But where we do reflect power systems physics, though, is in the second part, right? When we impose these weights on the power system scheduling, it's not entirely consistent because the statistical analysis doesn't deal with physics at all, but still it appears to perform quite well in the second stage.
All right, thank you.
Yeah, thank you.
Do we have any other questions?
Late in the day.
Going once, I know. That post-lunch block is always rough. Oh, we have a question here in the room.
Hi, Adam Suski, Imperial College. So I'm wondering if you're internalizing the impact of the forecast error in this factor that you are calculating through statistical analysis. Wouldn't be more appropriate to use as a benchmark, for example, stochastic unit commitment rather than deterministic one, or potentially unit commitment with some probabilistic forecast embedded, because this is what you are internalizing into the model, but you're comparing still to the conventional deterministic unit commitment.
Sure, great suggestion. So definitely you could use a stochastic unit commitment as another benchmark. And if you have a good model, perhaps, presumably you would use scenarios, and those scenarios, if you can handle many of them, they may capture some of this covariance or correlation effects between forecasting errors. So that's a good suggestion for future work. But yeah, we didn't try any of that, and I guess I could, I talked about how we didn't want to change drastically the way markets are currently operated. So from that perspective, a stochastic unit commitment has been worked on extensively in the academic world, but hasn't really been applied. And there are challenges in terms of having a market on top of a stochastic formulation. Right?
Vishnu Bhattrai from ERCOT. I have a very good question. I think it looks simple enough going from deterministic to just assign the factor that calculates the uncertainties and then assign it before going to the fully stochastic model. But I'm curious, is there any entities that is really using or at least going in that direction?
You mean towards stochastic formulations or
No,
towards
towards your type of
yeah,
formulation.
okay,
Like
okay.
basically, I
Yeah.
do see that as an in between,
Right.
let's say deterministic, all the way going up to the fully stochastic, right? It's
Yeah.
simple enough, easy to understand, but what that word is basically
Yeah.
doing is factoring in the uncertainties,
Yes.
right?
Correct. Yeah, no, thank you. I wish I could say yes, but I cannot really. It's really, we just wrote one paper about this, so it's still early work, but I agree with you. I like the simplicity of this and the fact that you kind of move in the direction of accounting for uncertainty, but without adding too much complexity into your original formulation. So that's some of the philosophy, I guess, behind this type of approach.
Hey, I don't know. This is Allison Campbell from PNNL. So you described your initial matrix of the forecast errors, which will have had to have been observed. So can you comment on how this would be incorporated into any sort of operations system? Would you be, imposing last year's forecast errors, last day's forecast errors, some forecast of what your errors are going to be, and then how do you account for that?
Yeah, it's a great question. So basically, you estimate the factors based on historical forecasting errors. That's right. So they actually, yeah, that's a very good question. How exactly how does that work? So even from one day to the next, you have so okay. So you run, you do your variance optimization, the optimization problem where you minimize variance. So you would update the forecasted availability of the renewable assets when you go from one day to the next, basically. So you re-optimize, but you're using factors based on historical data, but the forecasted availability of renewables assets will be updated from one day to the next. And then, of course, you could redo the factor analysis occasionally as well to kind of get updated factor matrices. So yeah, so that's basically how it would work. Good question.
All right, one more round of applause. Thank you so much. All right, we have one more presenter for this session. So we have Celine Yanikara, and she will be presenting on the significance of high-fidelity resource adequacy assessment, the case of New York ISO. So digging in a little bit more on a case study in NISO.
Good afternoon. Just waiting for my slides. All right. So I will continue on the topic of high-fidelity modeling, which is being discussed in this conference the last 2 days, and we saw some examples of it in the presentations, which is great. So I'm going to continue where my colleague Russ Philbrick left off this morning. He talked about high-fidelity modeling in the context of capacity expansion. I'm going to talk about it in the context of probabilistic resource adequacy, which is still somewhat a common misconception that it's not practical or feasible to do high-fidelity modeling for resource adequacy. So we wanted to share our experience. What have we learned from this granular nodal type of analysis that we cannot from traditional zonal studies? And more importantly, how can we use that type of granular information, risk information, So that's going to be the topic today. Next, please. So we chose the NISO system to illustrate this for a couple of reasons. One is it's a well-documented process. NISO has multiple resource adequacy studies for different time horizons, and their assumptions and inputs are very well documented. Also, it's an interesting system, especially in New York City. There's some local congestion, so we wanted to see how we can represent that or capture that in our high-fidelity probabilistic modeling. So more specifically, we chose the IRM study that NICA performs, 2023 version. So we took the pipes and bubbles zonal version that was used in that study. We replicated it using our software, which is analytics powered by PSO. We reran it, and then we created a nodal version of it, added the nodal configuration on top of it, and examined that version. So we're going to share what we learned from that nodal assessment compared to the zonal assessment. Next, please. But before we go into the study details and results, why do we even care about this, right? Why do we even do this? First, zonal models, and I'm going to be reiterating some of the things that Russ Philbrick, my colleague, mentioned this morning in his presentation. But first of all, zonal models require defining zones, and approximation of the transfer limits between those zones. But in an increasingly dynamic system, especially in terms of congestion patterns, how do we do that, right? Secondly, if we take away nodal details from these type of resource adequacy studies, how do we efficiently coordinate generation and transmission expansion? How do we compare the efficiency of adding transmission capacity on a line versus adding capacity on either end of that line? So adding the nodal details gives us that power. Lastly, planning reserve margin, the assumption that we have some margin on the system, even though some of that margin is on outage, the remaining part will be still sufficient, and no longer holds, right, because of operational details and transmission limitations. That remaining margin might not be usable because of those reasons. So even if your system is sufficient, local issues and shortages can still happen because of those details. So we need to capture those beforehand. Next, please. Next slide, please. So just an overview of comparison of our zonal versus nodal study. In terms of modeling effort, it might sound unintuitive, but zonal models might be harder because we need to define zones and approximate the transfer limits between those zones. In terms of nodal model, the physical system already exists and we have the representation of that. And the approximation in the zonal model in terms of transfer limits and definition of zones under the presence of dynamic congestion patterns, the accuracy and the quality of those results, the risk assessment, is very dependent on those assumptions. Whereas in the physical nodal representation, it's going to depend on the physical realities of the system. In terms of performance, yes, zonal models are fast, especially if you omit the operational details like commitment. But nodal models with appropriate techniques on scenario reduction, it can be on par with, in par with zonal representation. We actually have some past presentations on our scenario reduction techniques that we presented at FERC. So if you find me later, or if you reach out, I can send you those links. But I'm not going to go into detail of how we do scenario reduction in this presentation. In terms of outcomes, zonal assessments do not give us locational investment signals. And it doesn't give us the metrics that can be used to compare generation versus transmission expansion. Whereas through nodal and high fidelity assessment, we can get locational investment signals, which allows us to compare the efficiency of investments. So next slide, please. So now going into the study details, this just shows the data sources used in our zonal versus nodal study. Again, the zonal, the whole study is based on the NICA IRM study, except that we used our own weather data, 14 years of weather data, which gives us asset level renewable shapes and load and historical interchanges. We use that because we do need that for our granular assessment. In the nodal case, our power flow comes from MMWG, more specifically the 2022 vintage. In terms of constraints and constraint definitions and limits, we rely on historically binding constraints from NISO operating studies, but also our own contingency analysis. Next, please. So like I mentioned, we used 14 historical weather years, each of them processed in parallel using cloud computing. And each of those weather years further parallelized into biweekly periods, which all of them those are also processed in parallel. And for each biweekly period, we used 200 outage samples. So we could do more, but for the purposes of this analysis, and you will see the confidence interval results, it was good enough. Meaning that there was clear separation of the confidence intervals between zonal and nodal analyses. So we stopped there, and I'll show the performance metrics as well. We could definitely accommodate more outage samples. Next, please. Just a brief description of the weather data used in this study. Again, we used our own module, which we call Analytics Weather. In summary, it gives us calibrated historical data and asset level wind and solar shapes. Especially for nodal analysis, it becomes very important to use this type of granular weather data. Next, please. So a summary of the studies we performed. The first one is the pipes and bubbles zonal model as used in the NICA's IRM study. We took the same transfer limits and inputs from that study. And then the second model or second study is what we call the reduced nodal, right? So it's a nodal system, but we only include major interfaces. So you can think of it as the transfer limits in the pipes and bubble model replaced with actual physical tie lines. For that, we also rely on NISO operating studies and the limits that are published in NISO documents. And then the third study, the full nodal with complete set of internal transmission limits, constraints. Next, please. But for that one, we have some decisions or options, right? How are we gonna manage the transmission constraints? Will the system allow violation of transmission limits before shedding load to resolve local issues, or are we gonna shed load before violating transmission constraints? Are we gonna enforce them as hard constraints? So we looked at both of these actually. So the study one you see here, we call it the low transmission penalty, and study two, we call it high transmission penalty, meaning that transmission constraints are much, much harder and costly to violate. Next, please. So in terms of the difference between transfer limits in the pipes and bubbles model versus transfer limits of physical interfaces, we still see some differences. Again, one is a physical representation, one is a pipes and bubbles model. So just wanted to show this briefly because this will explain some of the differences we see between the studies. Next, please. So let's talk about overall NISO level metrics from the studies. The green column you see here is the metrics that are reported by the NICA study, IRM study. They reported an LLH of 0.33 hours and an unserved energy of 181 megawatts. So again, we took that same model, same transfer limits, and we replicated it using our software. We matched the LOLH almost exactly. In terms of unserved energy, we are in the general vicinity, but our reported result was a bit lower. That's because we didn't include some of the very detailed constraints in the IRM study, like constraints on how many times demand response units can be called and so on. And we use our own weather data. And then let's see how the physical models perform. Let's go to the next slide. So the first one is the reduced nodal model. So it's a nodal model, but only with major tie lines interfaces. So even that creates or yields a different result, almost 2 times, more than 2 times higher LOLH. And again, that's because of the difference in the physical representation of the system versus pipes and bubbles model. So we still see a difference there. But now let's go to the more interesting part, which is full nodal model. Like I mentioned, there's 2 types of studies we perform there. One is treating the transmission limits as soft constraints, so allowing to violate them to resolve the local issues before we go to load shed. Unsurprisingly, that's closer to the reduced nodal model with only major interfaces. But the interesting thing happens when we go to full nodal and we enforce the transmission constraints as hard constraints. So now we see more than 10 times higher LOLH and unserved energy, and the dispatch of the overall emergency operating procedures like demand response, conversion of reserves to energy, and so on. And if you look at the performance, again, the zonal model, of course, the fastest, but the turnaround time for the full nodal model is also very reasonable because of the multi-level scenario reduction techniques that we use. And again, we use a lot of parallelization to perform these studies. Next, please. So let's now go into what happens at the zonal level. This shows the load shed amount, the unserved energy amount for each zone in NISO, comparing the different studies that we performed. 2 things I want to highlight here. The problems are mostly in New York City and Long Island, as expected. And when we go from treating the transmission constraints as a soft limit to enforcing the transmission constraints, now we see a lot more unserved energy in New York City, right? That's because New York City has a lot of local issues. So it basically exchanges the violation of transmission limits with load shed, a lot more load shed. Whereas we don't see that in Long Island. Even if you have a low transmission penalty versus high transmission penalty, unserved energy is still comparable between those studies because Long Island, the issues there are not driven by local constraints. It's driven by the interface limits into Long Island. Next, please. Same story with overall emergency operating procedures. We can look into those in detail, but yeah, we see a lot more diversity there. It happens in a lot more zones than just New York City and Long Island. Next, please. But how do we look at the locational metrics and locational issues, right? Then we need to look at the marginal reliability metrics. These are basically location-ready metrics that measure the expected change in unserved energy in the system per 1 kilowatt of capacity, ideal capacity added at that location at any given time. So these metrics will allow us to interpret the locational results. Next, please. And we already are seeing examples of marginal metrics and more emphasis on it. On the first day of the conference, ISO New England had a presentation on marginal reliability impact, which is the same definition as ours, except ours is location specific. Next, please. So why is this important? Why do we look at marginal metrics? because again, it gives us the opportunity to look at this at the locational level. We don't get that information from system level metrics like LOLH. And actually, if we go back to the basics, LOLH and LOLP are also marginal metrics, except that we need to redefine them once we start looking at nodal and location-specific models. But these type of metrics give us the opportunity to assess efficiency of local actions like adding capacity at a certain location versus adding transmission solutions, again, on a certain transmission asset. Next, please. So again, LOLP, LOLH, these are also marginal metrics. We redefine LOLP as locational marginal reliability impact. This is basically the kilowatt of unserved energy reduction in the system given a kilowatt of ideal capacity added at a location at a given point in time. So if you sum this up, basically it gives you an analogy to LOLH. So this is what we will use to compare locational results. Next, please. And we can calculate this for the zonal model too, right? Because it has transfer limits between zones, so we can look at locational marginal unserved hours in each zone. In the zonal model, of course, we don't see any variation between locations within a zone because we don't have that information in the zonal model. But one interesting thing to point here, the locational marginal unserved hours in each zone do not add up to the system LOLH because the system LOLH doesn't have a meaningful interpretation once we start looking at locational impacts. But in the zonal model, unsurprisingly, we see a lot more issues in Zone J, which is New York City and Long Island. Next, please. So now let's go into the physical models. On the left, you see the reduced nodal model, which only has major interfaces. Again, of course, we don't have variation within the zones because we don't have internal transmission limits. On the right, we see the full nodal system. So at a first glance, you might think, oh, it doesn't have any variation either, although we start seeing it if you look at Zone E. But if we zoom into New York City, which is the next slide, now it lights up like a rainbow, right? Because we have a lot of local congestion and local issues in New York City, and we see a lot of difference in the locational marginal unserved hours between generation locations. It's interesting to look at because you have two injectors that are so close in distance to each other, but because they sit on different sides of a transmission constraint, they have a very different efficiency in terms of how they impact system unserved energy. So if you add a kilowatt of capacity in that Astoria location, which is the red dot, it's 2 times more efficient than adding capacity to that green dot, right? So this type of marginal and locational metric gives you the chance to compare the efficiency of actions and also in terms of efficiency of transmission actions. Next, please. So we can do this for transmission, right? We can look at the impact of increasing the limit of a transmission constraint on the system reliability, which we call reliability limiting constraints. This is not the same as transmission congestion, which is a fully economic thing, but here we're looking at the reliability impact of transmission constraints. So what is the impact on the system unserved energy if I were to add a kilowatt of capacity on a transmission line? Next, please. So this bubble chart here summarizes the locational marginal unserved hours for transmission assets. Each bubble you see here is an internal transmission constraint, and the triangles you see are the major interfaces. So this compares the impact of reliability limiting constraints. 2 things I want to point here. It's obvious that New York City has a lot more internal congestion than other areas. And if you look at the impact of internal transmission constraints, majority of them are actually more impactful than major interfaces, right? So nodal models give you this opportunity to capture the impact of internal constraints. Next, please. And this is just an example of a specific day with shortage. It gives you the chance to look into individual constraints that are more impactful. in this graph, it happens that the top 20, I think, are from New York City. Do I have another minute or no? Oh, okay. All right, just one more minute. So that was for the nodal part. I also wanted to get into now impact of operational details, unit commitment limitations, and limitations from inflexible generation. If you think about it, this shows just a very regular day-ahead process. We make decisions for an operating day sometime in advance, right? And at that point, the operators have a forecast of the system conditions, including the known system outages, and they make decisions on unit commitment, dispatch, based on that forecast of the system, and then they deal with surprise system conditions when the operating day comes through whatever flexibility left in the system. So the question becomes, what is the reliability impact on during the operating day subject to a base plan that was made? So unit commitment and operational details become very important in this type of analysis and capturing the limitations. Next, please. So we took one weather year and we reran it with unit commitment and explicit modeling of ancillary services. Now we see very large numbers that we don't see in reality, so I wanted to give an explicit disclaimer here, right? These results, we're not saying the NISO system is unreliable, but it provides us a granular representation of the system that reveal locational issues or infeasibilities that is usually overlooked by traditional tools and are normally avoided by operators through various operational actions like relaxation of the transmission limits, rescheduling of maintenance, or dispatch of granular demand response. So that's why we don't see these happen in reality, but we're saying using high fidelity tools and modeling, it allows us to see where the issues might arise, and it gives us a chance to deploy more efficient techniques to deal with those. Next, please. So having said that, we see once we start looking at unit commitment limitations and impact of inflexible generators in terms of min up and min downtime and so on, we see that the hours where the emergency operating procedures are deployed more than doubles. So this is just one single weather year, but wanted to include this because it was an interesting result. Next, please. All right, to conclude, physics matters. We saw that even for the reduced model, once we looked at transfer limits in terms of actual physical tie lines, once the Kirchhoff voltage law kicks in. Location does matter, as we saw in New York City. Generators that are so close to each other in distance have very different impact on reliability. And this gives us an opportunity to also measure the efficiency of transmission investments. So zonal analysis have issues because it requires defining the zones, and congestion patterns are dynamic, and the accuracy and quality is very dependent on approximation of those transfer limits. Sorry for taking too long, and I'll conclude with that. Thank you.
Elaine. We are now going to turn to the Q&A. Folks online, please drop your questions in the Q&A, and we will start with a question in the back of the room.
Hi, I'm Atri from Sandia Labs. So I have several questions for you. So my first question is, for the composite system reliability analysis, which you were calling the nodal analysis, you mentioned many times about the physical characteristics of the transmission lines and also the KVL. So did you do a full AC power flow inside each hour of each sample? That's my first question. Second question is, I saw that you pre-selected the number of samples, which was 2,800, I believe. Correct me if I'm wrong.
Yeah.
So if you pre-selected the number of samples, how did you ensure convergence of your metrics like LOLE, LOLP, LOLH, and all that? And this is more of a clarifying question. The third one, I'm not sure. Did you run the unit commitment for all hours for all samples, or was that done as a post-processing of your RA analysis? Thanks.
I'll start by answering the second question, which is the number of samples. So I mentioned that during that slide, but the number of samples we used for this illustration was good enough because you could see it's very clear separation of the confidence intervals of those LOLH and other metric estimates. So we are able to calculate the precision of our estimate. And for this type of illustration, it was good enough. We could do more samples because the speed of computation definitely allowed that. But for this demonstration, it was good enough for us because, again, the confidence intervals were clearly separated between zonal and nodal analysis. Your third question about do we do unit commitment for all samples? This ties into the techniques that we use for scenario reduction. I'm happy to talk about it offline, but I guess the short answer is no, we are being smart about it. We only do full detailed unit commitment analysis for outage samples that matter. So we do a two-stage approach there, and we can talk about it later. Yeah, otherwise the computational time would explode. So we have some techniques there. Your first question, sorry, what was your first question?
Sorry, yeah, that's a lot of questions. So did you use a full-fledged AC power flow in each hour of all your 2,800 samples?
No, we use a DC power flow.
Okay, so you are just using voltage angles and not the voltage magnitudes or reactive power there.
Yes.
Okay, so I'm not sure how KVL ties into that completely if you're not using a full-fledged AC power flow.
So what was the question? Why does KV matter?
How does the KVL ties into that? The Kirchhoff's voltage law. Sorry.
Oh, I just wanted to show.
We can talk offline. It's
Yeah. Okay.
Okay.
Yeah, sure.
Hey, Sushant Varghese, New York ISO. Yeah, I think this is a pretty good analysis, and I think the results make a lot of sense. I just want to. I had the same question about how you model, the flows, because the models we use right now for our IRM study, we don't model dispatch. We have a Monte Carlo simulation, so we don't actually do dispatch, which I think lets us do a lot of. It helps with computation time, definitely. I think the one challenge I see is, right now we have a zonal capacity market, right? Moving to a nodal capacity market, there maybe it's, that's going to be a significant shift, right? You're maintaining stable market signals, especially if you want to send investment incentives.
Mm-hmm.
Like sending those clear signals may get challenging. That's the one thing I see. But good analysis. Thank you.
Yeah. Yeah, I guess Russ wants to comment.
I'm shocked.
So this is always a constant tension. You want to represent things in a practical way that works with the markets, and zonal representation can make sense when you get to trying to define reward systems for participants. But that doesn't mean the foundational model can't be nodal, and then you abstract it to be the zonal result that you're looking for. Maybe you're just averaging over it, but you do maybe some cluster analysis to make sure that your zones are intelligently defined. But this industry has a history of going through this process of iterating between the simple models and the more complex models. There's a story I like to tell about ERCOT and its market development. It initially thought, hey, we just need a zonal model. That's all that matters. The congestion is all at the high level. And then when they went live, they saw all this congestion at the local level from these intrazonal constraints that they completely thought were not important, or they didn't see them as important before. And the model that they had for the zonal model was actually a nodal model underneath, abstracted to a zonal model. So it would have been an easy thing for them to switch, but they decided to change vendors at the same time, so they messed up.
All right. Are there any more questions in the room? Doing the teacher pause to see if anyone is thinking about it. Alrighty, well, thank you so much, Celine.
Thank you.
All right, thanks everyone. We're going to go ahead and get started with our last session for today. Thank you for bearing with us. Our last session is going to be a little bit longer. We've got 4 presentations lined up for you. Our first presenter is going to be Siva Visvesvaran from Cornell University, presenting on market-based storage, dispatch, and electricity reliability. Thank you. Siva, step forward, please.
Cool. Thanks. Okay, yeah. Hello everyone, my name is Siva Visvesavan. I'm a PhD candidate from Cornell. I work with Professor Jacob Mays as well. First and foremost, I'd like to thank PSEC, the Power Systems Energy Research Center, for actually funding this work under project number M47. And I'd like to thank the folks from FERC for actually giving opportunities for young researchers like us to actually present our work as well. Next slide. So I'm convinced that in every electricity market type of lecture, it's always beneficial to actually give a picture of what we're trying to study here. So here's a graph of CAISO, and this is an event that actually happened on 6th of September 2022. The x-axis is hours of the day, and the y-axis is the net discharge of battery storage in the specific day. And as you all know, CAISO is actually a very solar-heavy system, and the one thing that's actually very prominent in CAISO is actually the duck curve. You want your battery storage to actually appear during the evening hours when there's a huge ramp requirement. But on the 6th of September, something peculiar actually happened. It was a very high demand day, and you can see that between hours 13 to 17, there's actually a really high dispatch of battery storage. And you might be wondering why. Mainly because the price cap for that specific time between hours 13 to 17 has reached, and you being the battery storage, if you want to actually make the maximum amount of revenue as possible, you would actually want to discharge in this specific time because you actually get the maximum amount of revenue. What ended up happening is battery storage was able to exercise that right and discharge as much as it can, but there is some reliability concerns during the evening hours when we actually needed them for the ramp requirement. And the very next day, on the 7th of September 2022, you can actually see battery storage was actually following a similar trajectory of what happened the day before. And next thing you know, the system operator saw this happening and actually decided to introduce an exceptional dispatch towards battery storage to actually not react to the price signal between hours 13 to hours 17. Hence why you see there's a little bit of flatness in its dispatch. But during the evening hours, it can actually appear in its dispatch. So as you can see here, there's actually a bit of a trade-off, right? It's either the battery storage earns the maximum amount of revenue and reliability falters, or the very next day, reliability is preserved, but then battery storage will not actually earn as much revenue. Well, one can argue you can actually have some sort of out-of-market settlement for these types of cases, but it's not really ideal. Next slide. Yeah, and this is not something that I said, right? It's also very well documented in California ISO's own special report on battery storage. The Department of Market Monitor, and I quote, has noted that early discharging on this day can be explained in part by the $1,000 per megawatt hour bit soft offer cap. So basically the soft offer cap, or the offer cap in general, actually distorts the signal and causes battery storage to actually come up with actions that's not really favorable to the system at the end of the day. Next slide. So how could we resolve this type of issue, right? Next slide. So it's actually very similar to human behavior. It's either you introduce the carrot or the stick if you want to actually have some form of behavior at the end of the day. The carrot here is you could actually increase the price cap such that during the evening hours, the prices actually may be higher and batteries can actually react to those price signals. Or you could actually introduce some form of non-performance penalty. So say the battery is actually on the capacity market, it actually has to appear with a certain amount of capacity obligation during times of scarcity. And if they do not appear during those times of scarcity, they would actually incur a non-performance penalty. Next slide. Yeah, although non-performance penalties may be ideal, it's actually very difficult to tune how much penalty you should actually charge, right? And this is a case that actually happened in Winter Storm Elliott. market participants was actually like charged a really high penalty for not showing up during times of scarcity, and there was actually a risk of default. And at the end of the day, PGM actually decided to reduce the amount of penalties for these market participants who did not appear during times of scarcity. So to actually set the right level of penalty is actually very, very challenging. If you set it too high, there's actually a risk of default among the market participants. But at the same time, if you set it too low, the market participants can actually like come out of their commitment by actually like paying the penalty, and then there's actually a reliability risk at the end of the day. Next slide. So this is the main goal of the project, right? We argue that the failure to produce full-strength prices leads to premature dispatch and also leads to potential issues during scarcity events threatening reliability. We show that non-performance penalty, which is basically a product of the capacity markets, can impact real-time operations in terms of battery storage, and does have large impacts on reliability as well. And we also do not want to assume certain like behaviors among battery storage, right? So we also model a risk-neutral battery operator and a risk-averse battery operator. Next slide. So this is the method that we came up with. We actually generated like a parsimonious model where we can actually change the level of price caps and change the level of non-performance penalties. So in the very first box, we actually generate a set of wind, solar, and load scenarios based on historical data. We pass those wind, solar, and load values to an economic dispatch model to actually get a set of pricing scenarios. And based on those pricing scenarios, we pass it to a battery offer module. It runs an optimization to determine what is the right offer, what's the right offer and bid that it wants to submit to the market. And we actually solve a single interval economic dispatch to simulate market clearing in real time. And based on that, we can actually get a binding price and dispatch pair. And also this is an iterative model, right? We actually solve at every time step. So we're regenerating new scenarios based on the current state of the system, and we're constantly solving this type of model. So let's first jump into scenario generation. Let me give you a brief overview of what we do there. Next slide. So first and foremost, we actually use a probabilistic forecast. We hear a lot about probabilistic forecasts in the past couple of days, the day before as well. So here we also use a probabilistic forecast. We specifically use ARPA ePerforms dataset. Envel also provided this data as well, where we are able to get actual wind, solar, and load time series between 2017 and 2018. And we have in the probabilistic forecast of 2018 specifically. We decided to use the ERCOT system because we actually got some realistic generation data from Kate Doubleday et al. From Envel. And we specifically picked 18th of July 2018. The 18th of July 2018 is categorized as a 4 coincidental peak day. It's one of the 4. And it was actually a very high demand period. So it was actually ideal for our study. Next slide. So we actually came up with a scenario generation method, right? It's called KBoot, which stands for KNN bootstrapping method. And it's actually very simple. At the end of the day, what it does is the main goal is looking at the current state of the system, the current operating period right now. Have we seen these types of situations in the past before? And if we have, we can actually use that information to generate scenarios into the future as well. So the KNN part is where we use K-nearest neighbors to actually condition based on the current state of the system, and we use block bootstrapping to actually get all the previous dynamics of wind, solar, and load in the past and bring it to the current operating period to generate scenarios as well. Next slide. So by doing that, unfortunately, this is supposed to be an animation where we actually have a shrinking horizon. But by doing that, in scenario 1 is actually the actual historical data. We can actually generate realistic scenarios that actually follows diurnal patterns. And since it's non-parametric, we do not assume any distribution. This is like just previously historical distributions. We're able to come up with scenarios that tends to encapsulate the actual historical data, which is actually pretty good for us. So this is solar and wind. Next slide. And same thing goes for load. So we actually generate these scenarios every single hour, and we actually solve a shrinking horizon model. Next slide. So now let's jump into the meat of the whole model, right? I'm going to talk about the optimization part. Next slide. So to actually get stochastic prices, we essentially need to solve stochastic economic dispatch model. So it's actually a very simple model. Everything is like pretty much similar to how a lot of papers actually do it. The objective function is just to basically minimize expected cost of electricity. We have standard constraints, demand and power balance constraint, generator limits. The only thing that may be a little bit different is we also have like a pretty good representation of like battery SOC constraints and limits as well. Next slide. And this is our stochastic economic dispatch formulation, but sorry, this is actually, we want to also like try to simulate market clearing, right? So at the end of the day, we can actually like break down this model, remove all the expectations, and we can actually essentially solve a single interval economic dispatch, and that's how we're actually clearing the market at the end of the day. We do have one assumption that's baked into this model. We will not be considering generative ramp rates, since we are more focused in terms of like calculating what's the opportunity cost for battery storage. By including generative ramp rates, that's also essentially some form of opportunity cost as well. So since we are more focused on battery storage, we decided to actually relax those constraints. Next slide. So this is the battery dispatch model that I think is actually the main meat of the model itself. In the objective function, we want to maximize revenue in terms of like the charge and discharge actions. But as you can see, there's also another term there as well in terms of penalties. So this is where the non-performance penalties actually come into the model. Every other constraint is pretty much similar. The SOC balance constraint is pretty much very synonymous to most papers. The charge discharge limit constraints and the SOC limit constraints is pretty much similar as well. The one thing that's different is the penalty constraint. So if you can see there, we're actually representing what's the contribution of battery storage during times of scarcity and whether they meet the capacity obligation in real time or not. And capacity obligation is a parameter that we can actually change as well. Next slide. So in terms of penalties, a lot of ISOs do it very differently. But in this case, in our model, we actually represent our penalties based on two terms, the value of loss load and price cap. So depending on what the price cap we actually set in the specific model, our penalties can actually differ. So in this case, our model, the value of loss load is valued at $10,000. And based on that, based on the value of price cap, it can actually like change drastically. And another thing that I would like to highlight is how we're actually coming up with the bids and offers. So in the SOC constraint, specifically in the first hour, we actually extract the shadow price of that specific constraint, and the economic interpretation for that is basically the marginal value of storage. So in terms of like getting the offers and bids from it, we actually scale it based on the efficiency of the battery storage system itself. So in this case, our battery storage system is assumed to have an efficiency of 90%. So we're scaling that to actually get our offers and bids accordingly. Next slide. And like I said, we do not want to assume certain types of battery behavior. So we also have a risk-averse battery operator as well, and we want to study how risk aversion can actually play a role in batteries' actions. So we actually use conditional value at risk as one of our metrics to actually assign more weight towards the tail ends of our distribution. And this is a standard formulation that's introduced by Rockefeller and Urisev in their 2000 paper. And we actually use something similar for our battery dispatch for a risk-averse agent. And specifically, we can actually tune our beta parameter as well. In this case, we actually just set beta at 0.5. So we're equally weighting the expectation, and also like we are putting a little bit more weight towards the tail ends of the distribution as well. Next slide. So jumping to the results. So first and foremost, you want to establish a benchmark, right? So this graph is basically assuming that the system operator has full control over the battery storage system, and that would be a good benchmark for us to determine what's the right level of actions. So as you can see here, it's pretty good because we do not have any unserved demand. We are charging when prices are actually really low and discharging when prices are really high. So reliability is pretty much preserved in this case. Next slide. So now let's jump to the risk neutral model. Next slide. So this is assuming that the price cap is equals to the value of loss load, and we actually try to run some sort of optimization as well. In this case, the battery can bid into the market. The system operator does not actually have control over the battery storage system. So as you can see, the graph looks pretty much similar. The only difference is the price is a little bit higher this time, mainly because battery is actually bidding into the market, and it's scaled by its efficiency, right? So the delta between the prices is actually due to the fact that it's being scaled by its efficiency. Next slide. And this is a full strength penalty case if we actually have a price cap of $2,000 per megawatt hour. And as you can see here, the prices have been capped at exactly $2,000. It doesn't go above $2,000 at all. And we still have some level of reliability preserved as well. We do not have any unserved demand. And keep this in mind. You might think like, what gives at this point, right? And I'll jump in later on in terms of like, what's the trade-off here? Next slide. So now this is a case of exact same price cap, but then we've actually reduced the non-performance penalty values. And as I mentioned, if you reduce the non-performance penalty values, it's easier for the battery storage to actually buy out its position and not actually react during times of scarcity. So in this case, you can see there's actually a huge amount of unserved demand loss at 309 megawatt during hour 16 when the demand was actually at its peak. And as you can see, the prices are also kind of suppressed. And there's actually a reason why. Next slide. So this is to actually like compare different bids based on different price caps. And you can see that if you set the value of loss load at $10,000, the prices that the opportunity cost that's calculated is actually like pretty high. But then as soon as you jump to $2,000 and $1,000, you can see like essentially the bids and offers that, in this case, the discharge offers that's given by the battery storage to the system operator is actually deflated by a lot. And this may actually affect reliability as well, right? Because at the end of the day, the highest generator in this case is around 500 megawatts. So you can see $500 per megawatt hour. So you can see between hours 10 to 14, there's a likely chance the battery would actually dispatch during this period, and it may not actually appear during the more serious issues between hour 15 and hour 17. Next slide. And we want to see, we want to do some sort of sensitivity analysis, right? We want to actually try to vary the penalty strength and vary the price caps accordingly to see what's the performance at the end of the day. So if you look at the very left, you can see that at a 1% penalty strength value, you can see a drastic difference between the level of unserved demand at the end of the day. In a $1,000 case, you actually have an unserved demand of more than 900 megawatts. And in the 2000 case, you actually have like far lesser than that. So price caps do play a role when you actually have very low non-performance values. But as you increase the non-performance strength, you can actually see that the price cap doesn't matter as much anymore. You can actually see that there's a significant reduction in unserved demand if you actually at the 0.2 or 0.25 range. But as you increase a little bit more at 0.6 or 0.65, you can see there's still some level of capacity left in your battery for the next contingency that may happen. And another thing that I'd like to highlight here is that, remember I mentioned that it's actually risky to increase your penalty strengths in such a high level that would actually cause some sort of default among the market participants. So in this case, we can actually show that it may not make sense to actually increase the penalty strength up to level 1 at full strength penalty, because at the end of the day, at 0.6 to 0.65, you can see already like a plateau in terms of performance. So that's another interesting thing that we actually found in our study. Next slide.
And just a heads up, you've got about 3 minutes left.
Okay. So I want to mention about the missing money as well. So remember I mentioned that in $2,000 case and the penalty strength, full strength penalty as well, you can see that our reliability is pretty much preserved, but then there's actually a huge loss in revenue because the opportunity cost that's calculated by battery storage is around $4,700, but then it's capped at 2,000. So you can actually see a huge loss in revenue, about 235%. This is for the $2,000 and full strength penalty. Next slide. In the case of $1,000 and the full strength penalty case, you can actually see similar missing money in hour 16 during the scarcity period. But then in other hours as well, outside of the non-scarcity period, you can actually see missing money in hour 11, 14, and 15. And this is serious, right? Because like at the end of the day, if you want to remunerate your battery storage, some ISOs, if they actually have like a performance assessment hour in that specific narrow window of maybe 15 and 17, you may miss other windows that you're actually losing your revenue as well. Next slide. So I'm going to quickly go through the risk aversion part as well. Next slide. So when you actually have risk aversion in the mix, as I mentioned before, we're actually putting more weight towards the tail ends of the distribution. So as soon as battery storage actually sees a really high price in the beginning of the day, they might actually discharge more. So in this case, we can actually see significant amount of early dispatch that contributes to the unserved demand in hour 15 and hour 16. And this is actually like well talked about in literature as well. We've seen this in Australia, we've seen this in California as well recently in the 6th of September case as well. So this is basically what we expected and what we got as well. Next slide. But as soon as you actually introduce like capacity obligation, right? In this case, we actually have a capacity obligation of 4,500 megawatt hours. You can actually see that we have reduced the unserved demand in hour 15, and also we reduced the unserved demand in hour 16 as well. So by actually having a capacity obligation and full strength penalty, we have effectively shifted the risk towards the battery operator to actually come up with bids and offers such that it can actually react during times of scarcity. Next slide. And this is a case for the $1,000 case and full strength penalties and high capacity obligation as well. We can actually like reduce our unserved demand by a lot, by 0 in fact. So we've actually preserved reliability. Next slide. And we do something similar, right? We can actually do some sort of sensitivity analysis to actually come up with different levels of capacity obligation. And by increasing the capacity obligation and by having full strength penalties, we can actually essentially reduce the unserved demand. And that's the general trend as well as we increase the capacity obligation. Next slide. So to conclude, we've established that low price caps and low non-performance penalty does affect actions of battery storage and would also cause reliability issues into the market as well. And this actually brings a huge question in terms of how do we actually accredit, right? Because battery storage at the end of the day would actually be affected by these market policies that's introduced. So its actions are actually very highly sensitive to these market policies, and it may not be remunerated correctly in the capacity market, mainly because there is also instances where the missing money could actually occur out of non-scarcity hours as well. And for markets to function well, we may need to actually move towards like full strength prices and penalties, or we actually can settle by overriding the market during times of scarcity. And of course, the latter is not really ideal, and we want to move towards like more efficient pricing at the end of the day. Next slide. Yeah, thank you so much. Thank you for your time. I appreciate it.
We'll now move to Q&A. If I could please invite any speakers in the room to announce themselves or introduce themselves before they ask their question into the mic. Online audience, if you could please enter your questions into the chat.
Hi, Derek Wax, OCNC. Can you elaborate on the penalty that you mentioned on the marginal value of storage? I think you mentioned something about 90% efficiency, but does that mean that that's fixed throughout like iterations of the model?
Mm-hmm. Yeah, for this specific model, it's fixed. And I know like at different SOC levels, it can actually vary by a lot. But to actually like maintain some form of like convexity and to make it not too complicated, because the main idea of the research is we want to specifically study what's the effect of non-performance penalty and price caps, right? So we decided to actually make things a little bit more simple and make things a little bit easier to understand by actually just fixing the efficiency level. Yeah, thank you so much for the question.
Russ Fulbrick. Siva, it's an important problem. I'm wondering if another approach, your results were really real-time results, right? Showing how things are happening in real time. How much were the issues seen in day ahead?
Yeah, so we didn't actually study the day ahead market at all. It's mainly real time. And we actually like just ran the model sequentially at every hour. So unfortunately, I can't actually like know for sure what's the effect in day ahead, but
yeah, because I think removing price caps on its own is not going to necessarily resolve the problem, because in the end, there's always this uncertainty that you have to manage. And is that later peak going to occur? You know, they're chasing the money, and they say, well, I mean, this is the most I can get, so there's no point in waiting, even if I think the conditions are going to be worse later, which is driving your effort. But on the other hand, if there was a day ahead clearing, which forecasts that, which presumably that's why everyone's thinking about the operations needing to be later in the day, that day ahead clearing could actually provide a solution to the problem also, because it says, yeah, sure, you're going to see a problem starting earlier in the evening or in the afternoon, but we really need you in the evening, and there could be a mechanism to tie the day ahead results to the real time results to make sure that people hold their power until the most critical time. So that would be another avenue for dealing with the problem.
Mm-hmm. Yeah, that's fair. I think definitely there could be some information from the day ahead that could be useful for battery storage at the end of the day. But chances are the day ahead market could have some indication of that, and sometimes there's no guarantee that it may have that indication as well, right? So at the end of the day, it's always nice to actually have that real-time information such that the battery storage can actually react in real time as well. And that's mainly the focus of this study. We just focus on the real-time market and see how these specific market policies could actually affect their actions in real time. So.
Hello, I'm Hafiz Badafshan from Habitat Energy. A quick question on the metrics that you used. I'm curious, like CVAR, did you calculate post optimization, or you used it during the optimization, whether it was a constraint or in the objective function?
Yeah, so that's a good question. For the risk neutral optimization, risk averse optimization, right? We actually have we added a condition value of risk metric in the objective function itself. So it's actually like endogenously calculated as it sees new scenarios, right? So, and this is actually a very well written paper by Rockefeller and USF 2000 that I just mentioned as well. I could actually like send you the paper. We are able to endogenously calculate the condition value at risk and essentially put more weight towards the tail ends of the distribution and calculate the shortfall. So it's pretty cool, yeah. But yeah, we're endogenously calculating it.
So Michael Baker, I'm going to speak in a second about this problem, but to your day ahead point, in real time, if you know the day ahead price is going to be higher in the afternoon, you might be short that day ahead price, and so you don't want exposure of some real time spike, and so you actually will probably withhold going after that earlier spike to make sure you're covered in that evening, and so it sort of functions in the way you're talking about. And you can kind of manage the real time pursuing that spike and then still having state of charge in the tank for that evening day ahead period. So you still kind of get that in effect.
Yeah, thank you for your input.
We have a question from online. Trying to see if we can unmute this user. Okay, absent that. Sorry, UG, we'll go ahead and ask your question. UG, who from ISO New England asks, is the benchmark case obtained by time-coupled method or single interval economic dispatch, parentheses, the dispatch without the battery's offer? Have you considered the duration of battery's role in your study, especially from capacity accreditation? Maybe I'm not sure I got all that right.
Yeah, so I think I think I'll start off by actually trying to answer the first question. So to actually establish the benchmark, we also like solve it every hour. So it's not like a one-shot optimization. We actually like essentially have the same set of scenarios and run optimization. I mean, at every hour is different set of scenarios, and then we run optimization based on that. I'm sorry, I forgot the second question. Yep.
Just a moment. Second question is: have you considered the duration of battery, the role of battery's duration in your study for purposes of capacity accreditation?
Yeah, we do. So we actually assume a 4-hour battery storage system. Hence why you actually see like that huge block in the middle of the day that it actually reacts to. So yeah, we do assume a 4-hour battery in this model. Yeah.
Thank you. Do we have any other questions in the room?
I know this is a silly question, but I always have to ask it. Do you assume battery degradation over time?
Yeah, so that's also a good question. It actually ties into the very first question as well, battery degradation and battery efficiencies. In this model, like I said before, we just want to see what's the battery action based on these market policies that could be different. So to actually make the model linear, and also the fact that we're also solving iteratively, we want it to be quick. So we just assume that there's no battery degradation. But actually, essentially, you could add those constraints and make it work as well. But the main focus of the study is you just want to see what's the impact, right, of non-performance penalties and price caps. So that was mainly the focus of the study. We made everything else pretty much simple. Yeah.
Good answer.
Thank you.
All right, we're at about time, so let's thank our speaker once more.
Thank you so much.
Thank you again. Our next speaker will be Michael Baker. Will be presenting on unlocking the full value of energy storage with dynamic optimization software. Michael, please step forward.
Thanks. Hey everyone, really excited to be here. I'm Michael Baker, the CEO and co-founder of Taiba Energy. I started my career 10 years ago reading the FERC Energy Primer, so very excited to be presenting here today with probably maybe the few people that have also read the FERC Energy Primer. So I'm here today to talk about the role that software plays in delivering the flexible, rapid capacity that energy storage assets offer. At Taiba, next slide. We provide an autopilot system that in real time dispatches batteries and submits market bids to the ISOs. And in markets such as ERCOT, where we can update our bids as much as every 5 minutes, this real-time bidding enables us to do real-time dispatch, as well as the kind of forward planning and risk control monitoring that you'll do in the day ahead as an operator. We operate a gigawatt of assets across ERCOT and CAISO and are expanding into other ISOs in the coming years. Next slide. So I think we're all aware that we're facing some pretty significant challenges, both for affordability and reliability of electricity. I very much believe, working in this space, that batteries are going to play a key orchestration role in enabling clean, affordable, and reliable power. And I think it's incumbent upon the power producers in the space, such as our customers, IPPs, utilities, as well as grid operators who are designing the markets, to be able to appropriately signal the value of flexible capacity and fast responding assets, as well as us in the industry to deliver on that and make it so that we have very dynamic software and ability to kind of switch to always sell the right product at the right time. So I've seen this just working on this problem in person, and believe very strongly that batteries will play a really important role in making this happen. What software does specifically is manage the state of charge risk associated with operating batteries and makes sure that you can kind of allocate that finite capacity to the right product at the right time, just like the previous presentation was talking about, making sure you're actually hitting the discharge when it's most needed by the grid operator. Next slide, please. So I want to highlight that, we've long heard about the promise of energy storage. It's really not theoretical at this point. We're seeing in California already, in the evening ramp, storage is often the largest source of supply, supplanting natural gas just in a few years. Similarly, we're operating distribution level assets that are providing distribution benefits to PG&E and other utilities that are trying to maximize existing grid infrastructure. So not only is the flexible capacity important for meeting ramping needs, it's also important for maximizing our existing finite grid transmission capacity, distribution and transmission capacity. In ERCOT, over the last few years, we've also seen, despite significantly rising demand, we're able to both improve reliability. NERC recently showed that batteries improved reliability outcomes by 15% this past year, and deliver cheaper prices. And so, again, we're really seeing in practice the promise of batteries, right in front of us. So I just think, again, it's just really important that, across these markets, we're seeing that in valuing flexible capacity, and companies such as ours delivering on that, we're kind of getting a little bit of a blueprint of how we can proceed and kind of face these massive challenges that we have ahead of us now. Next slide, please. So I'm going to go into a specific example and talk about how this is actually delivered in real time. And so I mentioned a little bit earlier, what we're trying to do is figure out at any given time what is the best product to sell, and make sure we're positioned and available to sell that product. And so best product at the right time. As an energy storage asset, you have up to 5 or more applications that you can choose from, and you really need to make sure you have the state of charge to deliver on that and aren't taking on too much state of charge risk and exposure in the market. And so going back to what we do, we implement a way to kind of balance the different obligations you have in the day ahead or kind of bilaterally with real-time opportunity and the kind of ever-evolving prices. And so we have to kind of combine both forecasting models and a really quickly updating view of what prices are going to be with optimization models that capture the state of charge and degradation and efficiency characteristics of batteries, but also the key market rules that, that how you're able to participate in these markets. And so that's a continuous process that needs to be automated. And to get top performance, you need to be very responsive in delivering that. Next slide, please. So this is really relevant to the previous presentation, but the way we do this, and we can do this in ERCOT because the gate closure is basically instantaneously, we can encode our opportunity costs and our bids. And so they're just kind of simply the way we think about it is there's always a price that we're willing to charge and discharge at. And so how do we determine what that price may be? A lot of things come together, but first and foremost, it's your forecasts. What do you think future opportunity looks like? In Siva's example, we might be seeing elevated prices in the middle of the day, but do we think there's going to be a bigger spike later in the evening that we need to make sure we have state of charge for? If there's a little bit of a dip between those two peaks, we might be able to discharge early, charge back, and then discharge again. And so what this graph is showing is price on the y-axis, time on the x-axis. The green bars are our discharge offers. And so above the kind of lowest limit of the bar, we're willing to discharge. And then the purple is our charge bids. And so if the price goes below the top of those charge bids, we're willing to charge. And so if we see prices jump up in the middle of the day unexpectedly, there's a price we're willing to discharge at. And we might think because of our forecast, we can come back, charge, and then discharge later. And so that the bids here kind of encode our future projection of power. Also included in that is our view of the risk. So I was talking earlier about day ahead. Do you have day ahead obligations later? Do you have ancillary service obligations where you have to make sure you reserve specific capacity? So all of that is encoded in the calculation of these prices. It represents our opportunity cost. Next slide, please. So yeah, I mentioned a specific example. This is kind of a typical day in Texas that we're seeing a lot. Wind is very much driving real-time price spikes. And so when actual wind comes in well below the forecasts, there's a lot of opportunity for potential price spikes, and it can occur, overlapping with the period that the day ahead prices thought would be the peak or not. And so what we see is that, as the forecast comes in, because we can update our bids, we're actually going to raise our offers to account for the fact that we think, okay, there's actually a high likelihood of a spike later. And so we're less willing to discharge now. Next slide, please. You mind next slide? Thanks. So yeah, as I mentioned, there are a few things that go into this, but the price forecasts are really key for that. And you'll see in this chart, there's an area chart that we have. And so that's a probabilistic forecast. And we're looking at what's our mean expectation for the price, but also is there potential for a big spike? And sometimes if we see that, we'll not sell day ahead because we want to make sure we have availability to sell in the real time and withhold discharge earlier. Next slide, please. So to make sure those price forecasts capture that, we have to update them frequently to capture the latest information. And so what this chart is showing is just the evolution of our forecast. Initially, we didn't pick up the fact that wind was lower because we saw the same wind forecasts. And so over time, we caught more and more of the fact that wind was coming in lower and started updating our forward price projections higher, raising our bids and withholding discharge to make sure that we were ready for that kind of peak period. Next slide, please. To do that, our price forecast models are based on neural nets. And so you have to get in training the data or in training the forecasts, you have to make sure that in training, you're seeing the updating of forecasts as they evolve. And you understand, okay, if forecasts came in way lower than what I expected, is that information that I need to take into account, or is that just noise? And so in our training approach, we need to kind of give realistic data for how forecasts update and how our kind of view of the forward projections updates over time throughout the day. Next slide, please. So that's really key. The other component is what I mentioned before, in the day ahead, being aware that there is this potential for real-time spike and not overselling in the day ahead. And so that's where, we'll come up with, before the auction and the day ahead, we'll come up with our full, flow day forecast. And if we're seeing that there is a potential for a real-time spike, that means we'll sell less in the day ahead. And so it's a little hard to see, but this top chart, the purple is our day ahead price forecast, and then the green is our real time. In this case, our real time mean forecast was lower than what we thought the day ahead price was going to be, but we saw that there was that P90 price spike, and so we withheld selling day ahead energy to make sure we were available in the real time to kind of take advantage of what I've been talking about. And so that's a really critical part. The real time engine, no matter what your day ahead obligations are or what your ancillary service obligations are, you still have to operate in real time. And the degree to which you have real-time availability or capacity you can offer is the degree to which you can capture those real-time spikes. And so it's really important to kind of calibrate those appropriately. Next slide. So yeah, so ERCOT has been very much translating its view of what's important, what's valuable through its SCAD and through its LMP signal. They're also adding in ancillary services through the real-time co-optimization. And so you'll be able to sell both energy and different ancillary service products in real time. Currently, you can just sell the real-time product. But what ERCOT does with the rapid gate closure and its volatile price signal is it can make sure that batteries are available and incentivized to be available when there's a big wind miss. And so there is a huge fleet now of battery assets that are just kind of waiting for those opportunities. And so it's encoded the kind of reliability need in the energy price. And the software that I've been talking about is how companies actually kind of go out and deliver that reliability for ERCOT and deliver that affordability, because we can really quickly address those price spikes. So it's kind of it's both, how the market is set up and the fact that it gives a lot of ability for companies like ours to try to figure out how do we efficiently deliver this resource. So next slide, please. So yeah, just to wrap it up here, I really think there's kind of two sides of the coin here. So we've heard a lot of great things. I was really interested in the MISO presentation talking about dynamic reserve requirements. Loving the work that the MISO team's doing on RDC. So the more that our power markets incentivize and kind of provide a range of different services that assets can provide and effectively kind of price in the volatility of what they need, and make it so that we can deliver those attributes in real time, it creates value for energy storage assets, and it creates opportunity for figuring out how can we dynamically offer all of these different products effectively. And so that's really important. And on our end, what we're trying to provide for IPPs, for utilities, is software that enables them to figure out when is the best opportunity, so that they can obviously they're looking to make as much from selling power as possible, but in so doing they're providing the most valuable service to the grid. And so our software and other companies help deliver and kind of realize that value that batteries can provide. And so very much believe that we've already kind of seen the blueprint of what works, and it's working very well. And so now we got to figure out how do we scale that and bring that across the US and elsewhere. So yeah, very excited to kind of share some of these findings. And we'd love to hear what questions you all have.
All right, we'll now take Q&A. Again, please introduce yourself before speaking into the mic. Online audience, please put your questions into the Zoom webinar Q&A feature.
Hi, Celine from Newton Energy Group. Your price forecasts are purely machine learning based, or is it based on any fundamentals modeling?
Yes, it's purely machine learning based, but we do look at a lot of fundamental modeling to sort of figure out what features we think will be predictive and kind of learn from the fundamental based approaches. But ultimately, we're using machine learning. One thing that we found particularly performant about machine learning methods is the degree to which they can rapidly update to meet changing grid conditions. I mean, just over the time that we've been operating, the underlying price formation in both ERCOT and CAISO has changed quite a bit. And so do the models adjust quickly to new information and kind of a new supply and demand dynamic? And we found it to be the case that they're very performant in that regard.
Rob Homer, Energy Exemplar. Yeah, so I'm just going to keep beating on that, price forecasting, because obviously your batteries are going to totally charge and discharge based on the accuracy of your price forecast. Do you have some idea? A couple of things. You said you're constantly updating. So you're respinning the model, your neural networks every hour, or, high frequency, and then do you have any idea what your, kind of accuracy representation is? Your MAPEs or R squareds or whatever else on those? Thank you.
Yeah, absolutely. So yeah, certainly the accuracy of the forecast is the most important thing driving the optimization. And we updated those every 15 minutes because that's kind of the lowest level that we see true signal in forecast accuracy. We look at mean error as well as Spearman correlation, because ultimately we need to kind of predict the rank order of prices as we're trying to charge at the lowest price and discharge at the highest. So that's what we look at from an accuracy perspective. And the forecasts are very accurate. MAE is lower than $5, but they're not going to be perfect just inherently. And so that's where the bidding algorithm comes in that I mentioned. We don't have to be perfect. If we set our bids at the right level, then the dispatch helps us kind of get to that level. And so we find that we are able to hit the peak price intervals as long as we have state of charge. And so really what the forecasts end up doing is making sure you're kind of in an approximately correct state of charge so that you have the ability to sell if prices came in different than what you expected. And so forecasts are certainly important, but it's kind of the combination of that, the bidding and the optimization, that really delivers kind of the top performance in the market.
Yeah, so Yumal from DRW. Assume you operate multiple BSR in ERCOT. When you give the B signal, are you co-optimizing all your operated facility, or you're giving B signal one by one?
Yeah. So we operate we have multiple customers, and they'll have a portfolio of assets, and so they're able to kind of co-optimize across their different assets. But each individual, we're sort of maximizing the value of each individual asset, and each customer has a different risk-reward preference that they're encoding into the optimization. So it ends up being that every dispatch looks a little bit different, by customer, and also because they're at different nodes and have kind of different price formation. They end up having slightly different strategies, but we are always trying to optimize, maximize the revenue at a specific project. That's what's important.
Okay, so when you make decision for each individual facility in your algorithm, did you consider the possible inputs from other facilities?
Yeah, we don't consider that. I don't think we could, just from but we kind of encode that in our price forecasts. And so, we think, the whole grid is operating, or every asset is operating at the same time. We're encoding in our forecast what we think they're going to be bidding and what hours they think they're going to dispatch. So just to kind of maybe make that a little more concrete, we've been seeing in Texas, like on Fridays, specific days that batteries will discharge when the day-ahead price is at its peak, run out of charge, and then there's a price spike afterwards. And so a little bit of a game theory there, and wait for the fleet to kind of run out of battery, and then prices shift more to be determined by gas, and you're in the market to capture those higher prices. And so in our price forecast, trying to capture that dynamic, that's what's sort of encoding the game theory of what other generators are doing.
Thanks.
Vishnu Bhattrai from ERCOT. Very good question. I like the overall presentation, but with respect to some of those numbers, you said like in average it performed 40% better than the other assets, right? The concept is basically you're hedging, playing within day ahead and real time, right? Basically forecasting the price and then optimize between those two. I'm just curious to know your perspective. If the share of those storage increase, how do you see those numbers? Because those numbers seems very impressive, right? But I'm just want to know a little bit more about your perspective in terms of how that varies as the penetration of storage increase or other resource mix changes.
Are you asking sort of if, you know, basically if we can kind of arb out the differences across the fleet through just improved methods?
Yep.
Yeah. Yeah, I think what's interesting now, there is a lot of competition, and so it is very hard to outperform. The degree of the amount of products that you have on offer is, you know, pretty significant, and you're either in one or the other. And so and it's hard to predict which one is going to be the highest. And so even from month to month, you know, who outperforms can change. And so I guess the problem is really hard. And so there's and you know, which product is most valuable is always changing. And so I don't think it's going to be like, oh, we solve dispatch and, you know, we're you know, everybody's figured it out and, you know, there's no edge to be gained. I think there's always going to be a pursuit of edge because of how dynamic these markets are. With RTC plus B, now we have, you know, multiple products we can offer in real time. And so I think that's just going to make the complexity harder. So yeah, I think that the problem's hard enough that there'll always be opportunity for improvements. And because it's, you know, a binary choice, you're either in one product or the other, there's pretty disparate outcomes that can occur from that. And so there is always going to be like a pretty big spread between the fleet. And we're seeing that because, you know, were you in real time and captured the price spikes or not? Were there price spikes in that month? So a lot of different things that really create the variance of performance.
We have an online question. So Yuji also asks, what's the real-time optimization time horizon to find the best offers and bids? And have you observed crowding effect in ERCOT? He gives an example if you need an example.
Yeah, I would love an example of what he means by that.
For example, when too many batteries respond to the similar price forecast, the expected price spike shift to a different time interval.
Yeah. Okay. Yeah. So we have to run the optimization really quickly in order to get our bids in on time. So it is a fast optimization window, and we can do some cool things from software that I wouldn't be able to explain. Parallelization. So it does run really quickly for us to be able to kind of meet market deadlines. In terms of the crowding effect, I think kind of similar to a previous question, but yeah, it means that if we all kind of predict the same interval, that will collapse the price in that interval, and so there won't be value there. And so we need to kind of accurately predict what, you know, given the crowding effect, what's going to be the highest price. And so that might mean the price is later or earlier. Yesterday, the peak was, I think, like 5:45 when usually it's later. And so most, you know, we were able to go after that because we had those discharge bids in, we captured the peak, tried to charge back for the evening. And so, you know, probably most people were thinking, okay, let's wait for the evening spike, but you know, really the peak was earlier. And so it's sort of like a whack-a-mole. You know, if everyone goes in for one price, then the highest price could be a different interval. And so it sort of moves with the crowding effect.
Thank you. Any more questions from the in-person audience? We have one more online question.
Lee, I'll go ahead and let you unmute yourself. Go ahead.
What about collusion among the different, are there just too many batteries to make collusion effective, or is there really going to need to be regulatory protection there? Thank you.
Yeah, I'm not the expert there. I'd love to hear maybe what FERC thinks about that. I think, yeah, the competition will be a nice check on collusion because, yeah, just so many people are pursuing this opportunity and trying to figure out find edge in the market. And so if people are colluding, artificially keeping prices up, then that's a great opportunity for other batteries to undercut that. But I think I am really interested and would love to kind of understand the research better about how does market monitoring work when we don't have a fuel cost, we just have an opportunity cost formulation. And we come up with, I tried to demonstrate, a very principled opportunity cost that's based on our forecast, based on our obligations. I think that type of thing would stand up to the scrutiny of a market monitor, but it's a mathematical formula versus a fuel cost. So I don't know what's the answer there. If you have any thoughts, would be curious. But I think competition will be a nice check, as well as sort of principled and transparent approaches towards optimization.
No, thank you for your answer. It's a very complex question, very interesting question. Thank you.
All right. Well, thank you all for your questions, and let's thank our speaker one more time.
Thank you.
All right. Our next presenter will be a virtual presenter, Ning Qi from Columbia University. Will be presenting on locational energy storage bid bounds for facilitating social welfare convergence. Ning, if you could please share your screen.
Yeah, I have shared my screen. Can you see my slide?
Okay, just a moment. We're getting those up.
No, unfortunately, we can't see your slides on our end. Up. Spoke too soon.
How about now?
Yep, they look good.
Okay.
Thank you. Please go ahead.
Okay, thanks. Okay, so I'm Ning Qi from Columbia University. So it's a great honor for our team, including Professor Xu and myself, to present our recent work on locational energy storage bid bound for facilitating social welfare convergence. So this work is actually motivated by current public bid data by CAISO, and we actually propose preventive regulatory tools to mitigate market power of energy storage and try to improve the social welfare and energy market efficiency. So let's begin. Let's talking about the current state of energy storage market in the U.S. So actually, you can see from this map that most energy storage projects are developed within the electric market regions, like CAISO, ERCOT, ISO New England, etc. And secondly, we have seen rapid energy storage development since 2020. This led by CAISO and ERCOT. They have already deployed over 15 gigawatt and 17 gigawatt energy storage. So given this rapid energy storage development, so it has become essential to deepen our understanding about energy storage market operation and better energy storage market design. So also in the US, energy storage can provide multiple services. Their main operation remains the price arbitrage in the electricity market. The energy storage will charge during the value period when the solar power generation is excessive, and they will discharge during the morning and the evening peaks. And this also aligns with the price curves shown in the green lines. And also we need to know some basic rules for the energy market. First, energy participants should submit their bids first, and the system operator clears the markets. Secondly, the bids from the market participants should convert to their true physical marginal cost. And in the US, the physical capacity withholding is not allowed, but economic capacity withholding is allowed. That means a unit's offer price could differ from their true cost. But if the price differs significantly from their true cost, this suggesting the market power. And actually in the electric market, there are two main contributors, thermal generators and energy storage. For the thermal generator, the fuel price should always serve as a baseline for bid design and market power monitoring. That means for a thermal generator, there is no reason for them to lower and higher their bids significantly from their fuel prices. But how about the energy storage? So for the energy storage, their cost factors are complex and non-transparent. So it's composed of both physical cost and optimal cost. For the physical cost, there primarily lies in the degradation, and it depends on the SOC level. They cannot be immediately measured, but can be estimated based on the marginal degradation cost. For example, it's about $10 to $50 per megawatt. But for the opportunity cost, it's very hard to predict because it depends on the future prices and the forecast on proprietary and uncertainty. And it does not follow any standard process model, and it's hard to predict. So due to the difficulty in predict the future opportunity cost, it's impossible for the energy storage participants to design the optimal bids. So in the market participants, actually for the energy storage, they try to prevent the profit loss in the future. So they will withhold capacity in the day-ahead market to arbitrage in the more volatile real-time market. Well, in the real-time market, they will also withhold capacity in anticipation of the future price specs. So this has been verified in current CAISO and CAISO storage bid data. Actually, CAISO has published their storage participants storage bid data, and we actually compare their average storage bid data with the optimal high-side bid that generated from our dynamic programming approach. And we have seen a huge gap between their bid data with the high-side optimal bid. So this huge gap actually reveals that actually the storage strategic economy withholding may compress the market efficiency and reduce the social welfare. So what should system operator do to address this issue? Currently, there are two measures to enhance the overall market efficiency. So first is design the default bid that directly dispatches the energy storage. This is kind of a mandatory control. And secondly is mitigate market power that prevents energy storage to exercising much impact on the future price. But both approaches are in their early stage of development. For the default bid design, actually, CAISO has published the fourth highest day-ahead RMP with physical cost for the 4-hour batteries. But this approach excludes the future opportunity and uncertainty. So this will only be enforced when local market power is clearly identified. Secondly, for the market power mitigation, it's very difficult to distinguish the legitimate economy withholding from exercising market power. So the question is how could we set the baseline for identifying the storage market power? Okay, so we summarized 3 key motivations for our research. First is the complex storage cost factors. Second is storage strategic capacity withholding behavior will compress the market efficiency and exercising market power. Thirdly is the imperfections in default bid design and challenges in regulating market power. So next, we will propose our locational energy storage bid bound to address these issues. We first look into the one Oracle problem. The Oracle problem is the multi-period economy dispatch And from this problem, we can derive three very important prices signals from the deals of the constraint, from the deal of the constraints. They are electricity price, congestion price, and also storage optimal cost. And by using the Lagrange relations, we can easily to form the true marginal cost of the storage, charging and discharging in the right hand here. But unfortunately, the Oracle multi-period uniform dispatch problem is not achievable because no one can know the future, what the future net load will be, because it's not anticipatory. So thus, the true energy storage marginal cost, especially the optimal cost, is unknown before the real-time cleaning. But this problem motivates our thinking about, since we cannot know exactly the storage marginal cost, but could we generate the cap or robust value of the optimal cost? Okay, that's our bit bound. So for our bit bound design, we first formulate the chance constraint dispatch problem, and we compare it to the Oracle problem. We adjust the net load with 1 minus epsilon confidence level. And then we perform the chance constraint dispatch problem to obtain the optimal cost bounds based on the deals of the SOC dynamics. And we also rigorously prove that the ceilings of the high side optimal cost over any period can be bounded by our chance constraint optimal bound over the same period with 1 minus epsilon confidence. And then we use this optimal cost bound can form the real bit bound, which can dynamically cap the unnecessary high withholdings and monitor the market power of energy storage. And this is our key theoretical results. We also show some very interesting theoretical analysis on the bit bound dependency. The first thing we show that this bit bound is monotonically decreasing with SOC level. That means the bit bound should not be one value, and the system operator should design the bit bound based on the current storage SOC level. Second thing is that we find that bit bound goes up with the system uncertainty. That means energy storage has valid cost to raise their bits in the high uncertainty scenarios, especially for the extreme weather condition and the system with high penetration of renewables. The third thing is that when the system operator is more risk averse, they are more likely to raise their bit bound. But in practice, if the bit bound is very high, it will lose their effectiveness. So we will choose some trade-off value for this risk preference. Okay, that's for our method. We conduct the agent-based market simulation on the ISO New England its-own test system. And because our method is agent-based, so it's transferable to any market, not limited to ISO New England or CAISO. And this agent-based market simulation follows several procedures, including the generation of day-ahead and real-time Monte Carlo scenarios, perform day-ahead unit convenience, and also the real-time market cleaning with varying storage bidding strategy and varying ancillary scenarios. The first results of our simulation shows that our proposed bit bound in the red dashed lines can reliably cap the true optimal cost from the scatter plots here. So that means our bit bound is very effective. And also we show that the CAISO proposed determinate bit bound are relatively conservative and low. And this may reduce the true storage profit. And also we draw the head map to see how our bit bound can affect the system cost and the storage profit. For the 35% storage capacity and 30% renewable capacity, we show that our bit bound can ensure reliable cost reduction. That means there's no cost increase in the system. Then we show that our bit bounds have the highest effect in the high withholding and the low uncertainty cases. And also, there's no effects on low withholding nor high uncertainty cases. This suggests reasonable and legitimate withholding. The overall average system cost reduction is about 0.21%, and the maximum system cost reduction is 0.5%. These numbers are already very large because we do nothing but just release a bid bond. And how about the storage profit? We have seen mixed effect over storage profit. We have seen improved profit at the high withholding levels, suggesting in this area, the storage are bidding very bad. And also we have seen that the profit is reduced at the moderate withholding and low uncertainty cases, suggesting the mitigate market power here. And the maximum storage profit increase and maximum storage reduction is about 90% and 11% respectively. We also do analyze on the bid bond dependency. We show that the bid bond monotonically decrease with the SOC level. And we also see there are higher variation for higher storage capacity. That means the bid bond is sensitive to the storage capacity. This result also aligns with our another work about SOC dependent bid design. But in that work, we designed the SOC dependent bid from the storage participant perspective. But here in our bid bond work, we designed the bid bond based on the system operator perspective. And we also show that the bid bond monotonically increase with the net load uncertainty. And this also aligns with the price taker withholding bids that the bids can increase with the price uncertainty. Another result shows that actually this bid bond is very sensitive to the risk preference set by the system operator. And we have shown that for the larger epsilon here, it will increase the cost reduction effect, but may compromise the storage profit. So we find the optimal setting for the epsilon is about 5% to 10%. But for the CAISO deterministic bid bonds, it's about 15% for the epsilon. It has the cost reduction of 0.80%, but will sacrifice the storage profit by 20%. We do a lot of sensitive.
Dr. King, just a kind note, you have about 5 minutes left.
Okay. Okay. And we do a lot of sensitive analysis on the renewable storage capacity, and we show that our bid bond has better social welfare improvements with a higher storage capacity and economy withholding. And also, because we are using chance-constraint method, it's a stochastic model. So the uncertainty model matters a lot. We have shown that to model the distribution of the uncertainties, it's better to use the empirical quantiles or versatile distribution. But for the commonly used Gaussian distribution, it's not always appropriate because in practice, uncertainties of the distribution will have some skewness and multi-modal. Lastly, the most important thing for new market design and software development is the computational efficiency and scalability. We have shown that our method combined with a relaxed linear model proposed by Maths group in the University of Vermont can achieve tractable and scalable results here. And we have shown that bid bond can be generated less than 2 minutes for even 10,000 storage units. Okay, finally, we will conclude our work. First, the bid bond can reliably improve the market efficiency and regulate market storage market power. And secondly, bid bonds are unit location specific and can be tuned with risk preference and uncertainty model. Thirdly, bid bond has a strong dependency with SOC level, system uncertainty, and risk preference. And through our study, we have understand the storage participants have valid courses for conducting economy competitive withholding. And this bid bound enables system operator to remain risk neutral, fostering competition among strategic storage participation, while capping the offers to prevent excessive withholding. And for audience who are interested in our work, please feel free to reach out for our team and also read our papers online. And in the future, actually, system operator can also develop this speed bound based on other risk-aware approach, like CVR approach or distribution robust optimization. And we also note that for the longer duration storage, this formulation should incorporate a longer horizon and the seasonal and scenario pattern. And this is described in our another work here. And this is for the reference of our work. And thank you. And that's all my presentation. Yeah.
Thank you, Dr. Key. We'll now move to Q&A. Please introduce yourself before speaking to the mic, and online audience, please submit your questions to the Q&A feature in Zoom webinar. Any questions from the in-person audience?
Russ Philbrick, Polaris Systems Optimization. So is your focus mainly on the day-ahead markets and managing market power there, or is it on both day and real time?
Thank you. Both day-ahead and real time. Yeah.
Okay, and you identified correctly that in day-ahead, at least with lithium-ion storage batteries, it's nearly impossible to participate effectively because it's unless you have perfect foresight of what's going to happen in the day-ahead market clearing. If folks were to instead have state of charge management supported by the markets so that they didn't need to bid at all, do you still see market power issues of any sort?
Yeah, good question. Actually, so our bid bound is, actually we do not directly enforce our bid bound on the storage bids. Actually, we actually just propose this bid bound to prevent storage to isolizing excessive withholding. So when the system operator observe the storage has excessive withholding, they will enforce this bid bound. But it will not always enforce this bid bound. So it still allows storage strategic bidding. Yeah.
And considering that most of the market power issues are actually from portfolio bidding rather than just single unit bidding, how does the bid bound take that into account?
Yes. So a very good question. Actually, our bid bound is designed for locational. So actually, it can be designed basically align with the locational marginal price. So actually, it's not just for a specific storage unit, but it can be just enforced on the portfolio of the storage units. Yeah. Based their locations. Yeah.
Do we have any other questions from the in-person audience? At this time, there are no online questions, so we'll go once, go twice for in-person. Hearing none, let's thank our speaker one more time. Thank you, Dr. Key.
Yeah, thank you.
Right, our final presenter for today will be Jerry Wong from Columbia University, who'll be presenting on battery operations in electricity markets, strategic behavior, and distortions. Hi, Dr. Jerry, we see your camera.
Yes, so I'm sharing my
screen.
Yes. Screen sharing for this. Good.
Yeah, we can see your screen. Looks good. Take it away.
Hello, everyone. I'm Jerry Wong. I just graduated from Columbia and will be a postdoc at University of Washington, then join Yale as faculty next year. I'm very happy to be here to talk about my work battery operations in electricity markets, strategic behavior and distortions, joined with Santiago Balcero, Omar Bespes, and Bolun Xu. The electric grid is undergoing a transition with the rise of renewables such as solar. The picture on the left here shows the average daily generation by field type in California in April 2021. The x-axis is hours of the day, and the y-axis is the amount of generation in megawatts. We can see different types of generation: nuclear, hydro, wind, solar, gas, and imports. In particular, we see a big bulge of solar during midday, displacing gas plants, while other sources of generation are roughly constant throughout the day. But the issue with solar is that it produces energy when the sun shines, not necessarily when you need the energy. For example, during the peak demand at 8 p.m., there's no more solar because the sun sets. Batteries are a natural complement to solar because we can control them and they can shift energy across time. We can see a dramatic rise in battery capacity here. In this graphics from New York Times, the left is April 2021, barely any battery. Just 3 years later, in April 2024, the battery capacity is now around 25% of peak demand. These batteries are grid-scale battery storage facilities specifically built to arbitrage the grid. They look like these, like a football field with rows and rows of container boxes with lithium-ion batteries in them. And they're built by big companies like Tesla. Because these batteries are so big and their ownership so concentrated, regulators are starting to be concerned about the potential of battery market power. To mitigate the market power of these batteries, California regulators launched the so-called Storage Default Energy Bid Initiative, where they say, none of these storage resources are currently subject to market power mitigation, and the regulator believes that it is important to develop mitigation measures to manage market power, given the rapidly growing number and influence of energy storage resources. They also wrote a special report on battery storage where they documented unusual battery behavior. They didn't say outright in the report that it was market power, but we will later see with my model that these behaviors can be rationalized as a consequence of market power. When we see that these batteries arbitrage the grid, what do they really do? They buy energy from the grid during off-peak when energy is plentiful, and then they sell it back to the grid during peak when energy is scarce and the price is high. The key thing is that what drives the energy price is not the total system demand, but the net demand, defined as system demand minus renewables. This is the part of demand that needs to be covered by dispatchable resources, which can be conventional generators like coal and gas plants or batteries. This is the plot of the hourly net demand in Los Angeles in 2019. During midday, there is a lot of solar, so net demand is low and price is low. So off-peak is during midday, as we can see here. At 7 p.m., the system demand is highest and the sun sets. So no solar, net demand high, and price is high. Year over year, solar increases during midday, where system demand stays constant and the net demand goes down. So like this one is from 2019, and we can see here in 2020, 2021, 2022, and 2023. We can see the net demand during off-peak going down while the peak staying the same. So that means that we need more fast power plants to adjust their production up, to ramp it up quickly. And these plants tend to be both costly and polluting, negating part of the benefits of renewables. This is, as everyone here already knows, is called a duck curve. And batteries then do grid arbitrage by shifting energy from off-peak to peak. Ideally, the battery profits from the price gap between the peak and the off-peak. And it also ideally also helps the system by alleviating the ramp and shifting energy from off-peak when it is cheaper to the system to peak when it is more expensive to the system. But they are not quite the same objective. So the central question is this, like how aligned are these two things, battery profit and system objective? These considerations then motivate our research questions. First, how do batteries operate in electricity markets? That is, as a function of market conditions, how, when, and how much do they charge and discharge? Secondly, how does the strategic behavior of decentralized batteries distort decisions compared to centralized batteries? And lastly, what is the impact of strategic behavior on system performance? Here's the outline of the talk. First, electricity markets are very complex with many interacting entities. We propose and solve a tractable analytical model that is rich enough to capture salient features of this market, but also yields operational and economic insights. We can then explicitly characterize how a centrally optimal battery behaves and how an independent, self-interested battery behaves. And we identify 3 types of distortions, or ways that a profit-maximizing battery behaves differently from a centrally optimal battery. We then quantify the loss resulting from strategic behavior through the analysis of price of anarchy and calibration with real data. We then analyze the effects of market power, mitigation measures, and the effect of competition, and show that our insights continue to hold under extensions of this model. First, the model. What are the features of real electricity markets that we want our model to capture? We want our model to capture the following. First, the market clears in 2 stages, day ahead and real time. The day ahead market clears 1 day in advance based on the forecast, and the real time market clears the day of based on actual realized demand. We will discuss more about this in detail because it is a central feature both of our model and of the real market. Then, generators or power plants are also heterogeneous in their ramp speeds. Some of them can ramp really fast, some of them not so much. They also have different costs captured in the supply curve. We have also seen the duck curve demand trend, where we want to capture the fact that there temporally is a peak and an off peak, and that this demand can be random as well as correlated across time. The 3 entities in our model. First, the net demand is a system demand minus renewable generation. Both of these are both exogenous and treated as non-strategic. This is mostly true. Secondly, conventional generators. And thirdly, batteries. Here, we assume that batteries are strategic, but conventional generators are not strategic. This is in part to highlight the effect of battery strategic behavior, which is the focus of our work. But also that I think to the first order, it is reasonable to think of conventional generators as non-strategic most of the time, given that like the regulators have been controlling the market power of these conventional generators for over 20 years. And it is also easier to see what the default bit should be based on like engineering and operational characteristics. Whereas batteries are based mostly on opportunity costs, which are much harder to determine precisely. Initially, we will be assuming the extreme case, which is like we make the battery very powerful, that there is a single battery, a monopoly, it is perfectly efficient, and it has enough capacity. We'll be showing that even in this case, the battery market power is like non-trivial, but still bounded. We can quantify like what shapes the battery market power, and also shows that when we add like realistic features, such as competition between batteries or capacity constraints, the battery market power would be reduced even further. This is a duck curve, which we can capture in the simplest way by a 2-period model, where we have the peak demand and the off-peak demand, which are jointly drawn from a distribution. This captures the randomness as well as the correlation across time. We can also, later in the extension, extend this to a model with T, arbitrarily correlated demand. Okay, so here are the 2-stage market clearing. First, at a high level, there is a day-ahead market, which is based on the forecast, and the real-time market, which is based on realized demand. The day-ahead market is useful for two things. First, it is a forward market that reduces uncertainty for participants. And secondly, and more importantly for our model, is that we have some slow generators like coal and nuclear that takes time to start and to ramp up. So they need advance notice to produce. And this is a financial market. No energy has yet flowed yet. And in contrast to the real-time market, which is both financially and physically binding, it is based on the realized demand such that demand must equal supply at all times. We now look at conventional generators. To capture the heterogeneity in ramp speed, we assume that there are two types of conventional generators. There is a slow generators, such as coal and nuclear, that can only participate in day-ahead, as well as fast generators that can participate in both day-ahead and real-time. They all have different costs, which we assume to be captured by model primitives, the supply curve, which is that the GS and GF tells you how many generators there are with cost below a certain price P. We will make another simplifying assumption, KF, to be the share of fast generators at each point. We can then write GS and GF as like multipliers of G. We have seen earlier that the two-stage market clearing, we can now formalize this in our model. There is a day-ahead stage, and there's the real-time stage, and there are two time periods, peak and off-peak. So there are actually four things where you are clearing. You have day-ahead peak, day-ahead off-peak, real-time peak, and real-time off-peak. The demand in day-ahead is taken to be the forecast, taken to be the expectation, ED peak and ED off-peak, and the real-time market, which is the actual realized demand. And here is the key, which is that the battery, which is like our main player, makes decisions, which is how much to discharge the Z's in day-ahead and real-time. Where in day-ahead, because they're all based on forecasts, these are scalars, and in real-time, you can make decisions based on the realized demand history, so these are policies. Subject to the constraint that because the battery doesn't produce energy, it only shifts it around. If we assume that it is perfectly efficient, then the amount of charging must be equal to the amount of discharging. And because we also don't assume capacity constraint, we just need to keep track of how much it is charging and is discharging, or that the sum of the Z's, the total net discharge over the day or a time period under consideration to be zero, both in day ahead as well as in real time. Now, we give a model of how the prices are formed or how markets clear. The key thing here of battery market power is that their decisions, the Z's of how much they charge and discharge, can affect the prices. And they affect the prices such that the price has to be where the supply equals demand for each time period. That is, for each time period, first you have the market clearing in day ahead, where the red thing here, the day ahead price, has to be such that the supply from slow generators plus the supply from fast generators together, this is the amount of energy that is being put on the grid, must be equal to the amount that is needed, which is the EDT, the forecast net demand, minus battery discharge. Where remember, when the battery is discharging, our convention says that Z is positive, so that when the battery is discharging or putting more energy into the grid, the right-hand side goes down. Then like the generators would need to produce less energy, and vice versa for charging. Now, you have the slow generators. They cannot change their production in real time anymore because they're slow. So you can see here, it's the same. The only thing that can change are fast generators. So the real-time prices, as well as the generation from fast, would adjust such that the supply from slow plus supply from fast still equals to the amount of energy that is needed, which is now the actual realized DT, net demand, minus battery discharge, which is from the day ahead as well as from the incremental real time. This thing would then give you an equation that tells you how the prices, the day ahead price in red and the real time price in blue, is determined based on your the battery's decisions, the ZDA and the ZRT. And you can then do some algebra to solve for PDA and PRT explicitly in terms of Z. Now, we are looking at the battery as the main strategic player, and we are looking at this at 3 regimes. The first is a no battery status quo benchmark. The second is a centralized battery where you want to, like you are a grid operator, assuming that if you control the battery, you want to minimize some notion of social welfare, which we captured as a generation cost. And lastly is a decentralized battery, where you have like an independent battery, maximizing its own battery profit. Remember that we want to see how the centralized and the decentralized battery behaves differently. There is some related literature, which these audience might already be familiar with. Literature on forward and spot markets corresponding to our day ahead and real time in our models. Some literature on batteries and renewable operations, as well as on flexible resources, which are not quite batteries, but they have similar functions in that they can smooth demand across time, as well as some black box models of batteries with price impact and empirical structural work on batteries. Okay, now we have described our model. We can then identify the 3 types of distortions. First, we have our model. We can show that both the centralized and the decentralized problems are convex infinite dimensional optimization problems. We can then solve these explicitly, and then you can give the expressions for the centralized and the decentralized, which tells you how the battery is behaving as a function of market primitives. The algebraic here expressions are not particularly important compared to the interpretation that we can look and compare between the two and see how they're different, which we can interpret as 3 types of distortions, which I will now talk about. First is quantity withholding, or that the battery does not charge and discharge as much as it should. The intuition here is that you have 2 periods, peak and off-peak. If you are centralized, then you would want to minimize generation costs by equating the net demand between 2 periods, so that because you want to shift energy as much as from when the marginal cost is cheap, where to the period where the marginal cost is expensive, up until the 2 periods have the same marginal cost, but then the 2 periods have the same price, and which would lead to 0 battery profit if you are trying to charge and discharge at the same price. So a profit maximizing battery would not do that. A decentralized profit maximizing battery would only partially smooth the demand, capturing the trade-off between higher quantities and the needs to maintain price differences. You can do some hand waving math to see, okay, like what does it mean to have equal? And you can see exactly that this amount, half of the difference between peak and off-peak, shows up in the centralized battery discharge. Whereas it's decentralized battery discharge, the sum of the 2 purple things are less than what the centralized thing, and this is quantity withholding. Secondly, is the shift from day ahead to real time, where the main channel is that the battery hides some of its capacity in day ahead and only makes it available later in real time. And this is a structural consequence of sequential market clearing. And it holds even in the simplest case when there's no randomness and when you have day ahead and real time are identical markets with the same price function. If you want to maximize profit, you can write down the expression as maximizing the sum of day ahead profit, the quantity ZDA times the price PZDA, plus the real time profit, which is in blue, the ZRDT, the quantity, plus the price, which is determined from the sum of the day ahead and real time discharges. And draw the picture, we can—
Excuse me, Dr. Anuj Rajwang. I'm sorry to interrupt you. I just want to give you a 5-minute warning. We're aware that you have a lot of slides to get through as well, so if you could please move along.
Yes,
that would be great.
I skipped like much of the later. Okay, but thanks for warning. So yes, So we want to maximize the area, and then you can see that like you have you need two rectangles rather than one, corresponding to the two types of distortion. And you can see here in the expressions as well, where from nothing to like doing something. And the third distortion is reduction in real-time responsiveness, which has the same intuition as the quantity withholding, but for real time. And you can also see this as well in the red, where this is the amount that you are responding to real time. Okay, so we have seen the amount of the ways that they are different, but how costly is this? We can capture this by defining the price of anarchy metric that captures the incentive misalignment, looking at the amount of cost reduction that you can achieve in the centralized divided by the decentralized. So this price of anarchy is always greater than or equal to 1, and the lower price of anarchy, the better the alignment. We can prove that the price of anarchy is always bounded between 9/8 and 4/3, which means that there, on the one hand, there always is a non-trivial like incentive misalignment, at least 12.5%, but also that even in the very worst case, you can have no more than 33%, so that like you would not have the situation where like you can have like a battery blowout that have like a really arbitrarily bad. And we can do calibration with real data from California and also find that, say that in Los Angeles, we might get 1.15, and in Houston, you have 1.25, which tells you that out of all the best possible cost reductions, just having enough decentralized batteries already gets you most of the cost reduction that is possible. This is what we mean when we say the price of anarchy is bounded and not very large. So this suggests that if you are a regulator, like working in a working in a nascent market, you might want to prioritize like encouraging entry of batteries first to increase competition and also to have capacity in the market, and worry about like fine grain like market mitigation later when the market is more mature. In fact, we can prove like so far we show that even with monopoly battery, the effect of competition is limited. When you have competition, the effect is even stronger. If you have N batteries, the price of anarchy goes down as 1/n². So competition is very effective at aligning incentives, with the caveat that it would reduce the battery profit and might discourage entry. In contrast, we show that like a few ways that you might want to do market power mitigation, such as like introducing virtual bidders or requiring that the battery is discharged 0 in expectation can lead, or subsidizing battery discharge can actually backfire. So you have to be careful. Lastly, I want to we can show that like our insights of limited battery market power continues to hold in extensions when the battery has limited capacities, or when we consider joint investments and operations problems, when we look at convex supply curve, or that when the battery is like not perfectly efficient, as well as like for any T number of periods. So to conclude, we propose a tractable analytical model. We then solve it and find 3 forms of distortions. We show that the loss from market power is non-trivial but bounded, and that competition is effective, but market power mitigation measures, if not careful, can backfire. And this is also like a stylized model that can include like realistic features and is a building block for future work. Thank you.
All right, thank you very much. We'll now move to Q&A. Any questions from the in-room audience, please introduce yourself before speaking into the mic. And virtual audience members, please put your questions into the Q&A in Zoom webinar. Any questions from the in-person audience? Any questions online? Okay, going once, going twice. All right, well, let's thank our speaker again. All right, thank you, everyone. That wraps up today's conference. We'll be back here tomorrow morning let me make sure I don't tell you the wrong time. We'll be back here tomorrow morning at 9:15 a.m. We'll have dual track sessions in the morning. There'll be a session in here and a session in hearing room 1 next door. So 9:15, we'll see you tomorrow. Thanks.